Well, why don't we go ahead and get started? On behalf of the Mesoscale Microscale Meteorology Laboratory, I'd like to welcome you all to our joint WRF MPAS users workshop that we convene annually. And to get things started, I'd like to introduce our lab director, Gretchen Mullendor, to provide some opening remarks.
Thanks, Joe, and good morning, everyone. So I have 15 minutes, but I don't think I need quite that much time, so maybe we can get going early. We're going to hear about a lot of exciting work over the next few days, and MPAS has exciting new capabilities and continues to grow. You know, I feel like MPAS reached some sort of weather nerd milestone when it got picked up by Pivotal Weather, and thanks to NOAA and NSSL for helping make that happen. So yay, go weather nerds. Okay, and then, you know, WRF, we're going to also hear about its continued growth. You know, again, NCAR is no longer investing core funds in the development of WRF as we focused on MPAS, but the community continues to put in development, and we are committed to continuing to put those into the releases that we do as MPAS matures. We're also going to hear about a lot of really valuable research and critical operations done using these modeling systems. And ultimately, I think that's why we're all part of this endeavor. I mean, we are trying to test and build and develop the best models to provide understanding about the changing atmosphere so that we can help others reduce risks to their lives and livelihoods. This is why we do what we do. And I want to thank today all of our organizers for helping put this together, and all of the MCube staff that support MPAS and WRF, and thanks for NSF for helping support those staff that help put this all together. But most of all, I want to thank all of you, both everybody here in the room and everybody online. Hello online, good to have you here. The success of MPAS and WRF is really because of all of you. The NCAR models are successful because of co-development with the community. So thank you to all of our federal agency partners. Our community is strongest when we all work together. Thank you for all of our international partners. It's exciting to see MPAS tested and improved for applications across the globe. Thank you to our private industry partners for bringing in cutting-edge technologies and sharing them with the broader community. And a huge thank you to the research community. We do not lead as modeling systems without all of the innovations you bring into the models. And I want to give a big shout out to any students here. You are going to be the next generation of those leading in model development and use. And thank you for being here. It's exciting to have you here. So we have 2 afternoon discussion sessions scheduled this week. There's one this afternoon, and there's also another one on Thursday afternoon. I really do hope you'll participate in those discussions. I want to hear from the community, and the communities want to hear from each other. You know, what is it that we need to do next? What is missing? What should be the priority? What is our next step? So I really hope you'll all stick around and participate in those. I will be there for all of those. And if you, for some reason, don't get heard in those, you can grab me or someone else from the MPAS or WRF teams to talk to them. We all really want to hear what you're all thinking. So thank you for being here to present, but also I hope we'll have many, many great discussions. So I want to thank you all again, and I hope to see you at the reception this evening, and let's have a wonderful workshop. Thanks, everyone.
As you can see from the slide, this is the 25th WRF workshop, as well as the 7th MPAS one. We actually did our first WRF workshop back in the summer of 2000, which was before we even released the first version for community use. So there's been a lot of evolution of the modeling system over those years. As you know, traditionally, these workshops have always been in person as we developed a larger and larger participation over these years. And then the COVID pandemic hit, which shut us down for 3 years, 2021 and 2, we shifted to a all remote workshop, which certainly changed the flavor and tenor of things. Last year, we got back to having an in-person capability in a hybrid format, which I think worked out pretty well. And we're doing a similar thing this year. One encouraging thing for me is the number of in-person registrants has increased significantly this year over last year. I very much hope that we can continue to build the in-person participation as we can, because there's a lot of benefit in just the informal interactions that we have during the week. We have about 30 graduate students and postdocs, which is good to see. One thing we don't keep track of is how many are attending for the first time to these workshops. Can I see a show of hands? How many are first time participants? Wow, we have quite a few of them here. Well, that's really great to see. Very much encouraged to see that. So just to say a bit more about why we're here and what we're trying to accomplish. During the workshop this week, it's an opportunity for us to learn about the recent model improvements and updates, for all of us to share our modeling research with others, as well as to hear about what others are doing in their modeling research. As Gretchen mentioned, we want to discuss our community interests and priorities related to model development and support. And I can reinforce what she said about please participate actively in these discussion sessions. And on a more informal basis, there's the opportunity to strengthen professional relationships, interactions, collaborations, and so on among community model users. As far as the schedule, it's laid out here. We'll be having presentation sessions over the 3 days, today through Thursday. We have half-hour breaks in the morning and afternoons, and an hour break for lunch from 12 to 1. The lunch is being provided out in the atrium here, so you don't have to run all over town to find something to eat. And the patio area outside, I'm sure, will be open so you can get your food and sit outside if you want to eat as well. So we'll be beginning as usual with talking about model development updates and so on, and then moving toward applications. This afternoon, we have our first discussion session on development and support of MPAS in future application spaces. And I hope that gets everyone's juices flowing, because it will immediately move to our reception, where there'll be plenty of food and drink and opportunity to discuss issues further, and also enough so you can certainly consider that as enough for dinner as well. On Wednesday, we have the poster session in the afternoon. We'll have an opportunity for each poster presenter to present one slide for about a minute to promote their poster. The posters are all going to be up over in this area here. I want to encourage the poster presenters can put up their posters right away or anytime they want, and leave them up for the whole workshop, so people can look at them anytime. And then at the end of the afternoon on Thursday, we'll have another discussion session on that's more open to any topics or issues that you care to discuss. On Friday, there's a couple of mini tutorial or instructional sessions. The first is on structured grid visualization, and the second one is learning about GPUs. GPUs for dummies is the way I would think of it. So anyway, I want to encourage you all again to participate actively and get to know each other and have an enjoyable week. So with this, I'll turn it over to Jordan Powers, who will chair the first session.
Welcome, everybody. Our annual tradition. It's great to see a lot of familiar faces and a lot of new folks, too. We'll have 3 speakers in the first session today, which lasts an hour, and then we'll have a coffee break. For those speaking, I've got the box that we used to use. If you see me holding this up and the light is red, it means your time is up. We'll start then with a tradition of the workshop, and that's to get an annual update on WRF. And presenting that today will be Jimmy Dudia for the 2024 annual update. Jimmy.
So yep, this is the 25th annual WRF workshop. And so I guess it's like a silver anniversary. I didn't realize that until now. And we've had a quarter of a century of this model. This update will go into what we've done in the last year, which is basically everything since version 4.5. I'll recap what we released last year and that I talked about last year, and then a couple of bug fix releases between, and then version 4.6. So first I'll talk about version 4.5. And as I said, the version 4.5 last year, so if you came last year, you'll be familiar with all this. We had the new Grapple and Hale aerosol aware Thompson microphysics option. We had a new PBL scheme by Andrea Zanato, K epsilon theta squared PBL scheme called KEP. And the new T-key cumulus scheme was made scale aware by Wei Wang here. Bug fix version 4.5.1 in July last year. We corrected the counter gradient term for, if you recall, last year we were showing problems with the CAPS scheme over oceans, and that got fixed in July. Also, other minor fixes can be found on our regular web page that you find on our GitHub. 4.5.2 was December, where we fixed some rain auto conversion problems that have been problems since version 4.4 in 4.0 in WDM6 and WDM7. So if you're using those schemes, try to upgrade your version. We fixed the calculation order and the immediate melting in fast SBM. That's a bin model that we have. Minor fixes for the polar boundary condition, which people aren't using because it's the global implementation of WRF that now is taken over pretty much by MPAS. Other changes are needed for the new derecho computer at NCAR because they have the new compilers and new versions of Intel as default. And then other minor fixes are listed here. So new in version 4.6, which we just released in May, shared physics suite. I'll go into these in more detail. 3 new wind farm parameterizations provided by Delaware, a single layer UCM urban canopy model enhancement, which I think you'll hear more about in the LSM talk, Ocean salinity effect, I'll mention that later too. NSL microphysics was significantly changed, although there's a new scheme added, the 3-moment. MYNN, PBL, RUC LSM, they had updates, which I'll briefly mention. We also have now an option for a CMAQ compilation I'll go into later, and then minor changes. So the shared physics suite is something new. It's our attempt to go towards sharing physics between WRF MPAS and even in the future CCPP, which is the physics sharing mechanism in the NOAA model and the new CMA model. So we're trying to go in that direction of having a common repository, at least now for now, between WRF and MPAS and CM1, which shares one suite of physics, and it's this suite, what we call the tropical suite, but not the LSM or radiation. So it's a revised surface layer, the new scale-aware TKI scheme, the WSM6 microphysics and the YSU PBL, and we also have the orographic gravity wave drag in there. Oops. And the shared part is just the lowest level routines, the 1D or 2D physics routine. So the driver is still in the model, the individual models still retain the driver that calls those shared physics. This is more similar to the way CCPP, Common Community Physics Package, accesses physics. In CCPP, you also need a meta file to describe all the arguments in detail and what each variable actually is. And we have those meta files, but we're not currently using them in WRF and MPAS. So we have an MMM shared physics repository on GitHub. Laura Fowler will talk a bit more about that. And DTC has ensured that this is CCPP compatible with the meta files, especially working. And there's a talk by Weiwei Li later on about that. The wind farm wake models are new to us. They're provided by University of Delaware and Yulong Ma, Christina Archer, etc. And they're basically 3 wake models, Jensen, geometric, and Gaussian. And there's 2 wake superposition models, wind farm overlap method. And you can actually run an ensemble of combinations of these. They've optimized the ensemble. This paper describes how they've optimized that ensemble. So basically, when you have a wind farm or maybe 2 wind farms, you have the wake from one wind farm, which can interfere with the other downwind wind farm. And these parameterizations are different ways of dealing with the wake effect on downwind turbines. It can be, so you can run these individually, or it's an optimized ensemble, which the paper recommends. Ocean salinity effect, that's something that came to our attention in the recent years. And salinity typically reduces the water saturation at the surface by 2% for a wide range of realistic ocean salinities. So we've implemented the 2% reduction over the oceans. This should only apply when you're at ocean points, not freshwater or lake points. So we use the lake mask to avoid lakes when that's available. And it generally is available if you choose the modus option with lakes for your land use category. So we haven't found a major effect from this 2% reduction, but it can reduce the moisture and give you better verification of the water vapor over the ocean surfaces. So in version 4.6, this is activated by default, so you don't have to do anything to turn it on. And there's a salinity factor parameter, 0.98, which you can find in the surface layer code. As I said, it's only in the surface layer, MM5 surface layer schemes. And there's a parameter you can change if you don't want it, you want to test it. NSSL microphysics from Ted Mansell. They've added a 3-moment grapple scheme, hail and rain, and so it predicts a reflectivity moment in addition to the number and mass moments. So that gives you better size sorting while preventing reflectivity growth, and compares well to the bin scheme. The 3-moment scheme also uses a more robust grapple to hail conversion using a wet growth diameter. Also, TED has consolidated all the NSSL schemes, which used to be multiple MP physics options and still are, they're still available, but we want to phase that out in favor of having this MP physics equals 18 plus a set of nameless options to turn on whether you're using double moment, for example, or aerosols, and those kinds of things are now nameless selectable. And so in the future versions, we'll consolidate everything in from NSSL to MP physics equals 18. There's a README file about all that if you want to look for that in the doc directory of the GitHub. Joe also provided some updates because MINN is still being actively developed for the NOAA applications, RRFS, for example. And so several changes have been made in that scheme as it goes forward, and we're getting those into WRF as well. So basically a cloud fraction bug fix for radiation interaction, fixed number of subgrid plumes for optimization, other changes related to cloud PDF, and continued compatibility with CCPP and MPAS versions. RUC, Tanya Smanova has provided an updated RUC scheme because that is also being tested in or continue to be used in operational applications at NOAA. And we're getting the updates also in WRF. So it's been changed to maintain similar changes that were made for the RRFS, which is the successor to the PER model at NOAA, the 3 kilometer US domain. Soil model, the best soil evaporation has been updated, snow cover fraction, and an irrigation improvement. This shows an example of the changes with the snow cover fraction, where the old snow cover fraction was quite high over Canada, especially, and has been reduced in the new version to be more realistic compared to MODIS. Another thing we're working on, and Anthony Islas has developed, is CMAQ. CMAQ is becoming more of a modern standard for compiling codes. It avoids issues of reliance on provided dependencies. All that's automated. To use CMAQ, you can use configure new instead of configure and compile new, and the user is led through similar steps to before. Compilation occurs in the build directory, so things don't occur like with .o files that you're used to seeing, but everything is kind of hidden in a build directory. But you'll end up with executables that can be used just the same way. After version 4.6, which is considered a test phase for CMAQ to work out issues, we'll likely make CMAQ the default in version 4.7. And so CMAQ is ready to try out using these configure options if you want them, if you want to try it. Minor changes for the TKE diffusion. We've reduced the Prandtl factor. KM-opt equals 2 and 5. These you might use in the LES mode or sometimes with other cloud resolving applications where you're not running a PBL scheme. And Prandtl factor for momentum is 1 and for heat is 3. And for TKE, it turns out theoretically, a lot of people prefer 2, so we've gone in that direction. We used to have a higher value there, and so we've actually reduced the diffusion of TKE itself by a factor. In our test of the LS, it didn't have a big effect because it's only affecting the amount of diffusion of the TKE itself. Also, MP0 out, I don't think many people use that because our positive definite schemes keep things positive. But if you are using this, it used to affect all the 40 arrays, but now we've limited it to the moist arrays only. And if you want to apply MP0 out to all the arrays, you still have that functionality through a nameless option. But as I say, not many people use this because of positive definite keeps things positive well enough in most cases. Derecho migration. NCAR has main supercomputer is now Derecho, and Cheyenne is retired. So new code after version 4.5.2 compiles on the new Intel compilers. You can still use G4tran if you load GCC. And WPS is also now working on Derecho. So WPS and WRF latest versions are precompiled on Derecho. So if you use that supercomputer, you can find precompiled latest versions of the model. You can also use the current WPS and the older WRF versions if you're still using those on Derecho. Older WRF versions can use Intel Classic, which is still available as an option on Derecho. They can't use the new Intel compilers like the new versions of WRF can. And the G4tran is still available too. WPS has had a couple of updates, one for the single layer urban model, which I think Sinlin will talk about later. And there's a way to handle group 2 ECMWF data in ungrid. I'll show some results of for testing and verification. There isn't a clock here. Where's the clock? No, the time. Okay, I didn't see a timer. So the we conducted some tests of the early summer period in 31 days of May 2017 and 28 days of January 2017. Single domain resolution of 15 kilometers, so it's low resolution testing. We're mainly testing the things that have been upgraded significantly. Initial and boundary conditions is a whole US domain. I extracted from NCEP GFS analysis product. And each single case is initialized daily at 0Z, 48-hour forecasts. Actually, 26 cases are conducted for early summer and winter. And we did verification, basic verification compared to GFS. Nothing fancy in terms of verification. This is our domain. So these are tests we ran. We always test our standard physics, which is this set here, the version 4.5 and 4.6, to make sure nothing's really changed that surprises us. So that turns out nothing really has changed. Then we also added the MYNN because that had significant updates, the RRUC. So there's a separate test for these two. In SSL3 moment, even though it's only a 15-kilometer domain, we still ran it to make sure things look reasonable. And NOAA MP, which has had some changes as well. I'll only briefly show some of these tests. Mainly, we're just looking at these schemes, the way they behave with the surface verification here. So you have wind, 2-meter temperature, 2-meter water vapor. Basically, this is the spring case, the May case, and the February case. And this is averaged over all the cases. So the only things we notice here are that the RUC land surface model is moisture and cooler in the spring. That's these two here. This is the dark red line. NOAA MP and RUC both have lower wind biases than NOAA. So the NOAA schemes are here. The RUC and NOAA MP are here. We saw this last year too, that there are wind biases, more wind biases with the NOAA LSM. It's partly related to the roughness lengths being different, but we also find there's a lot of cancelling error in these schemes. So they're not really perfect everywhere. They just have cancelling errors in terms of wind bias. And then also in the winter, we see RUC is moisture as it was in the spring, but it doesn't have so much. It has less cold bias in the winter. Dark red line. We also looked at profiles, the wind profile, for example. This is the winter case. No notable wind deviations here. And so I won't say much about that, but there's generally not too much bias. As you can see, the zeros here in the middle. And all the tests are giving pretty much the same results. So none of these particular tests affected the wind profile. Temperature, there's some boundary layer differences here that we see. RUC has a cooler PBL bias in the spring, and NOAA and NOAA MP are warmer. So that's these opposite deviations in this, especially at 48 hours. And in the winter, the the winter temperature biases are more similar to each other. We also looked at rainfall totals. This is an example of one of the tests, the NOAA MP, just the rainfall field. So it's not really comparing it with anything. 0 to 24 hours and 24 to 48 hours for the May and the February cases. Some comparisons here. MYNN, NSSL, RUC, and NOAA MP. These are the differences from the standard case for the spring. The one that stands out here is that RUC tends to, as we saw, it had more moisture in the boundary layer. It also tends to have more convection over the US. So this is the one that stands out with more red. The rest are more random in terms of the precip differences. This is really your NOAA MP versus NOAA test in the right-hand column. In the winter cases, also not much stands out here. See some NSSL differences in the West Coast. And the total precipitation, RUC tends to have a higher spring precipitation and may be related to the moist bias. This one that stands out here. And in the winter, we see NSSL has lower, the 3 moment NSSL, remember this is 3 kilometers, so we're not really testing the 3 moment at high resolution. This just has about a 10% less precipitation in the winter. That's all I had. So any questions?
Anyone has any questions, please use the microphones. Check around the room and we'll go online. Wei, are there any questions from the remote audience? Like it. Okay, thanks, Jimmy. Our next speaker will be Bill Skamrock of NCAR, presenting the model for prediction across scales and atmosphere update for this year. Bill?
Thank you, Jordan. Well, what I want to cover in this 15, 20 minutes is what we've been doing in MPAS, but not in a lot of detail. You're going to hear talks later from, next up is Jake Liu, who's going to talk about MPAS and JEDI. And then later this morning after the break, Laura is going to talk about physics in MPAS and some of the updates we've made and where things are going there. So we just had a release recently, April 18th, MPAS version 8.1.0. Just to refresh your memory, that middle number is a feature release and the final number to the far right is a bug fix. So we had a couple bug fixes to 8.0, which was released just before last year's WRF MPAS workshop. And you can see now we've, about a year later, released another one. We're not on a yearly schedule here. Our idea is we release updates to features and bug fixes when we get them. There's something about having this workshop come up that motivates us to get new stuff out. So it only appears that way. But what I can tell you is that we have version 8.2 almost ready to go. And I don't know if Michael's floating around here, but you might see it this week. So you can see we're trying to get things out to you as quickly as we can. All these releases, of course, are available on GitHub through methods that you probably all know. The release version notes are also now on GitHub, beginning with that first bug fix release of 8.0.1. So you can go there and you'll find all the release notes there. When you go to the MPAS webpage, you'll also find links to release notes from versions previous to that. So if you want to see how things have progressed, you can go through those release notes. And as I mentioned, you'll hear updates for other aspects of MPAS later on this morning. I do want to mention a few things about some of our updates. We've been working on bringing together MPAS and JEDI. It does run together. There's releases of JEDI that work with MPAS. The way that works is that there's a particular version of MPAS in that JEDI release. That's not the latest release version that we have in the MPAS repository, the community repository. And the reason for that is that they had to make a number of modifications to MPAS to have it play well with JEDI. So recently we've been bringing in the modifications that they've had to make so that it can be run directly, pulling the MPAS model from the MPAS repository and building it with JEDI to then run. So, and part of that is essentially having the option of a CMAQ build available, and you'll see that later today or later this week in the release. That'll be an option. You'll have that available, but also something that came out in version 8.1, which wasn't required, but actually is very nice in data assimilation, is we have a capability to split the input and output files into time variant fields and time invariant fields, and essentially not write out the time invariant fields every time step, like the mesh description and things. There's a fair amount of data in there, it turns out. And this really reduces the file sizes particularly for cycling DA, but also for just in general for applications. Right now, the default for MPAS, for example, when it writes a history file, is it writes all the grid description information out with it. But you have an option here to skip that and in the restart files in particular, and this will really reduce your footprint on in your applications. And as I think all of you appreciate, if anything these days, it's our ability to write out data and hang on to it and analyze it. That's now the limiting factor in a lot of the things that we do. So that was available in the last release. So I want to point that one out. And it also helps with JEDI and the other data assimilation options that we have, for example, also for Dart. So our GPU implementation, we have a GPU implementation out there, and that's the one that we developed along with a number of folks, IBM, Weather Company, University of Wyoming, NVIDIA. Our latest computer to ratio here at NCAR has GPU capability. About a quarter of the nodes have that capability. We have not been able to get the full MPAS GPU enabled code to run on Duratio. And we've learned a lot about things in our GPU implementation or issues in our GPU implementation that are making that difficult. Based on that, we've decided to re-implement the capability in small steps to try to improve it so that it makes it more portable, more sustainable going forward. In the 8.2 release, which hopefully you'll see later this week, you're going to see some GPU capability in there. What we're releasing in that is being able to run the scalar transport on GPUs as a first step. And then we're going to continue to bring along the other aspects of the dynamical core, hopefully within this next year. And then we'll start on the physics. As you all appreciate, the physics are probably the hardest part of this problem, in particular because the physics has developed a number of you in the community. And so it's not completely under our control or purview here in M-Cubed. But I think in general, the community faces this problem of how to bring various aspects of the development that's all over the community into this GPU world. And this is the GPU codes are evolving rapidly. Other centers are trying a lot of different things. We're using particularly OpenACC. And how the best way to do this is not altogether obvious. So I think you should view any of the GPU implementations, particularly the ones we're putting out, as experiments, and we're trying to learn as we go forward how to do it best. But I would say there's no one clear answer out there. So here's kind of a second phase in our development, try to address issues that we've uncovered in our first phase here. So physics, as you've heard from Jimmy, and you will hear in more detail from Laura, we are moving forward with a shared physics repository for MMM models. That includes MPAS, WRF, and CM1, George Bryan's cloud model. For that, Essentially, there's going to be more physics updates released in version 8.2. Hopefully Laura will cover at least some of that of what you'll see soon. So she'll talk about that and give you more details there. So I'm not going to go any further there, but we are moving forward there. And in the discussion session later this afternoon, one of the topics I hope we'll be able to discuss is how we live in this physics world for the atmosphere models as it evolves, and particularly with shared physics, the CCPP, et cetera. So that's something that we'll have an opportunity to discuss in much more detail later today. So one thing I've been talking about starting, way back in 2018, was bringing MPAS into an Earth system model to enable coupling to an ocean, land ice, sea ice, more sophisticated systems that run in our Earth system models. And one of the projects, or some of the projects we have that are moving forward with that, is essentially bringing MPAS into NCAR's Community Earth System Model, CESM. And there are two projects that are working on that. One is called System for Integrated Modeling of the Atmosphere. That's pretty much an NCAR-based approach, and that is just focused on the atmosphere component, essentially for that. But there's also this project called Earthworks, and that comes out of CSU, that's looking at a GPU implementation of that with some tweaks to CESM, actually bringing in other components, for example, for the ocean. So I want to talk just briefly about those, and you'll hear more about bringing it into the NOAA UFS system later today too, or what that's potentially going to look like. And it's aspects of this and what that means for our support and development that I would like to see us discuss later this afternoon at that discussion session. So that will be coming up, and we'll get an opportunity to discuss that further. So first, CMA. This is bringing in the MPAS dynamical core into CESM, and effectively that is done. You can build CESM or versions of it, not the latest release version, although soon to be, it will be released soon. Then it pulls the MPAS dynamical core directly from the MPAS repository and does the build. We started this way back in late 2017. And well, here we are in 2024. And what I can tell you is that we haven't released it yet because we really wanted to be able to get to convective scale simulations over the globe coupled to an ocean. And what we found out over the years is that the infrastructure for CESM was designed for coarse resolution climate. It was not designed for high resolution global applications. We are now at a point where we're actually starting to run effectively 3+ kilometer global by shutting off various aspects, it turns out, of the coupler. And trying to work through problems we're encountering with that. It's taken a long time. Also, when we run with the physics and the atmospheric physics and CESM, their atmospheric component they call CAM, Community Atmosphere Model. It's not Convective-allowing model, so you have to translate there. Their atmospheric physics has needed some tweaking to produce respectable results at convective scale. We're there. And now I think we're getting to a point where the global implementation run at high resolution may be possible. A second caveat, though, I want to attach to this is that when we compare it to standalone MPAS, where we run high resolution global regularly now, it's 5 to 10 times more expensive, both in terms of the amount of machine you have to be on and the cost of the simulation. So I don't know when we're going to get to a point where this is going to be a practically usable tool by the community. So that's what I want to say about that. And I wish I could give you better news, but that's where we are. But at least now I think we have an understanding of the problems and maybe how to start testing this. So the other project is Earthworks, which has a lot of overlap with CMA. It's using the MPAS atmosphere dynamical core, the non-hydrostatic dynamical core, but it's also using MPAS ocean, the MPAS sea ice model, everything else. And the idea is it's going to run on the exact same horizontal mesh for all the components. So the ocean and the atmosphere, the horizontal grid cells would be coincident. And the idea is that we could then bypass the mediator if we had problems with that. Well, it turns out that mediator is more ingrained with how you run CESM than we appreciated. It turns out we can't bypass it. So as a result, we're facing the same problems that SEMA has run into. But also, given that this is an outside project funded by NSF, this is Dave Randall up at CSU that's leading this, it's given more push to the CSM crew to fix these issues in the model. So I think because of the appearance of earthworks 4 years ago, we're further along than we would be without it, without a doubt. There is actually a release of this functional release, which is listed below. And that right now will allow you to run a 30-kilometer global coupled ocean atmosphere in a particular configuration that's been tested. I think they've run at least a decade or more, a couple decades with it. And it produces not crazy climate, but it's not tuned. And I would say no one's actually looked at the results in terms of the weather it produces, except integrated over climate timescales. But these are climate folks that are leading this, so that's how that works. So we've got other things going on. We are working on new web pages for MPAS, and I believe for WRF also. We realize the MPAS web pages that are hosted on GitHub are kind of, well, they've been around there since our first release in 2012. We also realize that it's not necessarily easy unless you know exactly where to go to find things. So we're working on redoing those and actually bringing those more in-house to give you a similar look and feel to what WRF has, so that perhaps transitioning and finding things is easier to do. We are putting together a developer's guide. Michael's leading that. We have drafts of pieces of it, so that's coming along. We're also writing a technical note that many of you probably familiar with the WRF technical note. If you actually want to see all the equations or find references for physics and everything, that's where that is. We are writing a similar technical note for MPAS, but I want to point out that we're doing a little bit more than that, in that here's an example of a piece of it that, well, it doesn't display very well, but you can see, for example, here's the part of the technical note, the draft that talks about computing the vertical vorticity. Essentially, it's done on the triangles, the dual of the Moroni mesh, and it just uses the circulation theorem divided by the area. You get the vorticity. But also note that there's a call-out box there for where this is done in the MPAS code. This is where this equation is evaluated, and that is going to carry through to all the pieces of the numerics. And the idea is we're going to go into the MPAS code and reference back to the technical note. We're working on this. I'm hoping we'll have a solid draft by the end of the year that hopefully we'll be able to release to you. And I think this is going to be a really nice tool for people who want to go in and modify code, the people that have to support it, and perhaps even in universities for teaching students, they can go in there and they'll see it. So I think this is going to be a really nice addition to MPAS, and going past what's in the WRF tech note where you see all the equations, but you don't know where in the code those equations will show up, that this is going to be a big step forward in terms of the usability of this. Okay, one thing we hear a lot about is mesh generation. It's a real pain. We feel that pain. We feel your pain in there. We're working on a few things, of course, more efficient algorithms for just the standard mesh generation that uses Lloyd's iteration. We're also starting to work on, and we're going to get this done, I think, soon, essentially taking perfect hexagonal meshes and mapping them to the sphere with the standard projections. The nice thing about that is the perfect hexagons, of course, obey, they're trivially put together. You don't have to do any iteration. And given that the projections also maintain orthogonality, that the orthogonality, the perfect hexagons will be maintained in that projection. So that'll allow us to produce standard projection meshes with the perfect hexagons essentially trivially. So we're going to move forward on that. We've had our first meeting of a science advisory committee. We have one together. And we have a draft of the MPAS plans and priorities document that lists kind of what we're doing, where we're going. I'm hoping to use this as one of the things for the Thursday afternoon discussion. But we have a number of things we're trying to move forward in some way, shape, or form, both with in-house resources, but also partnering with the community wherever we can. And so I'll be showing this again on Thursday for further discussion. This list here, because you'll see the slides, will be available later. This is not a priority order here. There's no order in this list right now, and we'd like to discuss what people would like to see, what they feel is important for their applications, so we can help prioritize and do our own triage in M-Cubed in our development. And this is the last slide, or I think the last slide. We've got upcoming tutorials. For those of you who want to take advantage of them, we've got one in October. This is our fall tutorial at Howard University. It's in person. We can accommodate about 40 people, and I think we're going to have about 10 students from Howard, so there are about 30 slots left. The announcement for that is going to go out anytime. It may actually already be out, but I don't think so. I think it's maybe today it'll go out. So you can find that if you go to the M-Cube website and look for events, you'll see that. We've got another tutorial in Edinburgh. People want to travel over there. That's going to be a good time. Come on over if you want to learn about MPAS. And that's going to be sponsored by NCAS over there in the UK. Spring 25, we're having our virtual tutorial, but the dates haven't been set. We're following a virtual tutorial in the spring because those are very popular. We had 70 people sign up for it. We had a whole bunch of other people that just listened to the lectures. And we're going to a spring fall, but the fall will be in person. WRF is kind of switching things around. They're going to do winter in person because the hotel rates in Boulder are cheaper and maybe makes some sense. And the summer is going to be virtual. And again, you can just find announcements on the M-Cube web pages. So with that, I'll conclude, and we have time for at least a few questions here.
Yeah, just a comment.
Good morning, Cliff.
Good morning. There's nothing more important for predictability than to get a coupled, convective allowing atmospheric model with the ocean. I mean, that is such a high priority. What can we do as community to help you get the resources and personnel to make this happen? Because this is it. If we don't do this, we're screwed. So how can we make this happen?
I agree. I agree that this is a good one to discuss at the discussion this afternoon. And I don't have a good answer. 6-7 years ago, it looked like, okay, we're going to go into CESM, all our problems will be solved. And well, it's not happening, or not happening quickly. So I don't, there are some other possibilities. For example, if we go into the UFS, potentially we can do that. But understand the UFS uses very similar infrastructure to CESM, and we know they've run into some problems trying to run high resolution there. The same problems that we're running into. So there's no easy answer. There are some lightweight couplers out there that we're kind of looking at to see if we could do something quickly there. It's very hard to say. I think what we're learning from that, our CSM experience, is that to be on that leading edge, to try to take technology that was developed for coarse resolution climate to that is proving problematic. And it's no surprise that the centers that are successful have essentially built from clean sheet of paper kind of thing, their infrastructure in particular. Do we have any questions from out in virtual land? Or please go ahead.
Thank you, Bill, for the very nice talk. I'm really interested in the LES capability. Can you elaborate more on like the grid settings or boundary conditions or subgrid scale model available in MPAS now?
Yeah, so we haven't released the LES capability, but we have it on a branch. It's something that we definitely we have a number of reasons to move forward because a lot of groups want to use it. So I think you're going to see that, you're going to see a release with the LES capability and not too far along, because we want to get that in there because it actually has some impacts on the dynamics, and we want to make sure the GPU version can as we develop it, could take long. So we'll see it soon. Right now, the testing we've done is doubly periodic, idealized LES cases that run okay. We're working with a few folks to try to bring in terrain effects into the LES model, because right now it's a flat Cartesian plane implementation.
Thank you very much.
Oh, this is going to be equivalent to the old man yelling, "Get off my lawn." CMAQ. CMAQ is not my favorite tool.
It's not ours either. So right now it's an option, or it will be an option.
Who are you pointing at so I can,
Oh, Michael, of course.
Yeah, okay. I mean, the problem with CMAQ is it's sometimes mysterious. I understand maintaining make files is a giant pain in you know what. I guess what I'd say is I think one of the tricks is that the versions are tricky to use, because I know in the UFS they've had to have some problems when they switch versions. And then when you don't have control over your own systems like we don't in NOAA, getting the right CMAQ in there is often a little bit trickier. So I guess what I'm saying is be careful just getting rid of make files. I mean, at least we know how to hack them. And so I don't know what that means. I don't know if you want to comment, Michael, on here. So.
No, so the CMAQ capability is purely to support MPAS-JEDI, which uses EC build, which is based on CMAQ. So it quite honestly isn't my first choice for a build system. So I can say that the GNU make files are not going anywhere anytime soon. So yeah, CMAQ is purely right now just for MPAS-JEDI.
And our current make system is the default. So you have to work to get CMAQ or do something special.
The question for people remote is WRF going to CMAQ, and if so, why? Is there anyone in this room that can answer that? I don't know, Michael, do you control that, or Anthony? Well, it's not, it can neither confirm nor deny that it's going to stop.
I just want to make a general comment that you're going to see like different changes coming in. That is really, I actually want to thank, not point fingers at, our awesome software engineering team that are doing a lot of stuff to really try to streamline a lot of the processes that we have to do internally. So, but I mean, the other great thing about the software engineers here in MCubed, you guys are an amazing team. They are so cognizant of the user needs and not pushing technologies onto the users until they're ready, and there's documentation. And I so appreciate that. So shout out to the software engineers. Thank you very much.
Before we go, I just want to check, Wei, is there anyone remotely who has a question? Is that a yes, Wei?
Yes.
Yes, okay, so we're waiting for a remote question.
Is there any current research on the grid generation?
Current research, there's movement. So we are going to put together this, taking perfect hexagons, a perfect hexagon grid to map it to the projections. So for all you WRF users who have your favorite projections, you should be able to, with this, when it's available, trivially produce an MPAS equivalent. In terms of the other mesh generation, there are some folks out here, when maybe we'll hear about it when we're here. Yes, I knew we would. Yeah, and whom are probably pushing harder than we are on this, and have some, I think, some innovative techniques to reduce the cost of mesh generation. Because one of the things we want to be able to make available is the fact that you can stretch that mesh in order to push your lateral boundaries out, match the resolution of your driving analysis, all those kinds of things. So mesh generation is crucial in that world, and we want to make that easier. So things are happening in a distributed way, but we're going to focus on the allowing for those projections to get uniform resolution meshes onto them to help with people transitioning from WRF.
Okay, we'll move on to our next and final speaker of the session. We'll hear from Jake Liu of NCAR with WRF MPAS-JEDI at the 2024 annual update.
Okay, data simulation time. So we are a bit 5 times late, but I will say if we can keep our coffee break time on time. So this is annual update on the okay, I have a pointer here, I guess. Okay, okay. So I will spend maybe 5 minutes or so for the 3 items for WRF DEA update. So one new feature in version 4.6 is add the capability for simulating ghost ABI reading state. This contributed by my former colleague JJ Wright, a former visitor De Li, and myself. And for this capability, you can simulate ghost ABI data with different scans, full disk scan, or corners, or major scale scan. You can do a cloud detection for clear sky ABI reading state simulation. You can also possibly doing all sky DA with say all sky observation model. You can do superurban scaling and variation bias correction. We will probably not update user's guide for this, but you can check the corresponding pull request on the GitHub. Get more information. Another new feature is contributed by Zhixiong Chen from Fujian Normal University, China. That's for simulation of lightning date. So you have 3 options for simulating lightning flash rate. So you can convert this flash rate into vertical velocity profiles. Then you can simulate vertical profiles. Then also you could further convert vertical velocity into pseudo divergence or pseudo water vapor. So that's there is a publication there. You can check for more details. Another enhanced capability for is for indirect radar reflectivity data simulation. So this basically read in reflectivity, then retrieved into hydrometer profiles. Then you can simulate hydrometer profiles. But basically previous code is when for mixed phase of cloud, retrieving not take into account some subtlety, how you split between rainwater and snow and dropper. For the new enhanced feature, you can retrieve those profiles based on the relative ritual in the background field. There is a couple of papers describing this. So this same slide like last year, I just put here for your information. There are some newcomers for this workshop. As our director mentioned, our internal development resource is more to the MPAS and the MPAS data simulation. We're not stopping updating WRF and WRF data simulation, but basically, we're still maintaining, but maybe make some bug fixes, some new features contributed for external developers, we could put it in. But very limited resource to do the really supporting, this like answer your question may not very easy or have a lot of resource. So we're moving more to MPAS data simulation that's based on JEDI. Bill already mentioned. So basically, MPAS-JEDI is the MPAS data simulation based on joint efforts for data simulation integration framework. So basically, the JEDI, there is a bunch of people developing model analysis components. Basically, on the right-hand side, there are a few components, different models. There are a lot of models currently hooking up to this JEDI framework. But our team in MCubed, we focus on MPAS. So we already make a couple releases over past 3 years or so. First release back in 2021. Last June we released a second version. So we didn't cut off a third version yet. Partly because we want to make use the latest official MPAS model. So previously we make use of another MPAS model version that's 7.x based. Bill already mentioned we already make a good progress switching to official MPAS model repository. In this way, in the future, we can make better, better benefit from future MPAS model enhancement like GPU capability, like Bill mentioned earlier. So last year, last September, we already okay, that's the next slide. But so that's the features you can do with MPAS-JEDI. You can do there are several options for doing deterministic analysis. Basically, that's the state-of-the-art technique, like a hybrid 4D EMR. That's the current operation in Ensemble. Ensemble analysis, you can do ensemble of data simulation. Pretty much that's like an ensemble of EMR. We have also a couple options for doing using ensemble common filter-based data simulation like LETKF, or another is called the gain form of LETKF, or you call it LGETKF. One nice thing with MPAS-JEDI is that analysis directly done on MPAS unstructured grid. So you can easily do with uniform or variable resolution mesh or global or regional mesh. MPAS-JEDI is just like MPAS model. You can use same source code to do the regional or global setting. So it's very convenient. There are advanced capability to satellite readings data simulation. With cloud and precipitating affected microwave IR satellite readings data in all weather conditions. There are two radiative transfer model you can use, the CRTM or RT12. You can even, combine them together for very flexible setting. You can analyze the hydrometers as a part of analysis variable in addition to temperature, moisture, and the wind field. There are variational bias correction, also so-called situation-dependent all-sky observation error model. So yeah, so that's the thing I like to tell you. The last workshop I mentioned we will do this, but we did this last September. The first time we conducted this MPAS-JEDI tutorial together with MPAS model at NCAR. So all the material is online. You can check, even test the case. You can download, you can play, probably, you can set play with on your own machine. So this year we will do together again, but mention that model folks are doing twice. Model tutorial, JEDI, MPAS-JEDI, we will just do once in person per year. So next few slides, just tell you a little bit, new features with latest MPAS-JEDI code. It's not released, but development code you can use. So one thing is that we have more flexibility for doing ensemble localization settings and also background error covariance matrix. For example, you can do variable dependent localization line scales, for example, for different groups. For hydrometers or other dynamic, thermodynamic variable, you can set differently localization scales. My colleague BJ Jung has a talk on Thursday afternoon. As I mentioned, the hybrid 4D EMR may be the most advanced technique we have in MPAS-JEDI. That's the state-of-the-art technique in operational centers like Ensemble. So with our new computer Duratio, we can run more regularly with this technique. This is just a demonstration from my colleague Robert. So we compare the hybrid 4D INVAR versus hybrid 3D INVAR. For the over the 1 month cycling, you can see the figure shown on the right-hand side is the relative root mean square error reduction. If the negative side is means the error reduction for the 6-hour forecast, over the 1 month cycling period. So you can see even for the short-term forecast, you have, even maybe up to 5% or even, some higher level, maybe you have a 10% improvement. So that is quite nice. It's mentioned that the 2.0 release we made last year can run pure 4D INVAR, but not the hybrid mode. So the latest code and the future 3.0 code, we can do the hybrid for the INVAR. So another thing is that we spent significant effort over the last year for the LGEDKF. So LGEDKF is the main advantage that this technique allows to the vertical localization in model space, but the horizontal localization in observation space is very convenient for reading state simulation. My colleague Tao Sun is leading that effort. So here he will give a talk on also Thursday afternoon, but here what I showed is that we're also trying to improve the ensemble data simulation performance by adding also assimilating all sky satellite reading state. Here what I showed is that by adding a all sky MSO-A reading state also improved forecast performance up to day 7. So here you can see that's the verifier against the independent ATMS, another microwave sensor. The negative also the means that that's for against the different channels. Negative means the root mean square error reduction. Recently, myself also run a regional hybrid 4D INVAR at the convection permitting scale, which are simulation of hourly all-sky ABI reading state over this cornerstone. So basically, there's a 6-hourly cycling using 30-member ensemble input from MPAS downscaled forecast from GEFS initial condition over 2 weeks period. So, for simulating all-sky reading state, you need a so-called all-sky observation error model that's situation dependent. That's shown on the right-hand side. So basically, observation error is a function of so-called cloud impact parameter. Okay, I will not go into the detail, but just tell you that, so that's the common technique in current some operational centers. So here I showed for 4 channels, 3 water vapor channels and 1 window channel sensitive to cloud and the surface. The left-hand side is the O-B statistic for 4 channels. So basically, this tells you the different the standard deviation, the bias value. So you can see the 3 water vapor channels. There's some bias, channel 9, you can see there are larger bias, but channel 9, there are quite a small bias, like 0.13 Kelvin. So for first trial, I was just simulate channel 10 without bias correction. So here just to tell you, okay, this still working in progress. So so that's the 1 hour precipitation forecast for 1 single time. Okay, I just chose 1 time. There's some better result. You can see the stage 4 observation, the NOAA ABI data assimilation, and including all sky ABI reading state simulation and also clear sky ABI data simulation. You can see precipitation forecast. For some, this location, you can see some improvement from all sky data simulation. So that's kind of this still working in progress. But this is very encouraging for the convection permitting scale application using MPAS-JEDI. So MPAS-JEDI can also do radar data simulation. So you can do radio velocity, also reflectivity. We didn't test very extensively yet. But my colleague Zhu Mingying tried this radio velocity DA for a PyCon case study in 2015 period. So here just show you some preliminary result. Looks like we do have some improvement for the location of this precipitation for the 3 to 6 hour accumulated rainfall forecast. So this is my last slide. Just give you an idea. We are continuing working on this development testing, a lot of testing, especially assimilate, investigate more satellite readings data in all-scale approach. We prefer all satellite readings data, including infrared, microwave, visible band, active sensor. Would be nice. We can do all of these sensor with all-scale approach. There are a lot of work need to be done, VRBC, quality control observation model. We probably also try RT-top at some point as another radioactive transfer widely used by non-US countries. So we have a project also working with radar data, especially through parameterization data. Bill didn't mention, but I believe MPAS have some workable version working with some aerosol, like a go-kart aerosol model. So perhaps in soon, near future, we could also begin some work for aerosol chemical DA with MPAS-JEDI. So I just stop here. Any questions?
Wei or Kelly, are there any questions from online? No. Is this mic on? It is. I have a question, Jake. This is on the computing aspect with 4D VAR being in MPAS-JEDI. Have GPUs been applied for 4D VAR codes? Do you know if they offer the potential to speed up 4D VAR?
This is 4D in VAR, not 4D VAR. So no GPU, right? No GPU yet. Okay.
Okay, that's it. Thanks a lot, Jake. All right, folks, that concludes this session. We'll have a coffee break now and resume at 10:30. Thanks a lot.
So our first talk will be from Celine He of NSF, NCAR, RAL, and Land Surface. And I'm going to run the box here, but so if you don't notice the green light or the yellow light when it comes up, I'll probably stand up to let you know there's only 3 minutes left.
Hi everyone, thank you for coming. So today I'm going to talk about the major updates since the last major release, WRF version 4.5 to version 4.6 regarding the land service models, including the urban components. So the outline of my talk is so included the land service model physics update, the bug fixes, and also just to as a reminder for some of you who are not familiar with the land component of WRF, we have currently 8 different options for the land service model physics, including some of the widely used options like Unified NOAA land service model, ROC, NOAA MP, CRM, PLASU, and CTSM, and SIB. And we also have 3 different options for the urban physics, including the single layer, option 1, the multi-layer option 2, which is BAP, and the third option is the BAP-BAM with the building energy model. So the first update for the single layer urban canopy model, there are two new options and capabilities added to this single layer urban canopy model, which if you choose the urban physics equals 1. So essentially this was added by a researcher from Tokyo Institute of Technology. So these new options allow to read in global spatially varying urban morphological parameters, including building height, plan area index, frontal area index, roughness length for momentum, and displacement height. So the purpose of this is to more accurately calculate the service drag calculations over urban areas. The second new option allows to read in global spatial varying hourly anthropogenic heat fluxes from the monthly climatology dataset. So all these datasets, the 2D varying spatial varying datasets, have already been included in the WPS database. So people can use this if you activate these two new options. And here I'm also providing the references for the updates in this for this option. So just to give you a rough sense how this data set looks like. So here on the left, I'm showing you the major dominant land use land cover map from MODIS. And as you can see, the three major areas as an example for the Eastern US. And on the right, I'm showing you the building area fraction from the data set implemented in the WPS. And also the same map, but for the service roughness length over the urban area. And lastly, the AHE, which is anthropogenic heat energy. So you can see here, it actually represents the major urban cities due to the anthropogenic heat fluxes. So this is the anthropogenic heat fluxes from all the sources, not specifically for like say vehicle heat release or human residential heat use. It includes all of the things. So the second update for the WRF Urban is the updates for the urban local climate zone parameter table. So the issue is that before this bug fix, it's not a bug fix, but before this update, the urban local climate zone parameter table includes some unreasonable values for urban morphology. For example, the too large road width and some of the thermal properties are not reasonable. So researcher Alberto Martilli from Spain updated this table based on a more reasonable value, which comes from the mid-range values, global mid-range values of this traditional urban climate, local climate zone paper. And then, so currently our table have the most updated parameters. But again, just as a reminder, if users wants to apply this or run a specific case over specific urban areas, people can start with this default global mid-range values, but you probably also need to tune the parameters based on the specific urban morphology and thermal conditions. So next is about the land service models. So as some of you may already know from last year's update, so we have a brand new refactored version of NOAA land service model, which we call version 5.0. And we also have this latest tech note for the NOAA detailed physics and mathematical equations. So currently the coupling of the NOAA version 5 with WRF is still planned for release hopefully early next year for the next release version, WRF version 4.7. And in addition to that, we also have a NOAA standalone model container, so users can download the model to run the simulations in their local machines using this container. Some of the planned upcoming updates for NOAA version 5.1. So we have a lot of recent updates in the model physics from individual groups in the community. For example, we have this wetland representation and dynamics. the roughness sublayer turbulence schemes, and the coupling with a new snowpack radiative transfer model, scale-aware snow cover parameterization. So this snow cover parameterization will be used to substantially reduce the long-standing code bias issues in WRF NoMP. So we have been testing this recently, and it should be coming out soon. And also the new snow compaction parameterization, the spring wheat crop dynamics to enhance the WRF NoMP crop model. And we also have 3 other major physics update, which however requires more efforts and time and human resources to do that. So currently it's still on our to-do list, but we cannot guarantee there will be in our next release. Okay, so for the Plateau land service model updates, which has been improved to work with the urban local climate zone classifications. So in addition to that, there is also, I think Jimmy also mentioned a little bit about this. There is also updates to improve the effects of evaporation from transpiration soil in both vegetated and non-vegetated parts, and also the wet leaves. And this improves the impact from the ET on the ground temperature. So the previous Plateau land surface model only accounts for the effect from transpiration and evaporation from non-vegetated soil parts. So this improvement is to really add the latent heat effects on the groundwater, ground temperature from soil in vegetated parts and wet leaves. So about the rock LSM updates, Jimmy also mentioned this already. So just very quick, there are 3 major updates for this. First, there are 2 new options added to the snow model in rock LSM to compute the thermal snow conductivity and the snow cover fraction. So you can use these 2 updated new options to do the rock model run. There is also a new update to use the real-time vegetation fraction as an indicator for irrigation scheme to improve the irrigation. And lastly, they also changed these soil diffusion and hydrological conductivities in the rock LSM. So just a very brief walkthrough for the bug fixes. So in terms of the urban bug fixes, there is a net long wave radiation flux updates or bug fix, and also I want to know that we also identify a few more single layer urban canopy model code bugs recently, and this will be fixed soon in the next minor release of WRF. And for NoMP bug fixes, we have this leaf mass initialization for the urban part, and also the snow layer index bug fix, so that there will be no model crash if the snow layer changed by more than 1 layer within one time step. Historically, there was a bug that prevents this type of substantial changes in snowpack. And the next bug fix is about the ground heat flux sign in NoMP column model, which is inconsistent with the urban flux sign from the WRF urban model. And lastly, we fixed a bug for the vegetation fraction scaling for stomata resistance calculation and canopy interception calculations. With that, I would like to stop here and take any question. Thank you.
Questions for Dr. Yi?
Hello, thank you for the excellent talk. I have one question with the input data needed for the urban models. Have they been updated as well, or are we more or less just talking about the CONUS area?
Oh, it's global.
So they have been updated recently as well.
Yes.
Okay.
And following up on that, that slide there, is there a specific resolution of the model that you think is going to benefit from these urban?
I think it's 1 kilometer global.
Okay.
The
And then,
native resolution.
okay, great. And then just as a follow-up, on those NOAA MP improvements for snow, that was coming out in 4.7 of WRF? Or is that already in 4.6?
It's not there for the 4.6 yet, but it will be in the hopefully the version 4.7, because we need to couple the NOAA version 5 with the WRF first. And once we couple that, because currently the WRF code is already automatically connected to the community NOAA GitHub repository. So once we update the NOAA community code, then it will automatically update on the WRF side. So yeah, but we need to do the coupling first. Yeah.
Big thank you on that, though. We're gonna.
Early next year.
We have a question from the virtual side.
Yeah, so do we have a plan to update input data to WPS, especially geographical data? NLCD, for example, as far as I know, NLCD 2011 data is now available, but it is outdated for current year simulations.
Great question. So currently we don't have any plans because we have limited resources from NCAR side. But if the users are interested in updating that, we can work with the users or developers to get that into the WPS. Yeah, we really want the community input and collaborations on this. As you know, WRF is a community model. So yeah.
Any other questions?
There's one more virtual question. Can you please mention again any change with ground heat flux sign in NOAA MP?
Oh yeah. So traditionally, or before the bug fix, the ground heat flux sign is positive for the downward ground heat flux in NOAA, but then it is positive for the upward ground heat flux from the urban side. So when the WRF is going to compute the grid level mean values for the ground heat flux, these two signs are actually inconsistent. So we fixed that in the diagnostic part. So it only affects the diagnostic output. It does not affect the model simulation, the prognostic results.
Okay, you left yourself too much time for questions, so I have one more. And this
Okay,
is, you can just tell me, this is going to be a gotcha question a little bit. We're trying to, I think in the long run in NOAA, right, to merge RUC and NOAA, put some of the stuff that's the goodness of the RUC into the NOAA. So like, for example, more soil layers and things like that. Do you have a timeline for that? Or would you be doing that? And is there a timeline for that?
Short answer is I don't know.
Okay.
Yeah, I will probably not doing that because so our group currently is more focused on the NOAA development, especially the implementation and coupling of NOAA with different host models like WRF, NOAA Unified Forecast Systems, NASA Land Information Systems, all those major systems. But we are happy to work with the people or users to do anything relevant to other land service models. Yeah.
Thank you. Okay, we'll have to move on.
I think we have one more. Oh no.
We're gonna have to move on. Sorry, I'm sorry. I didn't mean if I missed you. I'm sorry. We'll have to move on to our next speaker, which is Laura Fowler, who will be updating us on all this goodness in the physics compatibility.
Oh, got you.
Okay, so a year ago, we released version 8.0.0, in which besides updating a few of the parameterizations like the NOAA LSM or doing a few bug fixings, for instance, related to the snow albedo, surface albedo over sea ice, we did start to implement a CCPP version of the moist physics parameterizations for the mesoscale reference suite. And those physics parameterizations were put into a physics_MMM subdirectory below the physics. Fast forward to last April, as Bill mentioned, we released MPAS version 8.1.0, in which we added an updated version of the surface and PBL and YNN parameterizations to include the EDMF version of the PBL scheme to WRF version 4.6. And we also put those parameterizations in that physics_MMM subdirectory, since they were since it includes a CCPP compliant version of the parameterizations. We also added a separate driver for surface processes over sea ice point, which would allow us to be more flexible when we start to add more land surface parameterizations to the physics. So today I'm going to talk about what's happening or what will be implemented in version 8.2.0. Yes, 2.0, which in accordance to Michael, we are committed to a release by the end of the workshop. Michael also told me that if it's not released by Friday afternoon, then just go knock on his office. It's 3006 in FL3, and it shows a little James Bond little icon. So go talk to him. Do not go to 3006. Go to 3007, actually. Sorry. So I'm going to, so in 8.2.0, we're releasing the NOAA MP-LSM. We're releasing an aerosol-aware version of the Thomson Cloud Microphysics, and we're updating and moving the physics MMM subdirectory to its own GitHub repository. So first, implementations of the NOAA MP land surface scheme in 8.2.0, which you can activate using the options SF_NOAA MP, unlike the instead of the default SF_NOAA options to run the land to run the NOAA land surface scheme. Note that that work was funded by the Antarctic Mesoscale Prediction System, which is itself funded by the NSF Office of the Polar Program. So we implemented the refactored version of the NOAA MP LSM. The source code was downloaded directly from the NOAA, the NCAR NOAA MP GitHub repository. And at the time of when I started to implement NOAA MP, we used a version 5.0.1. which I understand now moved to version 5.1. The source code sits in its own subdirectory, which is right below the physics directory. And let's see if I can use this, the pointer. So we have the physics directory. The physics NOAA MP directory is located below the physics directory. And we kept the subdirectory of the NOAA MP source code organized as in the NOAA MP original repository, except that for the driver subdirectory, now we removed the default parameterizations of the initializations and interactions between NOAA MP and the host model with our own modified source code. At the physics level, now in terms of interactions between NOAA MP and the host model, so MPAS, we have all the NOAA MP variables now sits in their own registry called registry_NOAA MP. We do that one-time step initializations in that NOAA MP init module. Then we have one-time step one finite time step to deallocate all the arrays that are needed to run NOAA MP. And of course, we have a NOAA MP driver, which is located at the same level as all the other physics drivers. If you want to change some of the NOAA MP options, let's see if I can do this. Anyhow, then you just go into the namelist.atmosphere, and under the physics_NOAA MP, you can change and kind of modify the options that you want to use instead of the default options that are set in the registry. Okay, this is not advancing. Do we need to point at something? Can I advance my slide? Here we go. Back one slide. Okay, so as an example, I'm showing at the end of the 10-day forecast using the 62.3 kilometer mesh centered over conus. I'm showing a difference in the latent heat flux between NOAA MP and NOAA on the left side, and a difference in the sensible heat flux between NOAA MP and NOAA on the right side of the slide. You can see that at the end of the 10-day forecast, then we have decreased latent heat flux over the continents in NOAA MP relative to NOAA, for instance, over South America. This is really not working very well. South America, Africa, and some over North America. And we have an increase in sensible heat flux again over South America, South Africa. The next slide show now the difference in the 2-meter temperature. No, it shows the 2-meter temperature also at the end of the 10-day forecast. On the left-hand side, you have the simulations with NOAA MP. Now we're centered over the conus domain, which has a 3-kilometer resolutions. And on the right-hand side, I'm also showing the 2-meter temperature, but now from the NOAA LSM. As you can see, we have an increase in the 2-meter temperature of the conus on the west side of the United States, and a slight decrease in the 2-meter temperatures in the eastern side of the domain. The second item that I want to talk about is the implementations of the aerosol-aware version of the Thomson Cloud Microphysics. To trigger that options, you use MP_Thomson_aerosols instead of the strict MP_Thomson that we have for that we had in previous versions. So we implemented the version corresponding to the WRF version release 4.1.4, and there are at least three reasons for this. First, we tested that specific parameterizations with many uniform and variable resolution meshes, so we can test the impact of the implementations at a different global, horizontal, and time scale. Also, we did not want to include black carbon separately from the other aerosol types, since we're in the midst of implementing a separate aerosol model. And we also need to more fully test the hail options that is now available in 4.6. So the default options for those of you who are not familiar with the aerosol-aware version of the scheme includes two types of prognostic aerosols. One which is referred to as water-friendly, the other one is referred to as ice-friendly, and those aerosols are based on the GOCART monthly mean climatology that is available also for initialization. So the water-friendly aerosols act as a source of cloud condensations nuclei for cloud water droplet nucleations, and ice-friendly aerosols act as a source of ice nuclei for ice crystal-like nucleation. This aerosol-aware version of the Thomson scheme interacts with the RTMD shortwave radiation scheme through the impact of the aerosol optical properties. It also interacts with the MYN PBR scheme for vertical mixing of those water-friendly and ice-friendly aerosols. It works both with the mesoscale and the convection permitting suites, and it works as well for regional simulations by providing lateral boundary collisions for both types of aerosols. So as an example, if you use the default implementations and use that binary data to initialize the global distributions of the two types of aerosols, you are going to get the top two maps. On the left side, I'm showing the vertically integrated amount of the number of concentrations for the water-friendly aerosols on the left. This is for June 6, 2012 at 6 UTC. We'll see that the maximum amount of water-friendly aerosols is located over the regions of maximum anthropogenic emissions. On the right side, I'm showing a map of the vertically integrated ice-friendly aerosols number concentrations. And the maximum in that type of aerosol now is located over area of erosions and lifting of mineral dust. Now, if you kind of run a short 5-day forecast using that initialization, then you kind of get the two maps that are shown at the bottom. So on the left, if I can read that, on the left you have the vertically integrated water-friendly aerosol number concentrations after the 5-day forecast. On the right, you have the one corresponding to the ice-friendly aerosol number concentrations after the 5-day forecast. Note that for the default options, the parameterizations of the surface emissions of water-friendly aerosols is highly parameterized, kind of more or less kind of depends a little bit on the original resolutions of your mesh, but there is no emissions of the ice-friendly aerosols. So at the end of that 5-day forecast, you see the impact of the parameterized emissions. For instance, actually here you can see an increase in due to the, which I think is overestimated emissions of water-friendly aerosols. The impact of the aerosol-aware cloud microphysics, as well as the impact by the advections, the mixing by the PBL scheme, and the convective transport by deep convection. You can, of course, kind of provide your own initializations of aerosols, which is what we have done here to simulate the June 11th, 2012 mesoscale convective system, which was observed during the DC3 field campaign. Here, I'm simply showing on the right-hand side a map of the 10 centimeter maximum radar reflectivity of that MCS on June 11th, 2012 at 19 UTC. So in this forecast, we initialize the water-friendly and the ice-friendly aerosols using CAM-CAM outputs of the different aerosol species. We also used realistic surface emissions from CAMs, which have been interpolated to the MPAS mesh. And we used some Gopard chemistry to update the individual aerosols to compute the number concentrations. So the map, the figure on the left-hand side shows the vertically integrated number concentrations of water-friendly aerosols. The one in the middle shows the vertically integrated number concentrations of cloud droplet over that MCS that is represented here. You can see that the number of water-friendly aerosols is strongly decreased over the MCS relative to the background aerosols. And you can see, of course, the corresponding increase in the cloud droplet number concentrations. Okay, so the third thing that I want to talk about is the continued implementations of the MMM shared physics repository in 8.2.0. So for the last couple of years, we've argued that in order to simultaneously implement the same version of the physics parameterizations in WRF MPAS and CM1, we needed to clean those parameterizations and make them available directly from one specific shared physics repository. So we introduced the concept of that shared physics repository at the 2022 virtual workshop. And the aim of that, of developing that repository was to facilitate the physics implementations between the three models, as well as that were developed and maintained at MCube, so namely WRF, MPAS, and CM1, as well as making those parameterizations available to different host models. So the new infrastructures was built on first using the Common Community Physics Package, or CCPP, and a public GitHub shared physics repository that can be accessed by different models. Here I'm showing an example of using WRF, MPAS, and CM1, and a separate host model that can pull from that shared physics repository. Okay. So what have we done to date in 8.2? As I said previously, all these CCPP physics parameterizations were in a kind of fixed physics _MMM directory in the MPAS source code. We moved that repository to its own GitHub repository, NCAR MML which is now shared and tested in MPAS-WRF and CM1 and directly downloaded from that repository. We kind of did all the parameterizations related to the most convections for the mesoscale reference suite. Not only that those reference suites are tested in the DTC SCM, but they are also tested in CAM-SIMA. We've added the surface and PBL MYLN scheme to start kind of modifying the most convection parameterizations for the convection permitting schemes. So once you clone and download the source code, if you go to the physics directory, you are going to see simply two physics subdirectories, the one related to NOAA MP and the original physics_WRF. Now you compile the model, for instance, make Intel core equal atmosphere. And now after compiling the model, you are going to see this additional physics_MMM subdirectory, which has been downloaded and compiled using the managed external capabilities. One more thing is that I want to note is that the NTIC parameterizations is not only being tested in the DTC SCM, but we also started to test it in CAM-SIMA so that we can also add convection permitting parameterizations and the other set of convection parameterization into CAM-SIMA itself. Okay, so in conclusions, we have implemented a NOAA MP. We need to work with developers because we have had issues with compiling flag used in MPAS, as well as some issues with using different sets of compilers. We have implemented the aerosol-aware Thomson cloud macrophysics. We need to continue the parameterizations and verifications of the Hale options. Parallel to that, we are updating our first version of the GoCard chemistry to GoCard 2G for data assimilations of the aerosol optical properties for air quality, for instance, as well as turning cloud aerosol interactions. In terms of the shared physics repository, we are committed to continue to streamline new physics and physics updates between the M-Cube models. We want to continue the development of that physics repository. We need to add the CCPP meta files. We need to add some more documentations. So that's also work in progress. And we're committed to help users update and implement physics using that same framework. Future release, we are hoping to be able to release the physics related to the CMAQ parameterizations. I think there's a talk by Jeff Williamson this morning after me, as well as continue the parameterizations of prognostic ozone for also future implementations in 8.3 or so on. That's it.
Unfortunately, we don't have any time for any questions. We'll have to move on to our next talk. Thank you. Next talk will be given by Mary Barth on the development of the MUSICA system.
Good morning. Thank you, Lou. So I wanted to begin by acknowledging all the people that have been contributing to this MUSICA project, but in particular, those listed here, Matt Dawson, Louisa Emmons, Gabby Pfister, Bill Scamrock, Ren Smith, and Francis Bitt, who all contributed to this work. So many of you may not know what MUSICA is. MUSICA is the multi-scale infrastructure for chemistry and aerosols. You can see that on the bottom right. What happened really is that in our chemistry lab, we got a little bit tired of trying to support chemistry for a global model, a regional scale model, any other models. And so we decided to come up with this idea of having a model independent chemistry module. So our goal is to have MUSICA be part of a chemistry transport models that represent local to regional to global scales, from the surface to the top of the atmosphere, and to have the capability to do two-way coupling with other Earth system components. And all this to address frontier science questions, which I know you're all itching to do. And some ideas that, examples of frontier science applications are listed here. And I'm sure there are many more that you can think of as we move forward in understanding atmospheric chemistry in our complex Earth system. Okay, what we're doing in the MUSICA project is taking a two-pronged approach to developing this new infrastructure. The first I'm marking as testing, evaluating, and applying variable resolution grid meshes in a global model. And in parallel, we're developing this infrastructure and refactoring code to create a model-independent chemistry modules. So I'm going to begin with the first. We've labeled these MUSICA version 0 and MUSICA version 1. They are both working with the community Earth system model and with the community atmosphere model. So, so this is referring to some of the work that Bill mentioned earlier. So there are two capabilities in CSM-CAM. One is working with the spectral element dynamical core, which is a hydrostatic dynamical core. And the second is what Bill was talking about, where the MPAS dynamical core was also implemented into CAM. I'm going to spend a couple minutes looking at MUSICA version 1 and show you why doing this testing and evaluation is worthwhile. So I'm doing this on a case study where we're looking at the Asian summer monsoon. I'm interested in convective transport, what convection does to the atmospheric composition. And so we centered a regionally defined grid, as you can see on the right, over Southeast Asia. We have a regionally refined grid going from 60 kilometers to 3 kilometers, trying out different vertical levels so you can get the impact of the vertical grid resolution, and then comparing it to a 60-kilometer uniform grid mesh. In all of these simulations, we're using the same physics, chemistry, emissions, and we're not doing any nudging. So these are all coming from the CAM model. We're just doing a 5-day case study in the middle of August to look at the impact of convection on trace gases. Okay, so I showed a little bit of this last year, and this is the type of thing I showed you. This is convective transport of propane, which is really a tracer of transport. It has a longer chemical lifetime, so this is great to say, hey, the transport looks okay. So what I'm showing in the top rows are the regionally refined grid meshes for 32 levels on the left, 58 levels on the right. And in the bottom row are the results at 14-kilometer altitude in the upper troposphere for daily average propane for the uniform grid. And so you look from eye to eye, you know, this is not quantitative, but really what you see is something that's pretty similar, the same large scale patterns, similar magnitudes. And so things look pretty good. And so there are a lot of chemical species, and I worked my way through and looked at NOx, nitrogen oxides, which is not only affected by transport and chemistry, but also by lightning. And you can see something different happening here. The upper row, where we have the regionally refined grids, have really high NOx over Africa and southern India. And remember, our regionally refined area, let's see if that comes up, is over Southeast Asia. So this is outside the regionally refined area, which is kind of interesting. We wondered what could be causing this. One idea is that, hey, in the regionally refined region, we have to have a shorter time step because of that 3-kilometer grid mesh. So visit the time step, or maybe it's this lightning NOx protection. And so just to address the time step issue, we went and looked at running the uniform grid with 32 levels at different time steps. So this is what I showed originally. The top one is the regionally refined results. The bottom one is uniform grid. So the top one runs with the 20-second dynamical time step, 30-minute physics time step. The bottom one runs with the 300-second dynamical time step, 30-minute physics time step. If we change that uniform grid to have a 20-second time step for the dynamics, you can see results here that those results are for NOx in the upper troposphere are much more like the uniform grid than they are the regional refined grid. If you change both the dynamics and physics time steps to short time steps, again, you see really modest changes and not anything significant like we see in the regionally refined grid. So we don't think it's the time step that's affecting the NOx mixing ratios in the upper troposphere. So let's take a look at lightning NOx. In order to determine the amount of lightning NOx or amount of NOx produced from lightning, we have these set of equations. So lightning NOx production rate is dependent on the flash energy. The flash energy is a function of flash rate, but it's also scaled to account for the different grid box sizes. And then the flash rate is a function of the convective cloud top height. Okay, so let's look at these particular parameters. The lightning NOx production rate, I'm showing this at 10 kilometers altitude where it peaks in the vertical. And on the left is the uniform grid mesh. On the right is the regionally refined grid mesh. I'm focused here over Africa. And hopefully you can see these light colors. But what we're finding is that there's 5 to 10 times more lightning NOx production rate in the regionally refined grid compared to the uniform grid. So what about flash energy? Same thing. We find 5 to 10 times more flash energy in the regionally refined grid compared to the uniform grid. What about flash rate? No, we don't see that 5 to 10 times greater. We see some changes, and actually I did do some quantification of that, and it's actually smaller in the regionally refined grid compared to the uniform one, but it's a smaller change than this 5 to 10 times difference. So it looks like the explanation of the high NOx in the upper troposphere is due to this scaling for accounting for different grid box sizes. This is a recent result, so we're now investigating how to fix that and hopefully have that corrected in the near term. Now I'm going to shift gears to the second part of our two-pronged approach of developing the infrastructure for model independent code. We're doing this with a sort of new software development paradigm where we have these goals for designing the infrastructure. What I really want to point out here is the amount of unit testing that's being put into the code and having standalone software libraries. Also, this bottom line of having runtime configuration so you don't have to rebuild the code every time you make a small change, especially for chemistry. If you change your reaction rate, if you add a species, it's a lot of work rebuilding the code. Okay. So I just want to give you an idea of what this software development ecosystem looks like. This is our infrastructure for MUSICA. And at the heart of this are these software libraries, right? So they're meeting these software goals that I showed on the last slide. That's shown here. There it is on the bottom row here, where we're putting in software libraries. I should explain this diagram real quick. This is a software development ecosystem. The arrows are showing dependencies. So the MUSICA library depends on each of these software libraries. The solid lines is current development. Right now, we're working on making that. The dashed lines are future development. And actually, I forgot to change the fact that we are currently developing this MUSICA Python connection. And then when you see dashed lines, that's a proposed development. Okay, so the software libraries are currently being developed. We have software libraries for the model independent chemistry module, MICM, and the photolysis rates calculation TVX. They can work as, they've been released to the community as standalone software. This infrastructure can be connected to any atmosphere, and here I'm showing its connection that's being worked on currently to connect to what we call CAM-SEMA. So again, it's with the CSM CAM model working in the framework of that SEMA project that Bill mentioned earlier. It makes use of CCPP, so the CCPP MUSICA wrapper is being developed currently, and we hope to have it functional by this fall. It can also be connected to a box model, and we've called that box model MusicBox. And just to give you a highlight of what MusicBox is, it actually can be run as a command line chemistry box model, or it can be run on a web hosted service. This is what I'm showing here in the diagrams, is this web hosted service where you can make changes at runtime. You can change what chemical species you have in there, what chemical reactions, what temperature, what pressure, whatever you want to, and a lot of different things you can change. It's kind of cool. Also added in this music box capability are these flow diagrams to show us what are the sources and sinks of particular trace gases. So this is great code for testing, for doing scientific research, and for training purposes. And then we can work with with partners to expand MUSICA into other atmospheric models. We're working with the NOAA group with connecting it to their CAD-CHEM project, which will work with UFS. We're working with the geochem community, particularly Harvard and MIT, to bring in their modules into the MUSICA infrastructure. One thing you might notice in this big complicated diagram is that I have a little square for MPAS-A. This is a future development, and I wanted to make a statement about that. So we are moving forward to implementing trace gases and aerosols in MPAS-A using MUSICA. Initially, we're doing the work to add GoCAR2G, and Laura just talked a little bit about that work, but we're bringing that into the MPAS-A model. With that, MPAS-JEDI can extend the analysis variables to aerosol species, so that'll bring in a data assimilation component. And then we have a student visitor that's just beginning work on adding a fire plume rise calculation. We're in the planning stages of getting the full gas-phase chemistry into MPAS-A through the model independent chemistry module. We're been working with the India Institute for Tropical Meteorology and with NOAA to further this goal. I want you to realize, though, the resources for this development work are very limited. And so don't expect anything to be fast-tracked, but we're happy to partner with people. Okay, with that, I'm going to just leave up the summary, and I'll be happy to take any questions. Thank you.
We have time for maybe one or two quick questions. Oh, I thought Cliff was going to ask a question.
I thought Cliff was going to ask a question about how smoke affects weather. I think that's a good one, Cliff.
I was kind of curious, I mean, not that I'm complaining, but is there a particular purpose for the Python hook into it?
Well, my first reaction is next generation, right? Who's learning Fortran in school? Raise your hand. I'm glad one person, but really people are learning Python. And so we think that that's an avenue to bringing in future modules that are written into Python.
Okay. Okay. All right, we're running a little behind, or do we have, no, come on up to the mic. Don't be shy.
Do we really think that Python is going to become a computational language that can execute compiled code?
You know what? The answer is yes. Because I recently reviewed a paper that is a cloud chemistry model that does that in Python. And PNNL has a Python code for LES. So yes, these things exist.
Is the common compiler companies going to support that? Or does it...
Use the mic. Mike, use the mic.
Sorry. There'll be a just-in-time. There already are just-in-time compilers for Python, which do compiled code. The other thing is you can actually accelerate with different things. And then the other thing that I'm kind of interested in is the concept behind GT4 for Pi, which is basically the FE3 model has been completely rewritten and reduced source code by about 40% and runs on any platform, including CPUs and GPUs from the same source code. So I think in the long run, we're probably going to be developing domain-specific languages like Python and then deploying to different architectures. Anyway, it's not my talk time. Our next speaker is virtual. Is that correct? So take it away.
All right. My name is Jeff Wilson. I just want to say thanks for allowing me to share this virtually. And I take back everything I've ever said about virtual presentations. Talked about this a few times, the development of MPAS-CMAQ as a system, and we're excited to finally be able to announce that we're releasing it for public use. So there's a big team involved with this, including some people that I think are in the room right now. If you want to have more informal conversations after this talk, including John Blyme, Russ Bullock, and maybe Rob is there. If you don't know what they look like, maybe they'll raise their hands for you so you can get up with them after the presentation. So just some background to start with about CMAQ for those who are less familiar with the system. CMAQ's been around for just over 25 years. We just celebrated 25 years with it. And it's EPA's most sophisticated chemical transport model. It's used for research, but its primary use case is regulatory modeling. And that demand from the regulatory side of the agency drives a lot of the design philosophy of CMAQ. So if you're wondering why something was designed or runs a certain way, often the answer is because of a regulatory need or use case. The most popular way to run CMAQ is to run it offline. So you run WRF once, and then you can run a lot of CMAQ simulations with just that one WRF run. But you can also run coupled with WRF, and that gives you the opportunity to have aerosol feedback with the meteorological model, and also allows for high temporal resolution information exchange between WRF and CMAQ. It's a less popular way to run it, but it is run that way. And in the EPA, we're running CMAQ from the sub-kilometer scale, which John will talk about tomorrow morning, up to 100+ kilometer grid spacing over a hemispheric area. So depending on the needs of the application, we do have quite a bit of diversity when it comes to configuring CMAQ. But with the increase in popularity and capabilities of MPAS relative to WRF, the EPA has embarked on an effort to support MPAS-CMAQ coupling. So the idea here is to have a system where you can pick either WRF or MPAS and have your workflow be somewhat similar. So you can run with a global MET model, MPAS, regional MET model, WRF, coupled, or you can stick with running offline CMAQ where you've pre-generated your MET input. David Wong has done most of the work to make this happen, including designing a unified coupler to support both flavors of coupling. He's also designed an I/O system called Models I/O, MIO, that's a little less rigid than the I/O system that's currently in CMAQ, which is called I/O API. So a lot of work being done to get the infrastructure going to support all these different types of coupling, different ways of running CMAQ. So CMAQ is treated as a column model when you couple with MPAS, so it's just call CMAQ. And as a result of that, MPAS is doing all the horizontal transport for the chemical species. And because of the chemical advection of the chemical species, you get an additional computational burden that shows up when you run MPAS-CMAQ. So the blue line here is MPAS-CMAQ coupled. This is number of cores and then time it takes to just run a day using the 9225 kilometer mesh. And it's going to depend on your configuration settings, but you can see MPAS-CMAQ is a lot more expensive. It's about 4 times as much after some decent scaling to run MPAS-CMAQ than just to run MPAS alone. And the cost breakdown that we've seen in general is about 40% from chemistry, 30% from advection of all the chemical species, about 200 chemical species, and then 30% from the meteorology modeling itself. So just gives you a sense of what it costs to run MPAS-CMAQ. To run MPAS as an air quality model, it needs to at least match WRF in performance when it comes to EPA applications. And as we know, bad air quality often happens during pretty boring weather, which isn't always the primary focus of MET modeling design, just kind of no weather days. So to design MPAS for air quality work requires some modifications to make it fit for purpose. And this includes adding some EPA-inspired physics that's already in WRF, as well as some data assimilation. So that includes ACM boundary layer model, PX, LSM, some updates to KF, changes to the core init atmosphere preprocessor, and then for data assimilation, just a relatively simple FDDA and some indirect soil moisture data assimilation in PX. And then Rob Gillum's paper in 2021 showed that this all results in meteorology from MPAS that's suitable for air quality work. So here are some pull requests working their way into the MPAS repository so that these configuration options will eventually be included anytime you download MPAS, so you don't have to worry about trying to reproduce all these modifications yourself. They'll be included when you pull MPAS from the repo at some point when these get merged in. So that's underway. So to talk about how we've been using MPAS MPAS-CMAQ at EPA, we've been testing a few different meshes and different time periods with this system. We do a lot of development on a coarse resolution uniform grid mesh where every cell here has an effective grid spacing of 120 kilometer horizontal resolution. And we like that because you can run about a year and 5 days on a few hundred processors. So we've run several years with that. But we also run variable resolution meshes for shorter time periods, including a 9225 kilometer mesh, a 6012 kilometer mesh, and another one that I'll talk about shortly. It's in the works. And we've been using this already for some R&D, including research about biogenic emissions, windblown dust evaluation, lightning knocks, aerosol nitrate catalysis, other things, chemical mechanism testing. So we're already using it in-house on these different meshes. To configure CMAQ yourself, you'll probably want to follow this typical CMAQ configuration that we use. First, you'll download CMAQ 5.5, which will be available this fall. And you'll want to run with the emissions we've prepared for the mesh, which includes US, EPA, NEI over America, and then HTAP emissions outside of the United States. And then we recommend running with inline emissions where possible, like windblown dust, biogenic emissions from Megan 3.2, and we have relatively rudimentary stratospheric chemistry. Stratospheric chemistry is not a big focus of CMAQ, so we usually use we use some other product to fill in stratospheric ozone. Usually we use the CAMS reanalysis. It's a European product. So now I'll share a little bit of evaluation here for good measure. Our focus at EPA is usually on surface ozone and PM 2.5. So I'll show ozone here. For ozone, we compare with the global TOR2 network surface observations. And what we see is we get some seasonal biases over these 3-year period. The red is the model, and then the gray is observations. This is just for the whole domain average, but it's not very different if you just isolate the United States. We see a summertime low bias and a wintertime high bias, so sort of a suppression of the seasonal cycle. And this is something we're working on improving, but the good news is that the model is not really going off the rails. It's not experiencing any sort of chemical drift, either in ozone or in other species we've looked at. So it's a stable system so far. And then if we look at the surface ozone in the context of other global models, this is just July surface ozone average for different periods for, say, NASA's GEOS CF modeling system, MPAS-CMAQ, the European CAMS global reanalysis, and the NASA's older MERA-2 chemical reanalysis. What we see is MPAS-CMAQ is well within the range of the extremes here for the global models over this period. And GeoCF has different years that were available, but I will say that from what I've seen, the interannual variability is smaller than the model spread. So again, this is good news, I think, and that might depend on how much you value model spread versus model agreement, but I think for MPAS-CMAQ performance, this is good news that it's a good sanity check. Like I said, we also look at PM 2.5 at EPA a lot, and what we're seeing for PM 2.5, here I'm showing a 9225 variable resolution results. So this is January and July, where 25 kilometer grid spacing is over CONUS. And then down in the bottom left, I just included a January result from a 12 kilometer CMAQ offline, Cartesian grid. So this is sort of the gold standard for evaluation in CMAQ. And when it comes to PM 2.5, the biases are more local and more driven by emissions. And I don't want to dwell on the different patterns of bias or anything, but if you notice the magnitudes are, the color bars are all the same scale and the magnitudes are similar. So they're not terribly different between MPAS and WRF driven CMAQ, even if you go compare 12 kilometer to 25 kilometer. So again, I think this is good to see and depends on how you feel about this level of sensitivity to emissions. But all that just to say that MPAS meteorology, even if it was perfect, it's not going to lead to a perfect CMAQ solution. It's not going to fix all your emissions. Okay, so after seeing that evaluation, I know you're asking when can we start using this tool? And as I said, we plan to release CMAQ version 5.5 in September, and that'll be a feature branch in the CMAQ repo. It'll look like this, so you'll be able to explore that, check out that branch. And we're going to put some pre-generated inputs that you need on Amazon Web Service, hosting on Amazon AWS. Those will be free egress, so free to download for the foreseeable future until Amazon changes their mind. But we're going to start with some 2017 inputs on the 120-kilometer uniform mesh because it's easy to troubleshoot and get spun up on, I think. That'll include emissions, FDDA targets, ocean file for CMAQ, Megan inputs, stuff like that. And hopefully there's enough interest that can justify adding other configurations for other meshes, chemical mechanisms, or time periods. So of course, contact us if you're interested in running this for a specific application, and it would be great to add to this data set. I will say CMAQ MPAS-CMAQ at first will not have full functionality. If you've used CMAQ, there's a lot of tools, including ISAM and DDM for source apportionment and process analysis type stuff. It will not have those tools yet, and it will be somewhat rigid with flexibility. So there's a lot of flexibility being built into CMAQ all the time, including this ELMO post-processor for lumping, say PM for different PM 2.5 types. And it'll have a pretty rigid configuration when it comes to ELMO. So there'll be some constraints on how you can run CMAQ out the gate. But more features will be coming over time, including with CMAQ 6.0 for our next release in 2026. Also in the works over that time period are additional experiments going a fairly high resolution of 4 kilometers using multi-stage mesh refinement. So on the right is an example of what this looks like. This is 240 course, so you can see the grid cells, but it's going to be 60 on the outside, 12 over CONUS, and then 4 over California is what we have running. We just haven't turned on CMAQ, but we have the MPAS part running, and this is pretty exciting. We're also testing the new chemical mechanism CRACM that's going to eventually be the premier EPA chemical mechanism, the default in CMAQ. CRACM 2 will be CMAQ 5.5 and CRACM 3 in 6.0, so that'll be continuously supported for use with MPAS-CMAQ. So in summary, we're releasing MPAS-CMAQ systems as an advertisement that it's finally going to be publicly available and supported. And that's going to supplement our existing WRF CMAQ applications. And again, to reiterate that we're already using MPAS-CMAQ in-house for R&D, and you can too. The new system behaves about as well as other configurations of CMAQ and about as well as other global chemical models. And you will be able to start using it this fall. So I'll stop there.
Questions for our speaker, please step up to the microphone. Virtual, go right ahead.
Is MPAS-CMAQ fully coupled online as a two-way feedback model? Does the model accurately represent interactions between chemistry and physics processes in the atmosphere? And will EPA replace WRF CMAQ by MPAS-CMAQ in the future?
For the first part, the feedback, we will be supporting aerosol direct feedback in the near future, but say cloud indirect feedback, is not on the roadmap until a much later date. So as far as feedbacks go, aerosol direct interaction will be by CMAQ 6.0, but not by November. As far as replacing WRF CMAQ, I don't see that happening in the near future, just because the regulatory needs are so great for WRF CMAQ right now that we're not in a place where we can talk about replacing it just yet.
Hi, Jeff. Great to see these developments. I was just curious, on the slide you showed the various MPAS-CMAQ with the other global models, and I think it was for ozone, right?
This is just July surface ozone, yeah, just when there's the highest ozone.
I'm just curious if you had any thoughts on why CAMS reanalysis and MERA reanalysis tend to have higher kind of background ozone levels over the oceans.
It might have to do with the marine halogen chemistry. I'm not familiar with what sort of marine halogen chemistry they use. We found that helped a lot. Golem Sarwar is in charge of that here at EPA. He also does the aerosol nitrate photolysis stuff. So you'll see his name around a lot, but I'm not sure if they have as aggressive halogen chemistry over the ocean.
Okay,
that'd be my guess.
Seems like GOCF might have that too, but okay, so it's like a chemistry issue.
I'm not sure. That's just, I'm speculating, but that could be it.
Anyone else?
I thought it was really interesting how you presented all these pull requests that you have towards the MPAS repository. And I think that brings up a bigger discussion that ties into what Bill said in his opening talk this morning, which is how do we work together as a community to support physics? Because it may not be possible for MCube to absorb and support all this physics. So how do you see your potential role in supporting this physics, or how can we work together as a community for that?
Was that a question for how does EPA see its
Yeah,
role? Or-
yeah. So I could you are at the same time issuing a public release, which you plan to support yourself, and trying to get some of your contributions into the mothership repository. So
Right.
how do you see those two things going forward?
So the history on this is basically how it worked for WRF CMAQ was, and other these things like ACM and for the PBL scheme and PX. It's just a continuation of the past workflow where something that's built for purpose here gets submitted to, as you say, the mothership. And I see that being a healthy way to continue moving forward. So I'm not sure if there's any planned changes to that workflow. But that might be a better question for MMM.
It's a hard question, Jeff, especially if organizations have different goals too. That's usually what happens. So anyway, we have to move on. Thank you very much for your presentation.
Yep. Thanks again. And talk to John Plime if you have further informal conversation.
And we'll move on to the next presenter from my home mothership at NSSL, Larissa Reams, to talk about MPAS-IT.
Thanks, Lou. Hold on, let me start my timer. So I'm going to talk a little bit about this tool I created a couple of years ago for our uses at NSSL, and of course is now available for everybody else. There's a post-processing tool that hopefully everybody can find some use for MPAS. So just a little bit about a motivation. If you've ever worked with MPAS data, you know it can be difficult to visualize or analyze. There are tools out there, but they might be unfamiliar to a lot of users, and they might have to learn a lot of new tools to be able to do some of the things that they're used to doing with WRF data. There is a conversion tool that's provided with MPAS to convert the data to a regular lat-long grid, but it's relatively rudimentary compared to some operational post-processing tools. And so a couple of years ago, NSSL decided that we wanted to run some real-time CONUS MPAS runs. And we wanted the output to be compatible with our standard post-processing tools so that we could provide the standard visualizations that we do some of our other WRF in-house runs. So we had to figure out how we could post-process this data to achieve that. And so my solution was this MPASSIT tool that I will say I built a lot of the background on some of the code that I have written and used for ChangeRes Cube, which is a UFS utility. So if you end up diving into the code and you've ever looked at some of the UFS code, it might look familiar. So a basic overview, MPASSIT takes the irregular mesh of the MPAS data from both the diagnostic and the history files and converts it to a regular grid. That grid can be regional or global. You can specify grid parameters like you do in your WPS, for those who are familiar with that, or you can actually provide it with a WRF output or WRF grid file that you want to mimic. It can be larger than your grid. It can be smaller than your grid. So it's relatively flexible with the output grid compared to what the input MPAS data looks like. It runs in parallel, so it is scalable. It supports multiple different kinds of variable interpolations, and I'll detail a little bit more later how that works. You can specify at runtime what variables you would like processed. And again, the target grid properties that's also specified at runtime in a name list. The output is standard netcdf format. If you set your name list options correctly, you can make the file be almost imperceptibly different from your WRF data. So it will look very much like your WRF data. The variable names are always going to look like your WRF data, but there are some small differences that I'll talk about here in a bit that you can change with your name list settings. I've provided the link here to the GitHub and a QR code. Don't worry, I will show all of these like 2 or 3 more times just to make sure that you can grab those when you have time. So some basics, I apologize, this is going to be pretty dry. I'm hoping even if you don't get a whole lot out of some of this stuff right now, this will be a good reference for those who plan to use this to come back to help with this process. Of course, you have to load your necessary libraries. It does use CMAQ like UFS utilities do, so the build process will look similar to those who have used some of the UFS utilities. Need your basic CMAQ Intel or GNU processors, MPI, also NetCDF, and then HDF5 if your NetCDF is HDF5 compatible. And the difference here that you'll see from WRF and MPAS is that this will need ESMF. That is, ESMF is the backbone of the entire code and is used everywhere. If you're running on one of the NOAA platforms such as Hera or JET, there are included working module files. So there's no need to load any environment separately. That will be loaded when you build it. So it should be a pretty seamless process. For other platforms, for your Linux platforms, your local clusters or Duratio, you'll need to configure some of the, you'll need to create a module file and set some of those appropriate environmental variables. Build command is pretty straightforward. Your target would be the name of your machine. Again, all of these options here in the second part are optional. Compiler would be Intel or GNU, and debug is your classic how much information you want and whether you want some stack traces if you're trying to develop some stuff. So running MPASSIT, there's these hist list variables. I apologize for the misspelling there. This is where you will provide the variables that you want to process. I'll show an example here in a bit on what those will look like. So this is how you'll configure the variables that you want. And of course, a name list, which I'll also give an example of here in a second. You will want to ensure that you're using enough memory based on how large your input and target grids are, especially if you're processing a lot of 3-dimensional variables. So you may want to run with more nodes and less processes because ESMF is pretty notorious for being a bit of a memory hog. And as an example, this is a command I would use to process a full 3-kilometer CONUS MPAS run onto a 3-kilometer CONUS target Lambert conformal grid. So I used 120 processes on 10 nodes. So just be aware that you might have to play around with the amount of memory you're providing your process. So I'm going to go through a lot of details here again. Don't worry about taking all of this away right now, but hopefully you can go back and view this later if you need some help. You'll provide your input files, the full path to your input files. Note that the grid file for MPAS can be the init or the grid file. It just needs to have the grid information in it, lots of the grid specifics. So I've tested it with both the init and the grid file, and that works. And then, of course, your history and your diag files from your MPAS output. This is the block decomposition file that if you've ever run MPAS will look familiar. This is optional, but if you're using a large grid, like a full 3-kilometer CONUS grid with a lot of grid points, you're definitely going to get some speed up in the interpolation if you provide this file. It doesn't have to be the same one you run your MPAS forecast with. It doesn't have to use the same number of cores. Just make sure that however many cores it's set to, that's also how many cores you're running MPASSIT with. This is the full, the output name. You can choose whatever name you want. Just make sure it's a .NET-CDF file. This allows you to either to interpolate one or both the diag or the hist files. So if you only want data from one or the other, you can specify that to cut down on your processing time. This is the variable I mentioned that will change some of how your data looks. I would set this to true if you plan to process through UPP, because the output is UPP compatible. It adds things like extra metadata, additional variables like a base. Like if you're used to looking at WRF files, there's like a base pressure and a base potential height. So this adds that, and it also puts the wins on your C-grid stagger like you're used to seeing in WRF. This is just to get some ESMF log files. Can make your directory kind of messy, but it's really useful if you're running into problems to help debug. And this is should look familiar if you've ever run WPS. These are all of the grid settings if you wish to set your grid to with the grid settings as opposed to an output file. So these are all your standard grid settings. Of course, this will look different if you choose a lat line projection instead of a Lambert conformal, but the options will look exactly like WPS. In fact, it uses all of the grid creation tools are from WPS. So it supports those options. Note that technically Mercator and Polar are supported, but I have not tested them. So I can't make any promises about those. And one note, this name list does not show, this name list was for regional grid. So it does not show that there is a setting called is regional. If you have global MPAS data, you will need to set is regional to false, but the default is true, hence why it's not in this name list here. So if you instead have a WRF input file and you want to interpolate your data onto that file, you can get rid of all of those WPS grid definitions and instead just provide the link to your WRF input file. I mentioned the hist list and the diag list files. This is what they look like. They're pretty straightforward. In both of them on the left column is the variable name in the MPAS file. And on the right, if you've used WRF data, those variable names should look familiar. Those are the names that you would like the data to be written to. You can change those to whatever you want, but I've chosen to leave these looking like WRF data so that it will process through UPP. And again, the hist list 3D is for your three-dimensional variables, so your variables that have a Z dimension, and 2D is for your variables that come from your history file that are 2 dimensions. The other two that you will need will be diag list, which is the list of variables you want from your diag file, and a hist list soil if you'd like to process soil variables from your history files. There are default settings of these in the repository, in the PARM directory, so don't worry about having to create these from scratch. You can start with what I have and pick and choose and add as you'd like. Some limitations, I mentioned that we do support multiple kinds of interpolations, but they are hard-coded. There are hard-coded lists of the variables we would expect you might ask for conservative or nearest neighbor. If you would like to change those, you can modify those variable lists inside the code. And as I'll mention on the next slide, I do have some plans to make that user configurable from the hist list files, but it's not as of yet. All of the three-dimensional history variables are assumed to be a vertical dimension NZ, except for ZGrid and W, as those are staggered. But again, this is a list in the code that you can modify if for whatever reason your data looks different than this. One note on target grid choice, you can choose whatever target grid you want. As I mentioned before, it can have parts of the grid that are outside the MPAS grid. It can be much smaller than the MPAS grid. But if it does have data points that are outside of the MPAS grid that you give it, it will be filled with zeros. The missing data will be filled with zeros. As I'll mention here in the future, I plan to make that user configurable. So I would like to make it so that you can set it to a NANS, which I know will be helpful for UPP if your target grid has missing data. If you fill it with NANS, UPP likes that better than you wouldn't want to verify zeros. You would want to verify NANS that would know it's not available. And again, like I mentioned, we want to make the HIST list and diag list interpolation options user configurable. Just some final thoughts. Again, like I said before, here's the link to the GitHub and a QR code again. Thanks to everyone who's tested the code. I've had a lot of people use this and provide me feedback, find bugs, especially Craig Schwartz and Yunhong Wang. Please reach out or make a GitHub issue if you find a bug or if you have a new feature or a request, and we can talk. So definitely do that. And I will leave just an example of two figures that look exactly the same as they should. That's all I have. I'll take any questions.
We have time for one quick question.
Hi, it sounds like you got a great tool here. Thank you very much for doing that. Just a quick question. In our WRF, we've set it up where our center longitude is not the exact same as our standard longitude. And I noticed in the UFS version of it, their change grid cube or whatever it's called, you can't handle that. Just a plug, if you can't do that sort of off-centered standard longitude, that it would be great to have that to match what you can do in WRF.
The only parallel between this and change-res cube is the backbone of ESMF and how it handles interpolation. It uses ESMF for interpolation. The grid creation is all WPS. So if it's a grid you can create in WPS and WRF, you can create it in MPASSIT. So you can create whatever target grid you want.
Okay, yeah, I saw you had a reference longitude. Just make sure you also have a standard longitude.
I think they're the same thing. It's just a different in naming convention, but yeah.
That was the assumption, and that's why I can't quite match it, because they aren't the exact same thing.
Right, yeah.
Thanks, Larissa. We'll have to move on. I know everybody's starting to get hungry. So I think people are sneaking out to get the early food right now. So our last talk is on UXarray. So go to it, Jeff.
Thank you.
All right.
Good morning, everyone. I am Orhan from NCAR CSL, and I'd like to talk about UXarray today. Before that, I feel like this might be a hard talk for me because it is not because of the UXarray tool, but because it is almost lunchtime. This is the last session, and while folks are starting to think about the meals, I have to talk about something that's not edible. So just bear with me, and let's do this before lunch. So thank you so much for your patience in advance. Regardless, UXarray is an extensible and scalable Python package we have been putting together for the last 3 years to support MPAS, and not only MPAS, but other several unstructured grids. Behind, let me just figure this out. Okay. Behind UXarray, there is a collaborative effort where our NSF awarded Project Rygene is collaborating with DOE's SEEDS project. So I am one of the co-PIs in Project Rygene, and I am in charge of the software development efforts for UXarray. Our motivation for proposing the Project Rygene was the arrival of kilometer-scale global models for weather and climate. And as a result of that, the slow but steady transition from structured grids to unstructured grids was also one of the motivations for Project Rygene. There are some challenges that I think most of the people in this room should know. There is no widely used convention for unstructured grids, in contrast to what is existing with structured grids. There is the UGrid conventions
that we are building UXarray, taking into account that conventions, but there are some people and community groups who are adopting UGrid, but it is not as widely adopted as it is for structured grids. There are just a few analysis tools that are capable of operating directly on unstructured grids without needing to regridding them to lot-long grids. And few kilometer resolution models generate lots and lots of data, which is making the things even further complex. And one last thing is some trivial functionality for structured grids may become really complex and computationally costly for unstructured grids. For example, finding the grid cell that contains a point of interest, for example. To address these needs, Project Rygene had two essential goals. One is the more obvious one, to develop an extensible, scalable, and open source software tool in the scientific Python ecosystem, which turns out to be UXarray, which I will be talking about in detail in just a few minutes. And in addition to that, we would like to do this in a sustainable and community ownership way. And I think the collaboration between Project Rygene and DOE Seeds project is kind of a good starting point for this, but we are looking for further community engagement around the effort. Even though we are mostly trying to put together directly functionality that would directly operate on unstructured grids, we are still wanting to put together regridding functionalities for cases where it could still be usable by the community. Before I jump into the details of UXarray, I would like to give you some background information about why the name is UXarray, what we are building UXarray upon in the community. So I think to answer that, I'd like to start with the introduction of Pangeo community, which is a community of practices around a number of community needs. I think in the core of everything, you see the XArray for multidimensional labeled array processing. And in addition to XArray, you can see Dask for scalability and parallelization purposes. And there is also Jupyter for interactive accessibility and documentation purposes. XArray is important, and we are building UXarray upon XArray. And the name might be suggesting already unstructured grid XArray. So XArray is convenient because it allows you to select values by not integer indexing, but your labels of interest. And it is commonly used by geoscience people because of the I/O input-output capabilities it has. It is supporting NetCDF and a lot of other input-output technologies like OpenDep, HDF, and ZAR. XArray can operate very well and smoothly with a lot of scientific Python technologies such as NumPy, Dask, Pandas, and Matplotlib for visualization. And it is performant with all of the vectorization and compiled language bindings. Because of all of these reasons, there are a lot of people in the community who are using XArray already. So, as I mentioned, we are building UXarray on top of XArray. Technically speaking, we are inheriting from XArray some significant cornerstone data structures. For example, to represent unstructured data sets and data arrays of interest, we are inheriting XArray's data set and data array. And on top of them, we have created a grid object which is allowing us to recognize what unstructured grid we are dealing with. And on the top of this slide, you can see all of the supported formats and file extensions. As of today, we are already supporting with UXarray. Just the exception here is icon, which is a work in progress. I think we are anticipating to support that in, I think, just a few weeks as well. What we are doing is whatever grid format we take into UXarray, we represent them in a unified UGrid-like convention, and that is being possible with the grid object. And I'd like to give you what strength might be coming from such a structure where we are inheriting from XArray. So with the help of this structure, the user of UXarray is able to not only call unstructured grid-specific functions, but they can also run any built-in XArray functions as is. So for example, just assume this case where you have to run a statistical function on your entire data set. You can do this with UXarray with calling the built-in XArray functions, or some of the XArray functions are overridden under the UXarray umbrella for unstructured specific purposes, and some other additional functions that we are implementing for specifically for unstructured grids. Actually, I'd like to ask a question here. So how many of the people in the room are already familiar with XArray? Okay, yeah, good. I think maybe slightly more than half. Yeah, if you are already using XArray, starting to use UXarray should be trivial. This is one more toy example where we have represented the same data in structured and unstructured grids on the left and right-hand side of the slide, respectively. On the left-hand side, you can see how you would do that in XArray. So basically, you would be importing the package in Python, and then you would be opening a data set. Then from that data set, you would be picking your variable of interest, also picking your time step, and then plotting that data. And very similarly, you would be importing your UXarray rather than XArray. Then the rest should look always almost the same. So opening the data set, picking your data array and data time step of interest, then plotting that. This is the unstructured grid, and this is the structured grid with the almost same lines of codes. I would like to give you a sense of what we did for achieving some things on the second essential goal, to build some community around UXarray. So everything, including the project lifecycle management boards, are open and publicly available on GitHub. And needless to say, our code is open source, and we already talked about Pangea. We have bunch of like comprehensive documentation, like contributors guides, user examples, user guides to train our user about structured and unstructured grids and the terminology around UGrid conventions. And we have made a lot of open discussions on GitHub to make sure we are incorporating community needs into our decision making for design and functionality prioritization purposes, and lots of examples around UXarray. And you can access the repository and documentation of UXarray through the QR codes. I'd like to give you some current status snapshots on infrastructure, functionality, and capabilities of UXarray. So infrastructurally, we are there with a user-friendly web page with a lot of user documentation to, again, give tutorials about UXarray and also give examples of specific use cases. And we have a detailed contributors guides for those in the community who would like to contribute to UXarray to some extent. And we are doing monthly releases on Conda and PyPy. The last release was May, and we are, I think, working on June release now. The current status for functionality as of last month's version was, I think we already talked about the supported data grid formats with UXarray. MPAS is one of them, and I think the most earliest one of them that we started to support. Grid metadata inspection is naturally available through the grid object, and we have put together some grid subsetting and remapping functionalities, and we are still working on some advanced versions of them as well. Computational operators wise, we have provided integration, gradients, and difference functionalities. And we have also implemented several visualization functions that for several months we have been giving tutorials and demonstrations around NCAR and outside NCAR. And on this Friday, if you are going to be around, we will be giving a mini tutorial about UXarray, visualization, and data analysis functionalities using some MPAS focus and MPAS datasets. This is just an example to show you what capability UXarray has. This is a 3.75 kilometer MPAS data, and it has roughly 42 million faces in it. And if you keep zooming through UXarray, you can see the MPAS structure underlying the data. Last but not least, the future work, including the work in progress. We are working on some advanced derivative capabilities. We are also trying to put together non-conservative and conservative zonal means. That was kind of a community question for us to prioritize. We are working on supporting additional grid formats such as GEOS, and the topological aggregations are partly there, and I think they are going to be in our June release, and some of them are going to be in the upcoming months as well. And rendering performance optimizations is also a work in progress. Longer term, we are looking forward to collaborate with more community groups and people, and we are open to discuss anything that we can do to support MPAS and other unstructured grids. So thank you so much. I think this should be the last slide. Yeah. Any questions?
Any questions from online? Yes? No? Go ahead. One question. I'm sorry. Yes? No?
Sorry, I'm just trying to keep everyone from getting into lunch. So a quick question, just to clarify, does UXarray inherit all of the parallel processing and HPC performance through Dask that goes through regular X-ray?
Yes, not from Dask, but since we are inheriting from XArray, like technically speaking, since our data structures are relying upon XArray data structures, we are compatible with Dask.
Great. And how long did it take to render that 42 million hexagons?
That's a good question. It really depends on the visualization function you are looking into. If you are trying to plot the actual polygons without, compromising with any data fidelity, it would take probably 20 minutes of processing. But if you are rasterizing, it is just a few seconds. And we would really like to showcase some of these on Friday.
Great, thanks.
Yeah, sure.
Your virtual question now? Okay, let's go to, what did you say? Oh, Abraham, does Abraham have a question there?
Yeah, I had a question. I wonder if you could go a little bit, just not to take too much time, but just about how the indexing works. For example, iSelect with XArray on the MPAS grid, especially with those nodes that are kind of off center of the lines from that one plot. Yeah.
That's a great question, and we have implemented unstructured grid specific iSelect for UXarray. So if you access iSelect through UXarray rather than XArray, you are getting the unstructured grid index selection. Is that a good answer to your question?
So I guess you had a figure back a few
slides ago that I think showed. Yeah, right there on the top right. Is that I guess the indexing method you have? I don't know if you could go just really quick into how that is set up.
Yeah, I can, but which one of the visuals are you talking about?
Abraham, I'm sorry, we're running late for lunch and want to start on time. Can you ask, I hate to cut you off, but this seems a very technical question. So can you guys do it offline?
All right, thank you.
I'm sorry. Yeah, we're just running late. And
I will be sure to, follow up with Ibrahim. Yeah.
Can you follow up?
Thanks
okay.
so much. Yep.
Thank you, everybody. Thanks our speakers again, and let's get to lunch.
Okay, it is 1300 hours for those of you who are from the Navy. We're going up to our next session. And this next session is kind of funny to see how this is going, because you got a NOAA guy sharing the session, and we have talks from NOAA GSL, from some commercial folks, from foreign weather bureaus, and from NCAR. And so if you ever thought that all these communities are just becoming stovepipes and staying stovepipes, just looking at the program that we have today for this session tells you that I hope that we are going in the direction that it looks we're going in terms of actually creating a much broader community and talk to each other. So our first speaker has not made it to the podium yet, so I think he's going to give up his time slot, right? So we have 18 minutes per talk. We will be running I'll be running the light switches here, which will be adjusted to 18. So if you talk too much, I can talk more, and I'll take you off the stand. Okay. Go ahead, Adam.
All right. Well, good afternoon, everybody. Thank you for having me. I'm going to talk about the MPAS evaluations that we did during the 2024 NOAA Hazardous Weather Testbed Spring Forecasting Experiment. I want to acknowledge all the co-authors I have listed here. These experiments are big group collaborative efforts, so it takes a lot of people to make them happen. So thank you to everybody that contributed to this. All right, see if I can figure this out. There we go. So these spring forecasting experiments, they are 5 weeks long. We do them every year at the peak of the severe weather season. They're jointly organized and facilitated by the Storm Prediction Center and the National Severe Storms Laboratory. Our 24 experiment was hybrid, which means that we have both virtual and in-person participation, 68 remote and 92 in person. The goals are listed there. The one I want to highlight for this talk is that we facilitate experiments to optimize deterministic and ensemble CAM systems to inform UFS development. And so we use this framework to do this that we call the community leveraged unified ensemble. Basically, this is just a way for us to coordinate all the different model contributions that we get from our collaborators. Whoops. These arrows don't make sense, but I think I have it figured out now. So the experiment this year included regional MPAS configurations run by NSSL and GSL in collaboration with NCAR. So we are doing this because our plan at NSSL is to replace WRF as a next generation die core for our warn and forecast system. Also, MPAS is being considered as a UFS die core. So we want a model that is able to accommodate further refinements in grid spacing, advances in data assimilation, and one that can fit within the UFS. So our results from last year was the first year that we examined MPAS configurations. We actually had one experiment 10 years ago where we looked at some, but in terms of recent experiments, last year was the first one. So the results were very encouraging, and so we've expanded those MPAS activities for this year. And so before I dive into some of the results, I just want to point out,
This year was great in terms of severe weather activity. So it had the most enhanced or greater risks for any month on record. And this is since SPC implemented the enhanced risk category. So several moderates, a high risk on May 6th. Also, the January through May period was a top 5 in terms of numbers of confirmed tornadoes. So great for us, probably not so good for lots of other people that were affected by it. This is a table. It just shows all the different model contributions that we examined during the SFE. And then I've just highlighted the regional MPAS configurations from NSSL and GSL. And then NCAR also contributed a global 5-member ensemble with a refined mesh over the CONUS. And Ryan Sobash and Craig Schwartz both have presentations later where they'll be talking about some of those results. So at NISL, we had 3 unique configurations initialized at both 0 and 12Z. 2 were initialized from HER with Thompson and NISL microphysics. 1 initialized from RRFS with Thompson microphysics. GSL had 5 members that they initialized from RRFS ensemble members, or REFS members is what I will refer to them as. And then we also did these resolution sensitivity experiments. The 2-kilometer run did not happen, but they had a separate 4-kilometer run that we looked at. All right, and the NISL configurations, we run those year round, and you can find those forecasts at cams.nisl.noaa.gov if you're interested. So this is a table. It's just showing all the evaluations that we did this year. The ones with the red boxes involve MPAS, and then the ones highlighted in yellow are the ones that I'll be presenting. And so we'll look at results from our day 1 deterministic flagships comparison, and we had a day 1 ensemble flagships comparison. We also have day 2 evaluations that I won't have time to touch on here. So the deterministic flagships, the point of this is to gauge progress for severe weather predictions from deterministic model solutions from each contributor. So we're kind of having all of our collaborators put their best foot forward in terms of a model configuration. And so we looked at the C-Shield from GFDL, MPAS from NSSL, and we used the HT configuration, so initialized from the HER using the Thompson microphysics because subjectively it was the best performing configuration from the previous year. And then we have HER, RRFS, NASA GEOS is an FV3 configuration, global with the NEST, and then MRMS there is the OBS at the bottom right. And so we're looking at the evolution of forecast reflectivity, comparing it to OBS, assigning a 1 to 10 rating. 10 is the best, 1 is the worst, based on things like the timing of storms, convective initiation, convective mode, the intensity of convection, that sort of thing. And then we have each participant just assign a 1 to 10 rating, and we compile those ratings throughout the experiment. Oh, and I have to emphasize these comparisons were blinded. You did not know which model was which when you were assigning these ratings. We did reveal the models after so that we could have discussions about that. All right, so these are the ratings. So the violin plots show the distribution of the subjective ratings. 10 is the best, 1 is the worst, and they're ordered from those that had the highest ratings from those that had the worst. So the HER was the best, which it has been the previous 2 years. And then MPAS was second best relative to the HER. And both HER and MPAS are kind of in a different category relative to the ones below it. They're quite a bit higher. And so all the FV3 configurations are ranked lowest. So we have RRFS, NASA GEOS, and the C-Shield configuration from GFDL. The order of these ratings was the same as last year, except NASA GEOS and C-Shield, or the GFDL FV3, actually switched places. So C-Shield is now ranked the worst there. And this is just showing the change in ratings relative to last year. And so I think intuitively, you would have expected that the scores would have went up, even if you didn't change the model configurations, because the weather regime strongly forced events that are inherently more predictable. So you'd expect the forecast to be a little bit better. And HER and MPAS were better, but RRFS actually went down. And I think that's because of some changes that they made to the configuration that actually hurt it more than it helped it. And C-Shield also happened to go down. This is just an example showing the type of things that we look for when we're doing these evaluations. And so this is just kind of a random case, 8 May from this year. This is 12 hours into the forecast. If you look at the bottom right, those are the observations. And you see you had storms that had just initiated kind of south of Kansas City. And then over the Kentucky-Tennessee border area, you had pre-existing convection. And so the HER and the MPAS runs to pick these areas pretty well. But look at the RRFS at the top left. You don't have anything near Kansas City. And then over that Kentucky-Tennessee area, you have this like speckly light to moderate precipitation, which we saw a lot. We're attributing that to the convective scheme, GRAF that was used, and it was only the deep convection that was turned on. And so I think you're seeing convection being suppressed by the convective scheme in the RRFS. So yeah, thumbs down for RRFS, obviously, thumbs up for HER and MPAS. All right, so you go forward in time. By the time you get to 0Z, you have this line of storms that formed the western part of the domain along a boundary. And then you also had storms in the warm sector in the Kentucky-Tennessee area that had kind of redeveloped. Look at HER and MPAS. They did pretty well. HER probably a little bit better than MPAS. Some displacement errors in MPAS, and then not enough convection in Tennessee. But if you look at RRFS, it's just missing convection everywhere. So that was not good. Again, thumbs down for RRFS, thumbs up for HER and MPAS. And then finally, we get to 30 hours into the forecast, and then I've just kind of circled the area centered over Tennessee. HER for this particular time would have been rated a little bit higher than MPAS as well. But then look in RRFS, you have the speckliness, and the convection is totally displaced. So again, we got our thumbs up and our thumbs down there. Okay, so we also did subjective ratings of environment fields and QPF. HER, top performer for all of those, temperature, dew point, CAPE, and QPF. MPAS, for all of them, a close runner-up. And then most of them, RRFS was in third. But I wanted to highlight QPF because RRFS, as you might expect from looking at those reflectivity forecasts, did not perform well for QPF. And it was the only model whose QPF rating decreased relative to the previous year. So this is just a table showing that change in ratings. Okay, so this is just showing an example of some of the QPF forecasts for a particular case. The OBS are at the bottom right. There was a convective system that had kind of grown up scale from some discrete modes and went across the south, Louisiana, Mississippi, Alabama, dumping some heavy precipitation. The HER got that axis of heavy rainfall pretty well. MPAS did as well, but it was displaced a little bit to the south. But RRFS never grew the system upscale. So you just had these kind of isolated areas of heavy precipitation. All right, now I want to go into some of our ensemble comparisons. And so we had, or I'm going to show results from 4 configurations that we looked at. So we have HREF, which is multi-model, multi-analysis, multi-physics, got a lot of diversity, and then it's also time-lagged. EMC refs, and so that's FE3, and it's got perturbed members at 12Z. So you have the control member at 12Z, the perturbed members at 12Z, and then we also throw in the HER because EMC has said they're going to keep the HER around. And so that's going to be a part of the ensemble here. And then you also have all those same ensemble members initialized at 6Z so in a time-lagged ensemble. SPC refs includes all of those 12Z members, but does not include the perturbed refs members that are time-lagged. It only has kind of the base time ones. And then also throws in HER RRFS at 6Z, her RRFS at 0Z. So 2 time lagged or time, so -6 and -12. And then MPAS-REFs essentially just replaces those FV3 members with MPAS members. And so for these ensemble comparisons, we look at storm attributes and we construct NMEPs from them that serve as kind of proxies for severe weather reports. Again, the comparisons are blinded and we do the 1 to 10 subjective ratings. This is just a depiction of what these fields look like when we do the evaluations. Okay, so what did we get? This was we were a little bit confused by some of these results at first, but I think I have good explanations for all of them. So for one, the ratings were more tightly clustered than they were for the deterministic comparisons. So you have HREF, SPC refs, and EMC refs all pretty close together. And MPAS refs actually perform noticeably lower. So what is going on? One, all the ensembles leverage her in the membership. So this is likely helping them, but also making them more similar. RRFS, so these ensembles have RRFS in them, and we showed that performed very poorly. So you would think, well, wouldn't the ensembles perform poorly as well? Turns out that the ensemble members have different combinations of physics that actually performed better than the control member. So the performance for the ensembles isn't being degraded as much. The objective metrics that we have, so this is a performance diagram on the right there, shows that the control RRFS member kind of falls in the middle of the ensemble members, but there was one perturbed member, M02, that actually performed quite a bit better than all the other RRFS members, and that one had scale-aware SAS, convective parameterization, MYNN, and Thompson. So recommendation would be, hey, let's just switch to that physics combination, I guess. So yeah. And what about MPAS performance? Why is it poor when the deterministic ones were so good? Well, it turns out we used the same UH threshold to compute those probabilities as we did for WRF, but the UH climatology is actually much lower in MPAS. And we had just implemented this 9-point smoother so that we could be consistent with how WRF computes UH. And I think we didn't realize how much that would dampen the UH magnitudes. And so when we looked at the probabilities, they were just lower. And people did not like that they were, systematically lower. And so the ratings were affected by that. So yeah, this is just showing the UH values kind of as a function of the percentile. So you have FV3 really high, NAM-NEST in the middle, and then WRF and MPAS, the lower ones. Okay. So the last thing, yeah, I just want to show some of these performance diagrams showing the different members here, and just a few things to point out. So this is objective performance of simulated reflectivity. And so you want to be up and to the right on these diagrams. The HER runs objectively much better performance than RRFS. The MPAS runs pretty similar performance to the HER. And then the RT initialized, so RRFS initialized runs actually performed better than the HER initialized runs. So this makes me think that the DA in RRFS is actually an improvement over the HER DA, which is a good thing. And then finally, so we have the REFs members there that I've circled, and then the MPAS members initialized from them are up there. And so they also have objectively better performance. So there's the REFs members and then MPAS initialized from those members. It's kind of switch back and forth. So, so I'm just I'll leave this up. That's it. I'm done.
Yeah, people running the experiment are very efficient in exactly using their time. So one question. If not, it doesn't matter because I'm pretty sure that this is going to be fodder for a discussion later on today. So thank you. Our next speaker, we're moving on away from NOAA.
All right, good afternoon. So I'll get right to it. In May 2023 and 2024, we ran real-time ensemble forecasts with 5 members, and these forecasts went out to 5.5 days. We did this with a global variable resolution MPAS configuration with about 3-kilometer horizontal cell spacing over most of North America. And we provided these forecasts to the Hazardous Weather Testbed spring forecasting experiments, where they were evaluated by program participants and also used in experimental forecasting activities. We also published them to a website that you can go and check out. It was pretty neat. I don't think it's too much of an exaggeration to say that these forecasts really did break new ground when it comes to medium range prediction. The current operational guidance suite that we have for medium range forecasts over the United States is relatively coarse convection parameterizing models like the GRAF, which has about 20-kilometer horizontal grid spacing. So this was the first demonstration that in real time, you can run convection allowing ensemble forecasts over the CONUS. So we think that was a pretty cool demonstration, and we did this in both May 2023 and 2024. I will mention that as a part of this demonstration, we also ran real-time forecasts from a completely separate modeling system in collaboration with GFDL that was based off the FV3 dynamical core. So it was also part of this demonstration of bringing convection-allowing ensembles into the medium range. But since this is an MPAS workshop, I'm not going to talk about these FV3-based forecasts. I think it's fair game to ask, why would you even bother studying medium range convection allowing ensembles? And well, I think unless AI and machine learning just put 90% of us in this room out of a job, that we're going to eventually be having global convection allowing models. We're not going to be running 3-kilometer regional models. And so that means we're going to need global convection allowing ensembles to quantify forecast uncertainty as the forecasts go into medium range periods. So I think that we should start learning about these future systems, and I think that there's a lot of society benefits of being able to extend hazardous weather guidance into medium range periods. Just a few science questions that we're looking to answer. It's really just about the benefit of having convection permitting grid spacing into medium ranges, because this is really unexplored territory, at least over the United States. So some things that we're looking at is just, is there a benefit of having convection allowing grid spacing after about 3 days compared to coarser resolution models like the GEFs that are currently run operationally? Can medium range convection allowing ensembles provide skillful and reliable severe weather forecasts and accurate storm mode depictions? And then there is a question about if it's worth the expense to run these medium range ensembles when we do have machine learning techniques that can give you the same thing at fractions of the cost. So specifically, here's what we did. We ran 5 ensemble members out to 5.5 days with MPAS. Here's our mesh. This was a global mesh with 15-kilometer horizontal cell spacing over the globe that's smoothly refined to 3 kilometers over most of North America. We used GEFs for the initial conditions, just members 1 through 5. All of the members use identical physics. So this is a single physics ensemble where diversity is only provided by the initial conditions. And we use the convection permitting physics suite with a scale aware new TIDCA scheme. If you're curious, we could do this with about 23,000 processors, and the forecast finished in about 7.5 hours. So this slide is going to prepare us for some movies that will hopefully play on the next slide with some help with some friends from the back. What you will see are observations in pink, and then paintball plots from the 5 members and the splotches, and then probabilities of reflectivity exceeding 40 dBz from the ensemble members. So what we're going to look for is for convection to develop over the Texas Panhandle. Look for the pink, that's the obs. And this is a 3-day forecast. And we've got convection that's begun to develop, and now it's going to move toward the southeast towards Houston as a bit of a Boeing segment. And at first glance, well, we'll play it again, if you don't mind. We'll play this a couple times. Now you can check out the MPAS members. And you'll see that as convection develops over Texas, the members pretty much have it. And then more impressively, they maintain the system as it moves. So I think for a 3-day forecast, this is pretty darn impressive. And especially this was a weakly forced situation where models tend to have a difficult time. We can go on to the next slide, and if you can play this movie, this is now the exact same thing. The obs are the same, but now this is a 4-day forecast. So again, we'll have convection that begins to develop over Texas, and it's going to move toward the south and east. And you can see the members more or less have it, and they maintain the system. It's not as great a forecast as a 3-day forecast, but again, it's a 4-day forecast. So can you do it once more? Thanks. We can just look at it one more time. So if you want to accuse me of cherry picking, that would be fair. This was one of the forecasts where in 2023 where it really nailed it. They weren't always this good, but on the whole, the guidance from these models, I think was pretty impressive. So here's some stuff where I'm not cherry picking as much. Again, subjective comparisons. We'll have on the left is a forecast from MPAS, a probabilistic forecast. Its updraft helicity smoothed greater than 75 meters squared per second squared, but you can think of it as a probability of severe weather on the left. And the right is the corresponding forecast from SPC. So 5 days out, MPAS highlighted the Texas Panhandle for areas of severe weather. There's also an area over Florida and over Montana. 5 days out, SPC said the potential for severe weather was too low. As we go to 4 days, MPAS looks pretty darn similar. Didn't really change much, still highlighting the 3 areas. SPC saying predictability is too low. This is a slight upgrade from potential too low, but still they don't really know where to draw some contours. If we go to day 3, MPAS looks pretty similar, slight reduction of the probabilities, but highlighting the same 3 areas. SPC at this point just has general thunder, no severe weather threat. If we go to day 2, MPAS looks pretty similar. Now SPC has given us marginal risks in Florida, Texas Panhandle, and Montana. When we go to day 1, now SPC is upgraded to a slight risk over the Texas Panhandle. So I'll just go back and you can look at the MPAS stuff and see 5 days out, that's what it looked like. 4 days out, pretty similar. 3, pretty similar. 2, pretty similar. 1, pretty similar. And now the OBS, the verifying OBS on the right, well, we actually had severe weather over the Texas Panhandle. We had some over Florida, and even one little report in Montana. So I think this is a really cool example about the potential value of these medium range forecasts. And we saw time and time again that really MPAS did a great job highlighting those areas where severe weather did occur 3 or 4 or 5 days in advance. Here's another example. This one maybe not be as good in terms of the MPAS forecast, but this is from 2024. That last one was from 2023. 5 days out, SPC at a 15%. MPAS has fairly high probability, 70% in Nebraska. They don't extend as far south as SPC. We go ahead and look at the day 4 forecast. Now we are taking some probabilities further south into Texas, and SPC is really going for it, 30% on day 4. Day 3, SPC is just enhanced. MPAS looks pretty similar on day 3 and day 4. I also want to draw your attention to these lower probabilities over Georgia and Virginia and West Virginia. Nothing in SPC for this general area. Day 2, SPC is going to moderate. Things in MPAS look pretty similar. And day 1, SPC is pretty similar. MPAS is shifted a little bit to the south on day 1 and also highlights this area here where SPC is not highlighting. So if I go back, you can kind of see how MPAS evolves. I would say there's more evolution going from 5 to 4 to 3 to 2 to 1 in this forecast than in the previous one, but it still generally highlights these areas. And here's what actually happened. This was a big severe weather outbreak day where there was a lot of severe weather. I think we might like these probabilities to be a bit further to the east, but okay. And I think that these lower probabilities in Oklahoma are actually pretty much spot on because there was a lot of uncertainty about how severe weather that day would evolve in Oklahoma. And also, if you'll note, 3 days out, there was a signal of severe weather in this area, and there was, and SPC wasn't on that one. The severe weather over here was more weakly forced, and this was all strongly forced. So there is a forcing dependence, I think, in predictive skill. Okay, on to a bit of objective precipitation verification. I'm going to focus on precipitation over the CONUS, to the east of the Rockies, compared to stage 4 analyses. I'm going to show some aggregate statistics. First, just the precipitation climatology. So the y-axis is the total amount of precipitation over the verification region, just divided by the total number of grid points in the verification region. Forecast time is on the x-axis, going out every hour to 132 hours. It's from 2023. OBS are in black, the MPAS members in green. We can see the spin up from the coarse initial conditions, and we overshoot during this first diurnal cycle. But the peaks of precip are pretty good. Day 2, day 3, day 4, day 5. The valleys are also pretty darn good in the members. And there's a bit of a timing error where MPAS peaks about an hour or two too soon compared to observations. But on the whole, throughout this 5-day period, MPAS did a pretty good job of representing the climatology of precipitation. On to a measure of skill. The y-axis is the fraction skill score. Higher values are better. The x-axis is forecast time, and this is for 3-hour accumulated precipitation for the top 10% of events, top 5% of events, and top 2.5% of events. MPAS is in green, and this purple is a reference. This reference is NCEP's operational GEFs with about 25-kilometer horizontal grid spacing. So this is beginning to look at, do we have any value from running these convection-allowing ensemble forecasts out into medium ranges? Dots across the top are statistical significance markers. So if you see a dot, there's a statistically significant difference. So basically, the story is pretty simple. MPAS did better than GEFs throughout the entire period. You can see the green line is above the purple line. Lots of statistically significant differences. So this was, the purple curve is the GEFs with just 5 GEFs members that correspond to the 5 MPAS ensemble members. But for fun, we can run like a 30 or 40 member GEFs ensemble for the cost of a 5-member MPAS ensemble at these grid spacings. So what I've got shown here is the GEFs with 30 ensemble members in the dash line. And when you include those in the probabilistic verification, you do improve the scores. But still, MPAS basically outperforms a 30-member GEFs ensemble. And this bottom row is indications of statistical significance comparing the 5-member MPAS to the 30-member GEFs. And you can see there are lots of meaningful differences once we get out into days 3, 4, and 5. These are relatively low percentiles. If we look at heavier rainfall rates, now getting up to like an inch per 3 hours, same thing. MPAS in green, 5-member GEFs in purple. We clearly see MPAS is outperforming the operational GEFs for 5-member ensembles, lots of statistically significant differences. We throw on the 30-member GEFs just for fun. Again, we see that this 5-member MPAS ensemble is outperforming this 30-member GEFs for these heavier rainfall rates pretty clearly. So this was 2023. We're hot off the presses, some results from 2024 that just finished this past May. And there are some differences. Perhaps the easiest way to look at it is just look at the markers across the top. And you can see, so this first row is for the 5-member MPAS versus the 5-member GEFs, and the bottom row is for 5-member MPAS versus 30-member GEFs. At this relatively light rainfall rates, we are not seeing statistically significant differences past about 72 hours. And this dash purple curve is a 30-member GEFs, which is better than our 5-member MPAS forecast once we get past about 3 days. And we see that at the 90th percentile and as well at the 95th percentile. But right at about here, we see the MPAS curve dip below the 30-member GEFs, but it's still above the 5-member GEFs. But definitely fewer indications of statistically significant differences when it comes to the MPAS forecasts. We can look at heavier rainfall rates, and now we're seeing that MPAS is doing pretty well compared to both the 5 and the 30-member GEFs at these heavier rainfall rates. But indications of statistically significant differences are ending somewhere between hours 72 and 96. And this is in contrast to the 2023 results, where we saw statistically significant differences between MPAS and GEFs really extending throughout the 5 days. And so I think this is a pretty neat result. What I think is going on is you've got 2 very, very different seasons. 2023 was totally weird. 500 millibar heights in 2023 over the month of May looked like this. You had this ridge of high pressure over the CONUS with anomalously high heights. It basically didn't rain in May 2023. It was very weakly forced. Contrast that with what we just went through in 2024 in May, where we have broad troughing across the US. Anomalies aren't as strong, anything some anomalous troughing, and basically everything was strongly forced. And so what I think these results might be suggesting is that the value of these high resolution forecasts could be flow and regime dependent. In stronger forcing situations, if you're just simply asking, is it raining in the right place at the right time, which is what those fraction skill scores were measuring, you might not always have value of the high resolution models compared to coarser models. However, in more weakly forced situations, at least when it comes to precipitation, that may be where the value comes in from having a high resolution ensemble in medium range timeframes. So to conclude, I do think these medium range convection allowing ensembles might have value. I think there are big questions about what it would take for forecasters to trust the forecasts in the medium range and questions about how you operationalize it. But I will say, NCAR, we're not an operational center, and we pulled this off running it in real time 2 years in a row. So if we could do it, I mean, NCEP could totally do this if NCEP chose to. The MPAS convection allowing ensemble usually yielded more skillful 3-hour precipitation forecasts than the operational GEFs. But I think there's potentially more value during the weak forcing situations than strong forcing situations. And then finally, I'll conclude by saying that the fraction skill scores that I showed you based on precipitation, precip might not be really the metric that really tells us the most about whether we have value of these convection allowing ensemble forecasts in medium range. And so we need to look at other things. We need to look at things like storm mode and as well as severe weather surrogates. And that's kind of what I showed in the first half with those subjective examples, which to me clearly showed some value. So I think this is a pretty exciting area, and we'll look forward to continue to digging into some of these results. Thanks.
One sec, Cliff, you get time to ask a question.
Okay, great.
What's the runtime difference between a GAFS member and a MPAS member?
Oh, I have no idea what GEPS is, but I mean, I think we can, like, just based on number of grid points, I think you can run like 30 to 40 GEPS members for one of the, for 5 of the MPAS members. It's something like that. But I don't know the run times itself.
So you only ran convective allowing resolution over CONUS.
Yep.
How much better would your forecast, especially the longer periods, have been if you had run convection allowing globally?
Yeah,
allowing things to, it might have been even better yet, right? Maybe much better.
That would be cool. We want to do that sort of thing.
Hi, could you just be a little bit more specific when you make the distinction between weak and strong forcing? Are you only making the distinction between the amplitude of the forcing, or shouldn't it have a little bit more to do with the extent of the forcing, as in strong meaning broader synoptic scale type lift versus just unstable initiation of storms?
I mean, in 2023 and 2024, honestly, it was both. I mean, there were just no forcing anywhere over the lower 48 in terms of like coverage in 2023. In 2024, I mean, almost every system that came through was strongly synoptic force from like a QG perspective. Okay. So in this case, I would say both. We can quantify these things more rigorously, but I mean, just from looking at the weather, basically every day during these two, there was just tremendous differences in terms of forcing strength, okay. QG forcing.
Thank you.
Yeah.
Okay, thank you very much. So we're running out of time. Next, we are going to industry. We are going to the Weather Channel. Take it away. My bad, Weather Company.
All right, thank you very much. My name is James Cipriani. I'm going to be talking about the Weather Company's GRAF system and our migration to JEDI for cycle data assimilation. This was definitely a team effort. I cannot take all the credit, so my team members are listed there. A particular shout out to David Heaps, who's in the audience, and also our NCAR collaborators, specifically Chris Snyder and BJ Jung as well. And just a point of reference, anytime I say JEDI, it's obviously referring to MPAS-JEDI, so the MPAS bundle build. So quick overview, we're going to breeze through a couple of these pretty quickly. We'll talk about GRAF very briefly, and then data assimilation, our current data assimilation system, and then our transition to JEDI and our sort of target observation and schema, and then even potential AI implications for GRAF. So for those that are not aware, GRAF is the Global High Resolution Atmospheric Forecasting System. It is driven under the covers by the Model for Prediction Scales. Everything that's been done in this presentation, unless otherwise noted, is with GPU. So keep that in mind. We heard Jake Liu talk about GPU integration potentially with some forthcoming MPAS-JEDI work. We're sort of doing that kind of ahead of time, if you will. GRAF replaced what was known as RPM, which is based on WRF. We've since sort of unified our operations. We were previously running a 72-hour forecast every 6 hours and an hourly 15-hour forecast. We've since unified that. Every hour is now 72-hour forecast. So everything has to be completed within 1 hour, similar to HER and RAP, just with longer lead time. This is just a slide that shows all the products that we're producing. We're obviously going to focus on the teal boxes in the upper left, the cloud analysis and data assimilation. But this just kind of gives a sense of kind of everything that we're producing with GRAF. Quick word on how we evaluate GRAF. We typically look at precip and temperature. We do some wind speed verification as well. You can kind of see this
Precip on the left, temperature on the right, ETS for precip, RMS for temperature. About 4 years worth of statistics. You can kind of see the graph improvement in red over time relative to her with respect to precip, and then both with respect to her and NAM on the right. There is a spike. That is showing up here in about February, March 2022, where our scale degraded. That was due to a bug in the cloud fraction component of the Thomson microphysics, which was quickly resolved. So let's get right into data assimilation here. I think most of us are aware kind of what it is. It's basically optimally combining information from a background, which is a short-term forecast, with a variety of observations. Each of them has their own error associated with it. A lot of different techniques. Sorry about that. A lot of different techniques. We're going to focus primarily on 3D VAR for this presentation, but we will talk a little bit about some ensemble techniques. So you can kind of see if I just base the description of data assimilation off of the diagram in the upper right, it's basically error associated with forecasts, error associated with observations. DA combines the two. You have an analysis that's closer to reality, and you, in theory, get a better forecast, especially in the short term. So what does our current operational data assimilation system look like? It runs every hour, of course, as we have to initialize our forecast. It runs at 26 past the hour with a limited set of observations and spin up from our MPAS configuration. We assimilate surface observations plus minus 30 minutes. Of course, there's a background error covariance matrix, a static one that we've generated that's not shown here, but it's all based on GSI. So there's some interpolation that goes on because GSI is not meant to handle MPAS data. So we have to basically run it globally on a Gaussian grid. So we're going to lose a little bit of information there since our resolution is 15 and 4 kilometers with 4 kilometers over the CONUS and over Europe. So we're basically running GSI at 0.2 degree across the globe and assimilating the observations. It's still more skillful than a cold start forecast, but again, we're going to lose information with that interpolation. The very last component is a custom in-house cloud analysis where we're essentially perturbing the hydrometeors based on the WSR88D site-specific reflectivity as well. So this example is just showing some analysis increments from GSI using cell phone pressure data. This is strictly an example. We are not assimilating this in real time. And in fact, this mesh was a 15-kilometer uniform mesh. It is not the operational variable resolution mesh. But you can see that GSI has been doing the right thing, and it does the right thing with the observations that we are assimilating as well. And it's just kind of cool to see, the areas of highest increments corresponding to the highest populated areas, because that's where most of the cell phone pressures are coming in. So you can see that that impact on the surface pressure itself, and also on theta, as well as a cross section over CONUS, kind of up to 6 kilometers. So you can kind of see how the background error covariance matrix that we have, that's GSI specific, was sort of spreading that error information horizontally and vertically. Where we're going, obviously, is a fully cycled system. Right now, it's really just sort of a short-term spin up and then sort of data assimilation kind of every hour based on that spin up as input. But what we have experimented with is just cycling the cloud analysis component across the spin up period before we even start doing any other data assimilation. Because we found that we have some issues with convective initiation, especially in the spring and summer months, with just doing our sort of partially cycled system. So what you can kind of see here for these two examples, and I'll toggle back and forth, hopefully. Observations on the left, graph 1 hour forecast initialized 6Z on May 24th of last year. This is sort of what the operational system would show at 1 hour. And then what the system would show had we done the cloud analysis at every hour within the 6 hour spin up. So you can kind of see, even without any other assimilation, just including that cloud analysis as part of the overall cycling process, you can clearly see the benefit of that convective initiation. Similarly, another example, again, I'm just going to toggle back and forth here. It's just the forecast initialized 1 day apart. And this example is a 2 hour forecast instead of a 1 hour forecast. But again, you can kind of see the same kind of thing. So keep that in the back of your minds as we sort of talk about where we're headed. And this will be part of our overall workflow that it will incorporate JEDI. Speaking of JEDI, we will employ JEDI and its advanced techniques. The nice thing about it, among other things, is it operates directly on the native MPAS mesh, which we could not do with GSI. So our goal is to develop a rapidly updating hybrid ENVAR system. We heard a little bit about those capabilities from Jake Liu. And this will be partially driven by an in-house MPAS ensemble, which will be, the perturbations will be updated by an LETKF, number of members to be determined, resolution of the ensemble to be determined. But the hybrid capability will allow us to incorporate static error covariances along with the ensemble component from the LETKF or from the short-term forecasts perturbed by the LETKF, and that'll give us a higher resolution deterministic analysis that should give us a better forecast. Current work, well, this is just part of it, but because we're focused on 3D VAR and that's what's operational and we want to replace what's operational first, we've essentially generated 5 months of retrospective GRAF cold start forecast data 4 times a day out to 48 hours. This is data being used for the NMC method as part of the bump software of JEDI. And big shout out to NCAR, especially BJ Jung, for helping us to generate our custom error covariance matrix. The resolution of that data is 12 kilometer. Most studies with JEDI have been at much coarser resolution for variational components like 30 kilometer, 60 kilometer type thing. So we're looking to use the uniform 12 kilometer mesh. Still going to be coarser than our target mesh, but there'll be some sort of interpolation of the increments back to the 15.4 kilometer mesh. This is just showing a schematic of some of the components of JEDI. I won't get into too much detail other than to say a lot of it has been abstracted. It's meant to be sort of model agnostic. There are certain things that are model specific, especially when it comes to like the geometry of MPAS and things like that. But our overall progression is 3D VAR to ENVAR approaches, and of course incorporating the hybrid component as part of that. We plan to go operational with phase 1 of JEDI, sort of replacing what we have with GSI towards the end of the summer. We're going to be standing up a parallel environment of a cycled system coming up here within about a month or so to compare with GSI. So there's a lot of information on this slide, but I'm basically focusing on the B matrix initially here because that's been sort of the key component of the variational framework that we're targeting. These were images. This image was created by NCAR, by BJ Jung. It's basically sort of showing some of the control variables that M cubed had as part of their 60 kilometer 55 level B matrix, and then our 12 kilometer 50 level. It's probably worth noting our model top is at 40 kilometers, and M cubed is typically 30 kilometers for the testing. But the takeaway, it's hard to see. Most of these control variables are very similar. There was some initial issue with some very large length scales in the humidity field. We believe that was due to something in the bump parameterizations, we believe, because our data, an example you can see here in the right of specific humidity, there's really nothing going on at upper levels. So there really shouldn't have been those large length scales, but that's been accounted for. And these plots are really just showing some examples of derived velocity potential and stream function that had to be done offline because of the unstructured mesh of MPAS. And you can kind of see stream function down here as a vertical cross section across the globe as well. So things kind of look as they should is kind of the point. This slide's all words, but very important. This talk was not sponsored by the NCAR MPAS workflow, but I'm going to plug it here anyway, because there is a publicly available Git repository that assists with the running of MPAS-JEDI. And we were able to leverage that with some help from NCAR and sort of get all the components of our system working. We just kind of have to tie them all together now in a cycled state. But this workflow essentially allows for YAML configurations and kind of on-the-fly updating of those YAML files that can be very cumbersome at times in JEDI in general. So big shout out to NCAR for that. The workflow has, as I mentioned, kind of options and placeholders for all the configurations. That includes the variational, which also includes E and VAR techniques, EDA and LETKF, like we heard from Jake Liu earlier. We've done a lot of our own modifications, branching off of the workflow develop branch. We've incorporated, as I said, everything is being done with GPU MPAS as the forecast component. We're still using the MPAS library that's built with MPAS-JEDI for the geometry and so forth as part of the DA step. But the forecast components run on GPU, which is a significant speed up. Cloud analysis, we've incorporated our cloud analysis into the overall workflow, so we can cycle with that. Different initialization options and incorporating our own in-house observations and retrieving them on the fly, which are surface observations of potentially radiosondes as well. As we add more observations, we'll leverage other components of the workflow as well. Speaking of that, we have been able to run sort of 30-day experiments and some other canned test cases from NCAR with a host of other observations, GPSRO, using the ROPP 1D operator that we've incorporated, radiosondes, SATWINs, aircraft, AMSU-A, MHS, things like that. We've also tested our own near real-time surface assimilation using some more stringent QC parameters than GSI allowed for, and that's a shout out to the flexibility of the JEDI framework. So what do some of these results look like for, let's say, a canned 30-day experiment? The purpose of this slide is not necessarily to say, these results are the best that they can be, because this is, a 60-kilometer resolution mesh. It's 2018 test case. The point is the system was stable for 30 days using our version of GPU MPAS, again, for the 6-hour forecast component. So again, a 6-hour cycling every 30 days here. But you can kind of see just kind of regions of the globe, that show higher RMS scores, for example. So maybe regions we should focus on as an example. And that's just really broken down in these other plots as time series and then just sort of bin latitude regions as well for some of the surface variables. So the point is the system was stable. We've also done 30-kilometer testing. Those results are not shown here. We plan on doing more 12-kilometer testing once we can get all of the 12-kilometer modifications into the workflow. Speaking of 12-kilometer, this was just a single data assimilation case that NCAR set up and ran, and we were able to run and replicate it as well. But this was a fairly recent 0Z analysis case using our B matrix, so 12-kilometer B matrix, background at 12-kilometer as well. And you can kind of see 5 of the 6 plots show some of the observations that were simulated. We got AMSU-A, one of the channels, some surface obs, radiosondes, things like that. And you can kind of see the cost function. This is just showing that JEDI is doing the right thing. It's being minimized. 60 inner iterations per outer loop, 2 outer loops, I believe. So things, kind of look reasonable. No statistics here, just because it's just a single case. But the point is, we kind of have all of these components. We're ready to set up a parallel environment. The plan is to pass in our 15.4-kilometer mesh as the background, sort of run the DA at a slightly coarser resolution, and then those increments would be interpolated back under the covers by JEDI back to the 15.4-kilometer mesh. So this is just showing sort of our relative priority of observations that we want to incorporate after this sort of phase 1 deployment. The asterisk denote ones that we have in-house. So radiosondes, personal weather station, and cell phone pressures as well. But a lot of these are publicly available, like on the NCEP server, for example. The issue is that for our cycled system, which is going to be hourly, these are in the 6-hour chunks globally. So what we may end up doing in the short term is, with the hourly cycling, maybe leveraging some of the publicly available wrap buffer files. It would only be over North America, of course, but for the duration of cycling that we'll likely do initially, because of the limited observations, we would reinitialize, more frequently than, every couple of days anyway. So we might be able to get away with just starting with those files because they can be easily converted to formats that JEDI expects. the image on the left is from an ECMWF paper. A lot of people are probably familiar with it. It's forecast sensitivity to observations. And you can kind of see the relative priority of some of these observations. GPSRO is a huge positive impact as well. So we're hoping to incorporate that as one of the, one of the initial op types as well. This doesn't really apply to like ensemble-based techniques. It's really sort of variational. But it's a good starting place for, for our 3D VAR capability, moving into more ENVAR approaches. A lot going on here. But bottom line is it's sort of a two component system. We're going to be running an ensemble, again, at a resolution to be determined, number of members to be determined. Those will be updated by an LETKF with a host of observations. And that sort of ensemble will continue to run over time. Time is here in the teal boxes. The second component is really the deterministic piece, which will then incorporate the ensemble error covariance information. Again, those perturbations will be updated by the LETKF. That information comes into the ENVAR, but there's also a static component that comes in as well in purple. That gives us the hybrid. Out comes a high-res deterministic analysis, which can then be used to initialize every 72-hour forecast every hour. Yes, it's ambitious, but given all the flexibility with the workflow, GPU modifications incorporated, this is kind of our target, and we think we can do some good here. So what I didn't mention is sort of the initial approach would be to sort of incorporate the cloud analysis within that short spin-up period, along with the data assimilation coming in shortly after. I'm probably running low on time. I'll touch on AI really quick. Lot of work being done with AI. We've seen some ECMWF, work with the Error 5 data set being used for training. This seems like a sort of a logical next step, low-hanging fruit for GRAF. Sort of generate a GRAF reforecast, sort of a reanalysis, if you will. Have an AI model train, and then potentially initialize that AI model with an operational operational DA analysis. We're partnering with NVIDIA to do some of this work, and these last two slides just show some of what NVIDIA has been able to do with some of their training on the Error 5 alone. You can kind of see, I won't spend too much time here, but their forecast net system is able to capture tropical systems and atmospheric rivers and things like that out to several days, which is very encouraging. And this is the last slide, which is just showing some statistics of forecast net compared to IFS. Again, we're hoping to do something similar with GRAF. I think that's the hope, but there's lots going on, and probably more than I'm even aware of. I'm going to stop there, and maybe there's time for a question.
Unfortunately, you're a few minutes over already, so we'll have to leave the questions for the coffee or for the discussion later. Sorry, Tom. Next speaker, please. We're going back to.
Okay, I'm going to talk a little bit more about our MPAS ensemble forecasts from 2013. So I'll just focus on the forecast we ran a year ago. And this is collaborative work with Craig and Dave Ahievich and myself in M3. So what's been touched on already is how can we extend these forecasts and to produce potentially predictable forecasts beyond the first 2 days. We've looked a lot at the first 2 days. Now we're running forecasts into the medium range. We see the benefits of going to convection-allowing grid spacings, but does that hold up over longer lead times when presumably the predictability at some point will be reduced? And so what I have shown here on the bottom right portion of this slide is some of our machine learning forecasts for convective hazards from the HER. And this is showing the Breyer skill score. So higher is better from different HER initializations. And in general, you see this diurnal cycle of convective hazard skill. So convective hazards meaning forecasts of tornadoes, hailstorms, intense wind events. And this skill generally is decreasing with lead time. And so this is covering the first 2 days.
And we're kind of curious, well, what happens after that and what might we have to do to produce forecasts that still have scale beyond the first 2 days? So this is an open question. And now we have models like MPAS that can really provide the framework for providing global predictions on at convection-allowing grid spacings. So last year, in collaboration with the NOAA Hazardous Weather Testbed, we ran several sets of forecasts that I'll just summarize here in this table. This basically is similar to what Craig talked about. I'll point out a couple differences here, additional forecasts we ran that were deterministic. And so the row 2 and 3 there talk about deterministic configurations where we're initializing with the GFS. One of them is a global 15 to 3 kilometer mesh. The other one is a regional cutout. So this is one of the comparisons I'll be talking about in terms of quantifying the skill differences. The regional cutout is basically just MPAS regional with a 3 kilometer area that was cut out of the 15 to 3 kilometer mesh. And so that gives us an indication of what benefit you might have from running the rest of the globe with MPAS, or what skill is lost by potentially cutting out that area and not having that and just using the GFS for initial conditions. We also ran an FV3 ensemble, and I won't focus on those results. I think I have one slide showing some of the skill of those forecasts relative to the MPAS forecasts. So we had a pretty nice collection of days. We saw sort of the climatology that Craig showed of this season being somewhat weakly for us. So it'll be interesting to look at how these results change into this past year. But this was the physics configuration for the 2 sets of forecasts. So just the broader research questions, is it beneficial to run these beyond 1 or 2 days for convective hazard prediction? Now, I'm really just going to be focusing on that question. So predictions of where tornadoes will occur, hailstorms will occur. What is the limit to this? What is the limit to convective hazard predictability at these lead times? These forecasts went out to 5 days, so that's really all we can look at with the MPAS forecasts. And then we can look at some other questions, the deterministic, one of them being the global versus the regional MPAS version and the skill differences there, as well as some things we're actively pursuing, and I'm not going to show results on, comparing it to other sort of operational systems, and then potentially applying machine learning to these forecasts. And also we're running these 5-day forecasts every day, so we can actually look at time lagging as well. And so this is the configuration we have, the 15 to 3 kilometer cell spacing across North America. And I'll mention the regional cutout here. Basically, we just took this 3 kilometer region, and it has about 40% of the cells. So it obviously runs faster, and we'll compare some quantitative results between those 2 deterministic forecasts initialized with GFS initial conditions, with the regional providing boundary conditions provided by the GFS. So just some technical problems that we encountered when running these regional forecasts. There were some failures that were encountered, especially along the cutout edge, mainly located points in the stratosphere. So we were using MPAS version 7.3. In version 8, there were some changes added into the relaxation zone filters that could potentially have avoided these model failures. The one thing that we did to run these was to turn on an absorbing layer for the top 3 model levels. And this is just flipping a switch. We wanted to keep these regional runs as similar in configuration to the global runs. So we didn't want to make any significant changes. So we basically just flipped this switch in the name list to do that. And that provided some more stability and allowed some of these regional forecasts to run. And again, mainly these issues were located in the kind of large updraft values in the stratosphere. So this is just an example of some of the forecasts from the MPAS ensemble for this 5-day period. So I'm going to focus on updraft helicity. This is our diagnostic that we use that is pretty much the most skillful diagnostic we have for anticipating where convective hazards will occur on a particular day. Here I'm just showing for the same valid period. This is valid from 12Z 11 May through 12Z 12 May last year, showing sort of the ensemble max. So just the entire envelope, if you look at all 5 ensemble members, put their forecasts of updraft helicity together, and this is what you get. And you can see as we get closer to the event, these forecasts tend to converge. So the area where the MPAS forecasts were producing large values of updraft helicity basically converges on two different areas. And then by day one, they're pretty constrained to those two areas. And we can basically smooth those forecasts. So this is getting into the evaluation part here, where we can take those individual member UH forecasts using a UH threshold and then smooth them to produce a forecast that we can then compare to severe weather reports. And if we look at these forecasts, like Craig did in his presentation, we can also compare to the SPC and see there's often correspondence in terms of where the MPAS forecasts are predicting severe weather and where the operational forecasts are predicting severe weather. So from an evaluation perspective, again, we're going to use this updraft helicity diagnostic and compare it to storm reports. So on the left is our field that we started with the UH field and then smoothed it. We have to apply a smoothing length scale, basically, and we can look at different smoothing length scales and evaluate the predictability of the forecasts across those different length scales. And then on the right, we have just a gridded field of observations of severe weather reports. This is basically at any point during that 24-hour period where a severe weather report was observed. So a tornado report, hail report, or a wind report. We can compare these two forecasts, the forecast and the observations, with the Breyer skill score, which is just going to compare the left and the right. The Breyer skill score, these are both skill scores. So basically anything above 0 is skillful compared to the reference forecast. And then the second one is the fraction skill score, where we take this observation field on the right and smooth it. And we can look at successively larger smoothing length scales to get a sense of what scales there is predictability in the forecasts. So for the fraction skill score, while there's still skill where the fraction skill score is greater than 0, we typically look at this threshold of 0.5, and that's deemed to be a useful forecast. So I'm going to start with this plot here showing the fraction skill score for different lead times for these MPAS forecasts. And on the horizontal axis, here's our length scale. So as you go from left to right, these forecasts become smoother. And a side effect of that is the probability magnitudes tend to decrease. They get smoothed out in space. And then in the vertical axis is the fraction skill score value. So we're really looking at where these are useful forecasts greater than 0.5. And you can see not only do the forecasts get more skillful with length scale as going from left to right, but the forecast at lead times, longer lead times, basically decrease in skill with the fraction skill score. So that's telling us that obviously the lead time, it has a strong dependence on predictability. We can see that at the smallest length scales, actually all day 1 through 5 forecasts as assessed by the fraction skill score aren't useful. So some of those small scale features, basically the predictability is lost fairly quickly in the forecast. And so here I have these blue dots that indicate at what length scales are the forecasts skillful. So on the left here, there's a blue dot at around 40 kilometers. That means for the day 1 forecasts, the minimum useful scale for these forecasts is around that length, 40 kilometers in the forecast. And that gradually increases with lead time. So we can look at this other metric, the Breyer skill score as well. So it's the same kind of plot. Now we're just looking for the Breyer skill score. What you'll notice here is it's taking into account the smoothing in the forecasts. So if you smooth the forecast at these long length scales, the forecast becomes somewhat less usable. The probability magnitudes decrease. It's smoothed out over a much larger area. So it is factoring that in here. And so you can see sort of an optimal length scale here where the blue dots for the blue dot there for the day 1 forecast where the Breyer skill score is maximized is sort of this optimal combination of smoothing, and then that actually increases. And so that's telling us something about the length scale, the predictability length scales as well. So this is actually just depicting some of that, where basically, if we look at the smallest smoothing length scales, we're seeing that you have this probability distribution that then becomes reduced at the larger length scale. So the Breyer skill score is one way we can look at this and basically have a sense of how much the smoothing impacts the forecast, and it's the skill relative to climatology. Okay, so this is a slightly different comparison. So now we're looking at everything relative to the MPAS ensemble. So the blue line is 0, the MPAS ensemble, and then we have a few different configurations of forecasts here. We have in orange, this deterministic GFS initialized forecast. The red is this regional forecast, that regional cutout. And then we have a few FV3 forecasts that we ran, as well as the operational HER. And so there's some interesting differences here. In general, we see, number one, the deterministic forecasts are just not as skillful as the ensemble forecasts. The GFS forecast initialized with MPAS, that 15:3 deterministic forecast, and the regional forecast are slightly worse than the operational HER for this, although the differences aren't huge for the fraction skill score here. In the FV3 forecasts, they're among the worst of the bunch in terms of the forecast skill, and they're sort of clustered together. We have a 5-member to compare to the MPAS ensemble forecasts. And obviously these differences are kind of a function of length scale. So at different scales, you can see as you're going to larger scales, these lines tend to converge, meaning the forecasts are all producing pretty similar forecasts on the larger scales, and the differences are maximized at the small scales. Okay, so this is a somewhat curious result that we're still sort of untangling. The regional forecasts, the regional MPAS cutout, we actually had pretty similar skill, and in some cases at slightly longer lead times, had better forecast skill than the global 15 to 3 kilometer forecasts. Now these differences are fairly small, but you can see as you go from day 1 in blue to day 2 in orange, day 3 in green, those differences, especially at the medium and large scales, tend to increase such that those regional forecasts has a slightly larger benefit with time. And so we're trying to untangle this. We're looking at some different fields. Obviously, again, we're just looking at the surrogate severe approach in terms of where UH sort of corresponds with convective hazards. We've started to look at precipitation fields for these two sets of forecasts to better understand these differences. And the precipitation forecasts are a little mixed in terms of whether the regional versus this full globe 15 to 3 are better or worse. So for this specific evaluation, we do see that the regional forecasts are slightly better than the 15 to 3. And so this is actually just a complete curiosity slide in terms of we initially ran all our forecasts on Cheyenne, and then the supercomputer change happened. And so we just happened to have 2 supercomputers up at the same time, and we ran all these regional forecasts on both systems just to see what the impact would be. Obviously, there's differences in compilers, differences in configurations of nodes and processor counts, things like that. But we were kind of happy to see the forecast differences were very small. There's not really a signal that emerges here. They're somewhat random, day 1 and 2. If you look here, there's not like an increase of error that seems to be basically just randomly associated with initial conditions on a given day and the different supercomputer configurations. But for this evaluation, the fraction skill scores were only different by 0.01 to 0.02. Okay, so I'm going to close here just with some caveats of these results. This is, again, just looking at convective hazard verification using storm reports for ground truth. We're really looking at kind of rare extreme events here. So if you think of the base rate of these events, it's only happening, say, 1% of the domain, 1 to 2% on that order. And so we're not even looking at things like, precipitation and other sorts of fields for these forecasts, which have larger base rates. Craig has looked at some of that. And so predictability of more common events may be different amongst these forecasts. Again, we're defining predictability in a very specific way, an event occurring within 24 hours, within a 24-hour period. I think we're starting to dig in terms of how this predictability varies on different time scales. Obviously, spatial scales is important, which is what I've shown today. And that sort of ties into how the forecast guidance should be presented. Obviously, if we have a sense of the predictability of these features, we can come up with guidance products that are tied to that predictability in terms of how to present this on different time and space scales. And this is just using one diagnostic from the model. Admittedly, it's a pretty useful diagnostic, but we've, for the last 5 years, have been using machine learning techniques to post-process these convection-allowing model forecasts. In pretty much all cases, they have significantly better skill than just using one diagnostic for a variety of reasons. And so assessing predictability, that's probably the best way to do so in terms of having a forecast that really is the kind of the best possible forecast for predicting some of these convective hazards from the convection-allowing model output. So a summary, we have these forecasts, they're skillful, they're better than climatology out to day 5. The spatial scale obviously increases in terms of how you would use this information and where there is skill. For days 1 to 3, amongst the different types of configurations and models we looked at, the MPAS Ensemble forecasts were the best. The regional forecasts were slightly better than the global 15 to 3, and we're still looking into that. And we're generating some machine learning based convective hazard forecasts for days 1 to 5, which we were testing this past spring. And this is an example on the right-hand side showing some of these forecasts. And I think there's a lot of utility in these, and we'll be continuing to generate some of these forecasts for the next couple of years. Thank you. I'll take any questions.
We have time for one question. It's quiet in the back, so I assume we have nothing online.
Thank you for running a big set of jobs on 2 different machines to see the difference. You've now excused the rest of us from having to do that.
Thanks.
And thank you for staying on time. Our last speaker of the session between us and coffee from the Central Weather Administration in Taiwan. Take it away.
Okay, hi everyone, and my name is In Zhang from Central Weather Administration in Taiwan. And today I would like to introduce the current progress of implementing the MPAS regional model in the CWA. And in CWA, we already used the WRF as a regional operation model for 10 years. And the last year, we let the highest resolution into the 1 kilometer. And also, we want to evaluate an MPAS system as another regional model system. So we want to propose there's a 10 to 1 kilometer variable resolution mass in the future. They want to explore new things like MPAS-JEDI. And before that, we would regard the MPAS as new regional model system. So there are different aspects for regional model assessment. For example, the lateral boundary. As everyone knows that MPAS can have the operator coverage of the lateral boundary. You can cellular or elliptical or polygons. So we would like to know the different coverage of the lateral boundary, how they affect the forecast scale of the regional model. And the other things, the resolution transition zone, like the nesting boundary or variable mesh in WRF and MPAS respectively. But this is the future world. So today I will introduce the lateral boundary testing of the MPAS. And before that, the WRF model is actually the operation model in CWA. So we would like to compare to the MPAS model. So we will find out actually the MPAS current situation, they have the limited package of the physics suite. For example, in the black box means that the current use in CWA WRF physical selection. We use the cumulus scheme with the Cambridge and microphysics scheme. There's a TCWA1 only used in Taiwan. And another sense is NOAA WSU. This is also in the MPAS, so that's not a problem. So the problem is the microphysics scheme we use in Taiwan is not applicable in the MPAS. So one of my work is implementing the TCWA1. This microphysics scheme is based on the GADA scheme and tuning according to the characteristic of the rainfall pattern in Taiwan. So with this work, we can have the similar physical option compared with the MPAS and WRF. So we are conducting a different experiment of different coverage of the regional model and in MPAS, and also compared to WRF model.
And all the experiments were conducted in the 50-kilometer resolution. So the first one is the WD01, means the Wolf domain 1. And this physics package using the operational setting in the CAA. And the second one is the It's WD01 Cambridge 1. D is the similar setting with the Cambridge as the previous, but the Cambridge setting is similar to the MPAS Cambridge. And the third one is the MPAS model. So the MPAS model with the similar coverage with the Wolf model. And the fourth one is similar to the previous one, but we have the obtuse angle with 4 corners. And another thing that we try to use the elliptical coverage of the MPAS regional model. And the last one, this is an experiment without the Tibetan plateau. In our operational experiments, we sometimes encounter the CF condition in the operational model. And also, usually they will have the blowout in this area. So we would like to try that if we have the regional model without this plateau, what's the effect of the regional model forecast capability? And also, we also do the global simulation of the MPAS. And all the experiment will calculate the bias and Riemann square error at this intercept area for all experiment, roughly. If you process it like this polygons. Okay. So this is the 50 kilometers resolution. So only choose the winter case and the typhoon case for the evaluation. So we choose the 3 typhoon in the 2023, and Mawa, Sola, and Haikui. And Mawa and Sola is the stronger intensity typhoon with the category 5 and 4 respectively. We can find that there's a track clustering between the Wolf and MPAS in the stronger typhoon intensity cases. And you can find that the MPAS have the northerly drifting component compared to the Wolf simulation track. In the Solar, they also have this north drifting component. And in Haikui, this is the medium intensity typhoon. So the clustering actually is dependent on the Cambridge setting. So there's a Cambridge setting. It doesn't depend on the model between the MPAS and Wolf. And for the typhoon prediction intensity, all the MPAS model have the stronger intensity compared to the Wolf. And we also look about the Mawa simulation. The Mawa, actually the backtrack is a curved trajectory. And we can see that after 5-day forecast, the orange one is elliptical boundary. For the MPAS, they have the smallest track error. And we further look at the time of different time snapshot, we can see that the elliptical regional model in typhoon have the faster moving speed compared to the rectangular like a Wolf model domain for the MPAS. It's corresponding to the faster retreating of subtropical high in the elliptical experiment. And also we conduct the experiment in the winter case in the late 2022 and 23. And there will be about 60 cases in total. And we use the NCAP data, and our methodology is to use the forecast time minus subtract the corresponding initial time. As everyone knows, the MPAS vertical level of the model is constant. So you can directly subtract this value and get the error of the model errors. So you only can, this is a very convenient way. So you only use the NCDF and CDO for calculating the raw data. So this is a synoptic analysis for 65 case. And the Wolf model, actually the vertical pattern of the arrow is similar, but didn't show on this graph. And you can see that we do the variable for the all pressure arrow and the theta and the wind speed. We can see in the middle of the row that in the theta, the Cambridge global have the large bias in the upper level atmosphere. And we additionally have another experiment, change the cumulus skin to nucleated skin. They can have much more improvement. And also look at the Riemann square arrow at the bottom row. You can see that actually the regional model, all the regional model have the smaller error in pressure and theta variables for all the experiments, which represent the benefit for the regional model. So we take a closer look about the pressure error at the upper atmosphere. That you can see that different experiments have the negative bias at the downstream out plateau, like red box represent. So we will now see that you can see the elliptical experiment and the experiment without the plateau have the different pattern of the negative bias. And this is the 5-day forecast error. So we want to see the evolution of this pressure error. So we have the time screen of pressure error analysis. We want to know that these pressure errors are from the lateral boundary condition or the model error. You can see that actually this pressure bias along the downstream of the Tibetan plateau actually is original for the Tibetan plateau, not from the LBC. And the experiment without the plateau, we can see that the pressure error actually is located at the Pacific Ocean and didn't transport to the eastward. If we subtract these two experiments, we can see that there's a negative pressure bias originating from the downstream at Tibetan plateau and propagate eastward as time goes by. And also the upper level wind field also corresponds in this statement that there's a cyclonic circulation. So this experiment, the subtract of elliptical and elliptical without the Tibetan plateau will represent the effect of regional model if they count including the plateau. So actually the experiment that contain the plateau may induce a cyclonic wind flow and also the negative pressure bias in the regional model. And also in the winter case, we do the surface data as validation. And the temperature and the missing ratio performance actually is no significant difference between the WRF and MPAS. But while you see the wind speed, there are significant difference because we found that MPAS actually didn't have the topo wind option. So another work is we implement the topo wind option too in the MPAS. And the figures show that the solid line means the topo wind is applied. And the dashed line means the topo wind without the topo wind experiment. And the blue line means the MPAS model, and red line means the WRF model. So actually they have the similar patterns. And on the right, there's the C topo variable that's using for calculate the topo wind. You can see that there's a little bit different just because the MPAS will calculate the variance internally compared to the WRF will use the static data. And another thing that we would like to propose the 10 to 1 kilometer mesh generation. So actually public mesh is not available. So we are doing the mesh generation by ourselves. And we find out that it's very time consuming. So we joined to the workshop held by the NVIDIA and NCHC and try to let the code to parallel on the GPU. And I briefly introduce some procedure of the mesh generation. The mesh generation will compose on 2 Verdonic computation and central computation. And this is the time for each iteration for each subroutine. So actually the Verdonic computation will cost a 0.15 and centroid computation actually already writing in OpenMP. So that is parallelized by the CPU. So we try to let this OpenMP into the OpenACC have the 8-fold faster in this section. And then we also try to speed up the Verdonic computation. And the Verdonic computation use the strict path in the Fortune 7.7 version. So we try to upgrade to Fortune 19. And there's still also have some improvement. And also we use the NVIDIA profiler to know where's the bottleneck. There's a CR-less subroutine in the strict path, there's a bottleneck, and we let them into the OpenACC. So they are more faster than before. And you have to mention that there's the TR mesh that will call every once for 10 times. So that will be not a problem. So in the end, we use the GPU for A100s from the NVIDIA, and we have the 6-fold faster than the CPU running. Okay, that's all I have. Thank you.
We have some time for questions. Anything online? In that case, thank you for making up the time that we lost during the beginning of the session. We're exactly on time for coffee. There's 2 more talks in this session after the coffee break, and then we'll go into our discussion.
No, he was busy. He just got. Well, welcome back, everybody, from the break. We've got 1 more session here with 2 talks and a discussion period to get us to the reception at 5. So that doesn't mean we should rush through, because we're not going to get anything till 5. So we've got that whole time. It's not like if we quit at 4:30 that it's going to be ready for us. So it's going to be 5. First up is Curtis Alexander from across town is going to talk to us about the MPAS work, development work that they're doing over there.
All right, thanks for the opportunity to walk through some of the activities that GSL is taking on and with engagement of MPAS. I obviously want to acknowledge the myriad of collaborators, so many I can't easily name them all here in GSL, NOAA, and our collaborators at UXarray with JCSDA and NSF NCAR. So I'm the messenger, so you can shoot me if you want on what I communicate, but this all the work, and I'm going to highlight here, is certainly done by other staff in the lab and elsewhere. Let's see. Advance. There we go. There's sort of 3 tiers of GSL development activity going on with MPAS. I've binned it into global, sort of regional convection allowing, and then convection resolving research work. The efforts we're looking at globally are deploying some meshes. We want to push that boundary ultimately to a global CAM, but we've started off with a 7.5 kilometer global mesh, just to start so to speak, get our feet wet running MPAS over that domain, doing some resource estimation. We're actually able to pull off a forecast for 20 AWS cloud instances, 2.5 hours to run a 48-hour forecast. But we're also looking at other aspects of our physics development with atmospheric river prediction, other related sensible weather elements. And then on the regional side, looking at some of the limited area configurations for MPAS. Obviously, NSSL's been producing some forecasts really the last 18 plus months now with a MPAS run at 3 kilometers over CONUS. But we've been complementing that recently with some additional MPAS configurations, looking at resolution sensitivity, adjusting the mesh size away from 3 kilometers, as well as looking at some ensemble design 3 kilometers. And I think some of these are touched upon in Adam's presentation earlier. I'll touch upon them again a little bit. And then also looking again at physics development across a variety of applications, whether it be over CONUS or the Atlantic Basin, for a variety of, again, sensible weather applications, including hurricane prediction. So a lot of different scales of work that we're focusing on. And another is pushing us down to 1 kilometer spacing or even less, looking at some extreme precipitation estimation, as well as fire weather prediction for urban scale applications. Within the specifics of the GSL physics development, we're focusing on a particular physics suite that involves Thomson microphysics that's aerosol aware, GF convection, MYN, PBL, surface layer, and RUC LSM. But we have this new version of these physics that we're looking at with a MPAS configuration run over CONUS. For lack of a better descriptor, we call it HER version 5. It's just newer physics than what the operational HER's running with. And again, starting to do some experiments and evaluation of the performance of the physics, generally speaking, initialized from either the RAP or in other cases, the GFS.
I will point to the talk that's going to follow mine on more details here for our physics development, as well as for that's from Joe Olson, and then tomorrow from George Grell on some of the GF parameterization work. We did already experience a couple challenges with the evaluation of this performance of this physics suite, and some of these were quickly fixed in the last couple of weeks, adjusting the acoustic time stepping, so to speak, for more stability. I did identify a problem with the albedo information that we had generated in this configuration. There's also a lag in the shortwave radiation that we've noticed. We had a problem with opacity of clouds, as well as a moist bias that was noted. And so we worked through some of these issues in short order with the physics developers to improve the, again, the albedo formulation and the static file data. So we also, again, noted this lag in the shortwave radiation updates. That's a capability that was in WRF that we want to get into MPAS to reduce that offset in the timing of the solar radiation updates. We also dealt again with some default settings, again with the opacity of clouds on the effective radii from the microphysics. So we've adjusted the default value for that to be true, and wanting that obviously to be carried forward with the MPAS versions and configurations. And then finally, the moist bias was some tuning of the land surface model. There was an overestimation of direct soil evaporation and some irrigation effects. And so work was done on this to some extent to reduce this moist bias that was noted in the 2-meter dew point forecast verification in particular. But again, just sort of starting to get familiar with the physics behavior of the MPAS at CAM scale. And so again, we made some adjustments to these physics configuration components, again, reducing the moist bias as shown here through a couple of different variables. Soil moisture reduced in the west, 2-meter water vapor mixing ratio, also lowered again from some of the changes in the RUC LSM, and the latent heat flux adjusted downward as well in some of those same areas. So beyond just the physics development that continues to happen, we've obviously been demonstrating some of these configurations, again, in collaboration with NSSL and some of the NOAA's testbed experiments, whether that be those various 3 configurations that have been run for, like I said, 18 plus months now. We're also looking at the updated physics in the context of other testbed experiment activities coming up, the flash flood intense rainfall that's underway, as well as the upcoming hurricane forecast improvement, or HFIP experiment. So potentially deploying these MPAS configurations to look at the performance in these other contexts. So again, we're initializing principally these configurations from the RAP or the GFS, but largely to scrutinize the physics development that's going on there. I do want to mention back on the testbed experiments, again, we were looking at a couple different aspects of MPAS this spring, one of which was the grid resolution or the mesh spacing sensitivity to convective forecasts. We were able to run both a 4 and a 3 kilometer forecast. We couldn't get the 2 kilometer configuration running yet, but it's something on the to-do list to resolve so that we can sort of see the MPAS sensitivity there. And we're seeing some pretty encouraging results where I think we're getting a lot of the same level of detail and information content closer to 4 kilometers when you compare it to the 3 kilometer solution. So that does give us some potential options down the road for when you consider compute resource needs for an MPAS type configuration. So that was one of the, again, evaluation activities in the testbed experiment. Another was the MPAS Ensemble work, where we built out a MPAS Ensemble of 5+ members. Here I'm just highlighting the comparison of the severe weather probabilities between the MPAS Ensemble and the operational baseline HREF, and the severe weather reports for 2 particular days. Again, I think as was noted earlier, the MPAS severe probabilities tended to be a bit lower than the other ensemble configurations, but again, there's a difference in the climatology of things like the UH diagnostic that I think needs to be addressed in MPAS. So I think that may bridge some of the difference between the performance we were seeing in the MPAS Ensemble this spring and the other ensemble configurations. But the overall envelope was certainly there in terms of capturing the severe weather events, just again shown in these 2 particular cases. Let me switch gears over to data assimilation quickly. We are working pretty closely with EMC and JCSDA, other partners, on standing down basically a GSI and basically adopting JEDI for our data assimilation framework. There's a lot of work that's been going on here recently, already now involved in a lot of the PRs that are getting submitted and reviewed for MPAS-JEDI, as well as the FE3 JEDI interface capabilities for the DA. So we've got a pretty good, I guess, momentum started on this front with the JEDI development. We've set up a sandbox with MPAS. Basically, it's a 12-kilometer domain and 30 Ensemble members for some preliminary tests over CONUS. Again, this is computationally cheap, but it lets us get the JEDI's fundamentals in place, observation operators, amongst other things, to get that all tested and vetted in a JEDI MPAS framework. Just a few examples of single ob tests. This is a one radio sun looking at the increments from the surface up through various model levels for temperature, adjusting the localization radius in the vertical and the horizontal, testing those impacts in JEDI with MPAS. Another thing we looked at is, again, the observation or O-B values, the sanity check of what this looks like spatially over the US. There's some larger differences near the coastlines, and this is often due to the fact that those coastlines act as either a water or a land point, depending on the prevailing wind direction. And that's a capability we have in GSI that we want to bring into JEDI to be able to handle some of those type of scenario-specific information when we do the O-B calculations. Another thing we're working on is, again, ensuring the observation format compatibility with JEDI, getting everything over from buffer to YOTA format. And so that's another effort in collaboration with EMC to make that happen. And then finally, generating some MPAS-specific model background error information using the 3D ENVAR framework to do that. But we need to get this regional static background error formulated. So we have some collaborations with NCAR on that front. And again, we'll be working with JCSDA to bring that into the JEDI software infrastructure. So the last thing I want to talk about is the integration of MPAS into UFS. Obviously, NOAA has an interest in furthering its unified forecast system as a simplification of the forecasting applications in the operational production suite. And to that end, one of the aspects of the UFS that we want to continue to enhance is this flexibility, again, of the underlying components that can be in the UFS framework. JEDI is already going to be an example of that in terms of the flexibility of the different data assimilation algorithms you can apply for different problems. We have CCPP as an enabling technology for interface of different physics suites with potentially different dynamic cores. And again, bringing MPAS into the UFS infrastructure is front and center for us now, given, again, what we want to go with convective-allowing modeling application needs. So I'll point you to a poster by Lisa Bernardet that's going to be talking a lot more about this in detail. I'll just hit some highlights here. And this is really coming out from a Tiger team that was assembled about 6 months ago to try to do some estimation of the work involved in bringing MPAS into the UFS. So there's a couple of steps that are going to need to happen here, including generalizing the atmospheric component from FE3 ATM to UFS ATM. This is going to be an opportunity to basically enhance both the maintainability of FE3, but also facilitate introduction of a new dicore like MPAS. So there's some abstraction and generalization that needs to happen in that coupling interface. And so that's one of the areas of work that are needing to happen. And the vision would be to have MPAS as a submodule under the UFS weather model. The code could point directly to the MPAS official repository, but that the interface itself would stay under the weather model atmospheric repo. Obviously, this is parallels to the CESM paradigm that was talked about earlier today. And obviously, there are technical challenges that have to still be worked through on this front, but I think this is the vision for how to bring this in. In terms of some of the other boxes to check, pre-processing, on that front, I think we're in pretty good shape with MPAS already. There's probably not a lot of work on that front to bring that into the UFS infrastructure. Same with the data assimilation. I've already talked about some of the DA work there with JEDI. There's already existing interface with both FE3 and MPAS on the native grid. So I think that that aspect of integration in the UFS framework is also relatively low. In terms of bringing in things like stochastic physics, there's some work going on here. DTC is helping further some of this effort to bring in some of these schemes for stochastic physics, the ad hoc schemes, into the MPAS standalone. But obviously, if we get to a point of having the physics dynamics coupling with CCPP in place, that enables these same stochastic options through that framework. There's some other stochastic techniques that also could be revisited with the MPAS on the structured grid. I'm not going to go into the details now. Cellular automata is one of those, but I'll save that for another day. One of the other aspects is the intercomponent coupling, where we can leverage the NOAA cap for basically being the wrapper and the entry point for these different Earth system components, if you will, to allow for that interoperability within MPAS. So again, some of this functionality already exists, again, using CSM as an example for that. But this is another step of the way to getting MPAS into UFS. There is some more detail, again, on the physics dynamics coupling itself with CCPP, but I'm going to save my time and let you talk to Alicia more specifically about that. The other last few aspects are MPAS-IO that we need to look at for production of output on the native grid, and some of the utilities that can be involved for interpolation to lat-long grids, and whether we want to have asynchronous IO, basically a right grid component capability is another factor. Post-processing, we've already heard more about that earlier today. Using the unified post-processor, there's an MPASSIT tool to help post-process the MPAS output. We think we can integrate into the authoritative UPP code those capabilities that we need from MPASSIT. But there's certainly other aspects of the post-processing that we want to consider, whether we also want to run it inline in MPAS with a right grid component. And then finally, the workflow. Obviously, there's ways in which we can run the whole system end to end with the various components with MPAS and the DA. Obviously, we want to have a generalized framework where we can here, rather than basically having to, individual approach for each application. So basically, we want to start from a regional workflow if we can, and then branch from that for MPAS and manage the differences there, rather than, again, having, workflows specific to each individual application be developed separately. And so we're going to be using unified workflow tools to demonstrate some of this with some of the GSL runs that I alluded to. Also refer you to the poster about this topic on the unified workflow tools. So finally, resource estimation for bringing MPAS into UFS. This Tiger team came up with about 13 FTE effort to estimate the amount of work to do all of the steps I just talked about, minus the CCPP, which is listed here. I just didn't have time to go into the details there. So we're working on a plan, again, within NOAA to figure out the resourcing for this in terms of funding and all of that. But I think that's the key thing in terms of getting MPAS into UFS. So in summary, GSL is getting heavily involved in a lot of different aspects of MPAS from a variety of applications and scales, including the data simulation, physics development, and infrastructure work. We have a lot of interest in a variety of different mesh generating aspects of MPAS for different areas and resolutions, variable resolution, and even discontinuous grid applications. So that's my summary. I guess if I could also summarize the fact that I know GSL has been heavily involved in some other aspects of UFS the last couple of years, but I think really in the last 6 to 12 months, we've picked up speed and steam with MPAS development and engagement. I will say, finally, we're committed to getting MPAS tested for a future UFS-based RFS. If you want more information about where we're at, status update, timing, schedule there, I will point you, shameless plug, to the upcoming UFS Epic workshop in late July, where registration is still open and you can participate in and learn more about activities, including an MPAS session at that workshop.
Thank you, Curtis. There's a lot there. This is going to be this material will be part of the discussion session a little later. So, but if anyone wants to ask a quick question on something put up there, does anyone have anything that they are is really burning?
Technical question that is not going later. So if you talk about the interface to the physics, there's that you said that there was still some UFS stuff, no, FE3 stuff embedded in what UFS is doing right now. Would that also require messing with upgrading the numerics in how the physics and the dynamics are integrated together?
Yes.
Thank you.
Okay, thank you again. Thank you. The last talk in this session for the discussion, we've got Joe Olson's going to talk to us about physical parameterizations.
All right, thanks. I'd like to thank my co-authors for their work on this, especially for the past 3-4 months. We really just started working with MPAS, just downloaded code about 4 months ago. So I'm just going to overview some recent developments and some of the parameterizations that we develop at GSL that are being implemented into MPAS, as well as some of the systems we've set up to initiate our testing. As you can see, we're still using WRF and MPAS at a variety of different scales. We haven't fully gone to global yet. But another sub-theme of this talk is really our move to sub-module repositories as well. So this is just an overview of the different suites we develop at GSL for each of the model components. We're trying to get all of these into MPAS, all of them updated right now. I'm going to go over some of these in the subsequent slides. I think the take-home points here is that we still do plan to switch to NOAA MP for Rufus V2, and we also plan to switch to RTMGP, but we have not started testing that at all yet. So first of all, the MYNN updates, it's been fully universalized now for all MPAS misspelled, WRF, and CCPP. One scheme works in all of them, and it's been fully refactored. It's now only a K-only scheme that sped things up quite a bit. Now as a new driver, and this driver can almost the same thing, can work in both WRF and MPAS now. Since it's a K-only scheme, the I and J's are moved up into the driver level, and this is basically based off of Laura Fowler's version for 8.1. So not much has changed. It's just to fit the new K-only scheme. There's a new component here that's really more to help us with the global models, because it's a stratocumulus problem here. We're just linking the turbulence to the radiational cooling atop. We have a new 5 downdraft component here that's fully integrated to the TK equation. It helps us regulate the TK in the clouds and the overall cloud cover in the global perspective a lot better. Wayne will be talking a little bit about this tomorrow morning. And we've also begun revising the subgrid clouds, specifically for WRF and MPAS, because the different DICOR is going to have a different cloud climatology. So, and basically all the past few versions have been more or less tuned for FE3. So yeah, in summary, we have one scheme that can work in all of these different model hosts, but they're still only in our GSL repositories at this point. Tempo is basically the consolidated version of the Thompson-Eidhammer scheme. It's kind of been taken in a lot of different approaches. There's a lot of different versions out there. This brings it all back together. This is a work led by Anders Jensen. It's now already exists in a submodule repository that's linked to MPAS and CCPP now, and it brings in again all the options, the hail awareness, so on. Anders will talk more about this tomorrow. The Unified Gravity Wave Physics Scheme, this is something that's been developed in the FE3 framework for quite some time. It's slated for operational GFS version 17. It has all these 5 different components. And right now, what we have in WRF and what we've implemented in MPAS is just the version that carries the top, let's see if this works, just these top 4. We don't have the non-stationary gravity wave yet implemented in WRF or CCPP. That's basically our next step. I think that component is important for any type of seasonal forecasting. We'll work on that next, and that's also going to be moved to a submodule repository shortly. The GF convection scheme, it's also been primarily developed in FE3 over the past few years, but both global and regional applications. A lot has changed since the WRF version. It hasn't been updated in a while. So, but basically here's some specs for it up on top. A lot of it has been updated, the scale awareness, the scale adaptivity, the aerosol awareness. It is fully implemented for Rufus version 1. The C3 scheme is meant to be kind of a successor, but that's kind of a collaborative work with NOAA PSL and EMC to take kind of the best of what's in the SAS scheme and some new features from Lisa Bankston and PSL. Notable is prognostic area cloud fraction or prognostic area fraction. This is currently being evaluated though. So right now we've only implemented the GF version of this into MPAS for preliminary testing. It has this new downdraft component that we're also assessing at this point in time. This is also expected to be moved to a submodule repository, and at that point we'll be able to update the WRF version 2. So moving on to the system testing. Again, we've only started this effort a few months ago. And so as of right now, we just have 2 development runs. Curtis basically called this Dev1 HER-V5, basically the same thing. It has this HER physics in it. And we're also running a version with the GF convection scheme, and we intend to run another one with the NOAA MP as well, but that hasn't been started yet. These are all MPAS CONUS runs at 3 kilometers and cold started off the wrap. There's no DA yet. That's expected to be coming soon though. And again, these products are so new, we don't even have them fully connected to all components of our verification system yet. That said, we've started doing some tuning and debugging anyway. And this is one good example here. This is the diurnal composite over the last 11 days of our downward shortwave radiation bias at forecast hour 6. You can see the MPAS run. Diurnal composite tracks the wrap run pretty well. Not too surprisingly, it's initialized off the wrap, but it outperforms HER and Rufus pretty well and gives us an overall pretty good diurnal temperature bias, especially near 0 during the day. However, we are a little bit high bias at night. We think that's part to do with that moisture bias that Curtis talked about. We've improved it a lot, but it's still there. For example, this plot shows the dew point bias at forecast hour 1 for HER in red, RAP in gray, Rufus in blue, and then 3 different MPAS runs that are initialized off of each of these respectively. And they have the same color, but they're in dashed. You can see by hour 1, the MPAS runs are already, significantly more moist than the parent run. So we don't know what's causing this yet. We don't think it's the dye core. So we shouldn't call this an MPAS error. It's more likely a lingering problem in our physics implementation, maybe somewhere in the MPAS in the init stage too. We're not sure yet. But we consider this our top priority over the next couple of weeks to hammer this out, because this can have ramifications on the convective statistics and whatnot. So we're also still testing in WRF. This is partially because we have a lot of colleagues in DOE who want to test other components coupling to this in at least research mode, like WaveWatch 3, ocean models. But we have this system, this 3 and 1 kilometer nest set up. We're running daily forecasts in support of the Wind Forecast Improvement Project 3. It's an 18-month project that's centered over this area. We have a bunch of coastal stations with continuous profiling sites, 5 of them here on the islands and the coast, offshore buoys, barge and ships as well. So for Block Island, which is located about right here, and Nantucket, which is about right here, we're starting to get some stats rolling in. We have weekly weather discussions to go over the biases associated with this modeling setup. This is the center point of it. And we've basically found that our biggest forecast problem so far, at least in the cooler months in the spring season, has been precipitating fronts that roll through. We're systematically high bias. Luckily, this distribution of wind capacity factor error, wind capacity factor being the total potential amount of energy that a turbine can draw from the atmosphere, we generally have a pretty small bias. But we do have a large tail, and this comes from a lot of those passing fronts. Sometimes they could be such a high bias that the model can predict you know, winds beyond the cutout threshold. So basically turns off the hypothetical wind farms. And in that case, then you get this, you know, we get zero wind energy when there actually is some. And so you get this blob down here. There's other forecast concerns, but this one really sticks out. This is one we have to make progress on in order to really show improvement during this field project. We're also setting up a system for the Hurricane Forecast Improvement Project. It starts in 3 weeks, actually, and we're still in the process of setting it up, to be honest. So I haven't even really started hurricane-specific tuning yet, but you can see we have this tilted ellipse domain. We're going to run 2 configurations with and without the convection scheme. They're going to be cold started off the GFS. We're going to run the system twice, 0 and 12 UTC out 5 days, twice daily. So that's our plans. We really don't have much results ready for yet, but this is probably going to be the thing we work on the most in the next 3 weeks. Okay, so about this transitioning to submodule repositories, we think that this is the best way to go for centralized development. It's always been a little bit of a challenge to have different schemes and different model hosts. We want them to be unified, and so our co-developers can all work on the same code no matter which modeling framework they're working on. We're trying to set up some automated unit tests, so every time we make a commit to our own repositories, we can get first order checks done immediately, but we'll still leverage the regression tests associated with each model host when we check these parameterizations into the model repositories. I like this because it's a clear separation of the scheme and the model hosts. I think that's pretty important to me. So we can incrementally track our improvements over time in a public facing permanent repository. And it can even tag specific versions for publications and things like that. So we're not stuck to the release versions of specific model hosts. We can do it at our own granularity. So in summary, our model development has returned to MQ die cores. And of course, we have a lot of multi-system, multi-scale testing going on right now. Again, we haven't started the global testing yet. I'm excited to do that because we're running FV3 globally too, not just to make comparisons, but to actually do die core specific tuning if need be. Because that really hasn't been done in the M-cube die core for quite some time. So this cross die core optimization is just about to begin. But since we're moving to standalone submodule repositories, I think one important outcome of this workshop, in my mind, would be an agreed pathway to official implementations of these submodules into each of these respective model hosts and whatever related model code code modifications come with them, because some of it's beyond the scheme level, and not just for GSL. I think this would, obviously our colleagues at NSSL and elsewhere have done a lot of work too. I think we need to get this centralized as soon as possible. Thank you.
Are there any questions for Joe? Well, I have a quick one. So these repositories, do you consider those effectively UFS repositories, or are these ones that each of the developers and their local labs will set up, and the UFS and maybe standalone MPAS and WRF would pull from them? How should I think about this?
Well, they're meant to cross, UFS and non-UFS applications. Like say for WRF, for example, we want them in WRF too, and that's not really part of UFS right now. So I think it's kind of meant to span all implementations. They will be, I think the overall regulation of these repositories is still an open question, at least on the detailed level, but I think they will be focused on UFS work, no question about it. But it's meant to span beyond that. different question, since I'm really happy to see you're looking at all the other potential MPAS applications within NOAA and within the UFS. It does raise a question, particularly for things like HFIP MPAS. One of the things that the H4 and the halves, both with the H4 and with the FE3 version of the hurricane models in the UFS have is the capability of either a relocatable nest or a relocatable grid refinement. Do we know if that is something that MPAS is looking at or not? Perhaps it's the question for you. No. You should look at that.
Over here. Right here. Here. No, here. Has your name on it.
Yeah, you just mentioned that you have noticed some of the bias and the 2-point bias in the MPAS focus. Have you noticed any issue in the FV3 application? Similar issue?
Not comparable. I mean, as you can see in our, oh, sorry, if I go back to this slide, you can see in FE3, Rufus is trending high bias at this point in time. And some of it could be just part of the synoptic regime though, because a lot of our summer retros that actually went a little bit dry. Technically, dew point is 2-meter dew point has been one of the strengths of Rufus. Actually, it's been really good. So I don't think FE3 has its biases. The same physics, you know. So, well, it's the same physics, but there's probably a flawed implementation here. That's a problem. I don't consider this an MPAS bias by any means. I don't mean to push this on MPAS. It's probably a lingering flaw in our physics implementation.
Well, the coupling of the physics is different in FE3 than in MPAS and WRF, for example. So there's a lot of things that could be affecting that. Okay, we're at the final part of this last session of the day before our reception. And essentially this is discussion. And you can see the title, Development and Support of MPAS in Future Application Spaces. And the reason we have this as a topic for the discussion is that the landscape that we're living in is changing. If you look at our experience from WRF, essentially the operational centers that used it, there were a lot of them that did and still do, took the WRF community release, maybe did some tweaks or put some layer on top of it if they needed significant extensions. I'm thinking for climate applications and other things. But then they used what it was effectively the community release. So through our tutorials and meetings like this and stuff, the community would be educated in how to run WRF, and that the centers could draw on that experience, students coming out of graduate programs, et cetera, to work on their systems. Well, now, as you've seen, we're entering a different regime in that it's not the full MPAS release that's going to be used in a lot of these major applications, particularly in the NOAA applications. We're going to pull the DI core, the dynamical core from MPAS, and slot it into their own system. As you've heard from in these last couple talks, particularly from Curtis's talk, we have experience in how that's done. As I mentioned this morning, we have MPAS in our community Earth system model, and that's pulled directly from the MPAS repository.
So with a particular tag out of that repository. And kind of that's that. We've had to put in changes into MPAS to facilitate that. I expect we'll probably have to put in perhaps some more changes, facilitate MPAS, the dynamical core being pulled from our repository and brought into the UFS. But it's essentially doable. From our experience though, now having, for example, MPAS tutorials is not going to teach someone how to run MPAS in the UFS. It's definitely not going to teach anyone how to run MPAS and CESM. And CESM and the UFS actually share a fair amount of machinery there. And I can tell you from experience, because I've run MPAS and CESM, and of course I run MPAS. Running in a coupled system with that infrastructure, with effectively what's known as the NOAA infrastructure, CMEPS, which is the coupling infrastructure, CDEPS, which is the data handling part of that. It's a lot more complex than running WRF and MPAS. Of course, you're getting coupling with that, but it's a lot more complex. So the questions that we, and I'm thinking we at NCAR and M-Cubed have, is what does this mean in terms of how we move forward with support and development now that the components that we're developing in our release system, just parts of it are going into other systems. It's obviously important for us to work with, for example, NOAA, like we work with CESM, mostly in the climate lab on the hill there. It's important and we have good working relationships when we move this forward. But it's now essentially a larger support burden, if you will. And also there's this question of what expectations are on both sides from M-Cubed. What does, for example, NOAA and the UFS need from us, and what can we get from them, if you will, in terms of furthering functionality or what have you. So in terms of those questions, essentially I thought of two, but you can probably think of a lot more. And so this is from my perspective, and that's what I've been giving you now. That's kind of informed with the WRF experience, which had a lot of positive outcomes. It had a number of negative ones in terms of the relationship, things that didn't work, things that did work. Now we're going to something different. So I would say hopefully we've learned a lot of lessons, because some of us from past are still here. Me, for instance, and a number of other folks like Cliff remembers a lot of things, and other people, but it's a new world. And in terms of benefiting the entire community, what should we be doing here with our MPAS development and support in M-Cubed? So essentially, we're looking at what we're going to need to do for technical support for these other models where the MPAS dynamic core goes in. And given that that's sort of my child, if you will, I know if something goes wrong, they're going to, oh, it must be the dynamical core, because, and so we're going to have to work with them to work through these issues. But we like technical support, documentation tutorials, our tutorials, UFS tutorials, things like that. How do we see ourselves working that? And then on the other side of that, in terms of the other side of what we provide to help with those applications, is can we leverage them? So for example, there's going to be all the physics suites that are used both in global implementations of the UFS and in her implementations and other ones that'll be run. Should we be pulling them to run in our MPAS release here, for example? Can we leverage the analysis tools that the operational applications will be using with the standalone model? Should we actually work to be able to configure the release model here, the MPAS release here, to essentially reproduce the operational UFS configurations that in this case aren't coupled, for example, to an active ocean, for example. So those are the questions that I would throw out there. And you've heard the talks from, I think, Curtis really summarized really well what all this means in terms of what's got to happen, at least from the NOAA side. And we'd like your thoughts on where things should go. So with that, we got a ways to the reception. So please start speaking up and tell us what you think. Cliff, you usually start these off. So that's why I look to you.
Could I say something controversial?
You sure can.
Okay. You know, we have a tremendous opportunity here, but there's tremendous dangers. I mean, let's face it. It's now there's a realization that MPAS is the way to go, right? Let's go back 10 years ago.
No, let's not, but go ahead. You can go ahead.
Okay. No, let's go back 10 years ago. The US operational NWP was in trouble, and everybody knew it was in trouble. We were inferior to the rest of the world. And so we had the Weather Service going one way. We had WRF, we had MPAS developing here. Okay, so then the Weather Service decided they made a terrible error. They decided to use the FV3 core, and that turned out, and we're seeing it here today. It was a huge error. Okay, and now we're trying to reverse back 8 years of an error, right? And it's clear that we got to work together. That's the trouble. We bifurcated. You know, the Weather Service went their way, NCAR went that way, the Air Force went the other way. So we divided our efforts, okay? Then we had the EPIC, right? EPIC Center was going to bring us together to work together, right? But that didn't happen. What happened? It became a computer software support group, okay? In there and run by Raytheon. It's been a disaster. So the message here is, folks, we got to work together. I look in this room here, we have such resources, okay? We could have, and I forgot to mention JEDI, okay? Forget JEDI, tremendous advance in trying to have model agnostic data assimilation. So we have MPAS, which is clearly the way to go. JEDI, the way to go. We have all kinds of interest in physics, okay? Well, we shouldn't go the way that the National Weather Service does what they do with MPAS, and other people do what they do with MPAS, and the physics, God knows who does it, okay? This is not the way to do it. Well, once we need to come together. We need one center. What the EPIC concept was originally, one center, it should be here in Boulder, right? Combining, you know, NCAR, the universities, the Weather Service, NOAA, everybody, to create one state-of-the-art modeling system. And it should be done here, properly resourced, and we shouldn't divide ourselves, okay? So we've been doing it the whole wrong way. We've divided ourselves. And MPAS is clearly the way to go. This is a really unique opportunity. We have to take advantage of it to bring ourselves together to develop one state-of-the-art system that goes to convection-allowing resolution globally. It can be used for all kinds of applications. That's what we need to do. No more divisions. Okay, maybe that's controversial.
Well, there are several controversial points you made. But I want to let others respond. I'm sure there's other thoughts out there.
Hi, I have a question on something you said in one of your very early slides earlier today. And this kind of builds off of Cliff's point. You mentioned that now there's been established an MPAS Science Advisory Board. And so I'm kind of curious if you want the community to come together. Is that internal to NCAR? Is that invite only? Is there a formal application process if your voice isn't already part of that? Or what's your vision of that?
So it's all outside of NCAR?
Okay.
As an advisory panel. It's not required by NSF or even by NCAR, but it's a good thing to have to get a reality check on things. We're going to we meet twice a year. I didn't put up the list of people on it. I think we can probably put that somewhere at some point, like on our new web pages when we get them there. So it was by invite. We tried to get a group of people from the community, some new faces. This replaced the Research Applications Board, which is this. Wow, it started a long time ago for WRF. That we needed to evolve that to something else. So we did.
Okay. Do you see in the future opportunity for others who might not necessarily have been part of that conversation to apply to join? Not necessarily a guarantee, but at least a pathway to become part of that community?
I think we could, Gretchen, why don't you go ahead and address that one? That's a politics question. So the M-Cube director answers that one.
You didn't need to go away quite. Yeah. So no, it's fine. I just wanted to say, I mean, I thank you for your question, and also I'm going to comment on Cliff's topics too. I mean, I totally agree, and I don't want to say anything against the comments that are like, "Hey, MPAS is the best." But this is all about how do we work together, right? And it is honestly, I don't really find people that disagree with that point. I don't know that that's that controversial. It's the devil's in the details, right? About how do we work together. And I think, I can meet with various different groups and we have very complementary missions, but we do not have the same mission. Like if you look at NCAR's mission and who we prioritize, and then you look at NOAA's mission and who they prioritize. And really, if you look at a priority list, we might have all the same stuff, but the order is different, right? And who we respond to first, or who do we need to be most responsive to? And that's where the differences come in. And if we bring in NASA and DOE, there's additional like complementary but different missions. And so I actually think this is the question we want to ask is like, how do we do this? Because it isn't easy to accomplish the goals that we all have. So I actually think we do want to work together. So let's do that. I'm really excited about this energy. But we need more process in place. I mean, I hate to say it, but yes, I am the director. I'm going to talk process. Okay. Sorry, it's yucky, but it really is about, and in response to your question, thank you for asking about our advisory committee. Yeah, we needed to stand that back up. So we made sure we had some people that already knew sort of what was going on in MPAS, but from industry, from other agencies, from universities. But how can that should not be the only way that our messages are coming in, right? How do we be more transparent about what's going on? So anybody, whether or not you're on the advisory committee or not, is giving us feedback. When I said that at the beginning today, I really we want feedback. It's just, I feel like we need a lot more process. We never want to share with NOAA, like, oh, here's what we're hearing from our community. Hey, what are you hearing from your community? How do we coordinate amongst those things? And then, yeah, it runs the fastest, it has the most accuracy. It's like, again, we end up when you get into details, we do have some places where we're going to make different decisions. Like NCAR wants to have a model that has the most flexibility as possible because it's used for all kinds of applications and all kinds of research. NOAA might have a more focused subset, not focused enough maybe, but Curtis is like, more focus, please. But yeah, but has very specific outcomes you're going after. So but I think we don't know how to do this yet. So I really want to hear ideas. So not only like, what capabilities would you all like, but how would it work for you? Like if a committee can only have so many people, so there's got to be more ways that we get feedback. But then that feedback, who does that go to? And how do we decide what that means? So I know I'm saying more questions than answers, but I think that's what this discussion's about. So thank you very much.
I should say this discussion session and the one Thursday, that's 2.5 hours. That's longer than our advisory panel will meet in a year. So this is your opportunity here to tell us what you think and want.
Since there are a lot of new people here, my name is Hendrik Tolman. I'm from NOAA, from Weather Service. And I've been having the fun job the last 10 years or so after I moved from being the EMC director to a senior advisor to try and get this community to work together. And so I don't know what, I think Cliff said something at the beginning of this session. And Cliff and I either massively disagree or agree at exactly the same time. Because it is obvious that as a big US and even international community, if you look at all the resources we have together, we should be easily able to do the things that we want to do with the rest of the world following us. But how exactly you get there are more ways than one to do that. And if you, terminology is kind of a interesting thing to think about that way. And if you talk about the unified model of the Met Office or the unified forecast system, the language doesn't work properly because the word unified doesn't mean the same thing. So the Met Office and IFS have followed more or less what Cliff was saying. We want to have one guru, one SAR that runs one center that does everything at the same time. And yeah, that would be a lot better in some ways than running it as scattered as we have done for a few decades. But you need to learn from the past also. That is what the Unix folks said too. And then Linus Torvalds proved them wrong by having a system that is not governed from the top by one SAR or one organization. And I want to make it very clear, I'm talking here about my personal view of that, my personal opinion. This is not, I'm not talking here as a senior leader from NOAA, telling what the NOAA strategy and the NOAA position is, but from what I have seen, 30 years of community modeling with WaveWatch, with HWRF, with CRTM, it is better to be organized and to be working together than it is to be scattered. But it's even better to allow everybody to do what they want with the same tool set. And this is the idea that Linus Torvalds started off with Linux. This is basically what we've seen with some of our operational models. One of the reasons why Weather Services and NOAA is going UFS is that, as an example, we had something that we couldn't do in one of our models. A university did it. The French Navy paid for getting into the UFS. The Corps of Engineers decided to pay for optimizing it. The Navy put some money in, and suddenly we had a capability that jumped 10 years ahead. Now, is this without risk? No, of course not. Is this still having the chance of creating stovepipes and all kinds of good stuff? Yeah, of course. But I do personally believe very strongly that a truly open source and a truly open science world where people can put stuff into our models that we didn't even know that could be done or are broken is way stronger than trying to be centralized and doing it the old-fashioned way with having a well-established kingdom. And there's one really big problem with that, Gretchen. And the big problem with that is that on the one side, you think that you would have to have very strong governance, very centralized governance for that. And that's the one thing we are struggling with the UFS and with, by the way, like you said, UFS and CESM are really sort of very similar in terms of how we're organized. I personally believe that you have to be more organic than centralized in order to have all these different things done properly. I don't want somebody to tell, I don't want a wave model to tell you what they have to do in the CCPP. I don't want a ICE modeler to say what has to be in atmospheric post-processing, that kind of thing. You have to be a little careful with that. But with that, you have to set up some kind of governance that makes sure that the existing ecosystem of communities that's already there is enabled and not stopped by doing everything together. That means that you have to have a governance that is more based on do no harm, backward compatible. If I change something, I don't break something from somebody else, than trying to govern every single step along the way. Anyhow, my personal opinion, and I know that we've talked about this many a time. Cliff and I agree with the fact that we need to be centralized. We very clearly disagree on the power of community versus the power of a single kingdom. Yes.
Okay, hey, Abraham, what do you got to say?
Hello. Yeah, how's it going? Yeah, I'm joining from Hawaii, as it's a little bit earlier here. But yeah, I had a few comments. One thing I guess I noticed with the global prediction for MPAS is we kind of have these large regions like the US and East Asia and Europe. They have using MPAS to create this like kind of localized region with high resolution. And I guess I would hope for, I guess, some more collaboration between countries, I guess. Because what I like about MPAS is it's like you can have this large scale system, but you can apply it to like local regions with ease. And it's kind of like this base core that you can build off of. But I would hope to see more collaboration. I guess I might be reaching a little bit too far, but I guess, for example, like if we want to have, I guess everyone's dream here is, I guess, to have small scale global, like cloud resolving model. And in order to get it right, to get the prediction of that right, you need to have small scale and it needs to be global. But like we have definitely huge computational costs with that. Is maybe there's some way that multiple countries can take part in parallelizing the computation so we can get that scale down. And the other thing that I'm personally interested in is place-based prediction for local communities. How can we make it easier for a local community to take MPAS and apply it to their like local region? For example, like Hawaii, it's a very small region, but can we have the same thing that the mainland United States has, but just around Hawaii and zooming in on that and utilizing MPAS?
Well, to address your latter part, I think you're going to see NOAA working on that because they're interested in more than just CONUS. Alaska, Hawaii, Guam, Puerto Rico, so that they've got a lot of ground to cover, and I think we're going to see some hopefully innovative techniques pushed out there. MPAS is just getting to the point where I think adoption is happening. You've seen a talk from CWA in Taiwan. They're working with it. So there are other centers around the world that are starting to work with it, although not so much necessarily globally, but looking at it as a regional model. The other countries that run global models, they have their own global models. So that's kind of how that is. The other application space that we haven't heard much about, and we won't hear much about this particular WRF MPAS workshop, is in the climate space. So for right now, for example, my biggest thing I'm doing as a scientist is running diamond simulations, which are 3.75 kilometer global, and we're running a year. And I'm about a third of the way through the year, and we're going to finish that up this summer and fall. And there's a lot of work in terms of model intercomparison and looking at the biases in the configurations that we're running to see how they work. So there's a lot of things going on that I think a lot of collaboration at the global scales. But I would say right now where we're seeing most of it in terms of at the working level is maybe in that climate weather interface, that sub-seasonal to seasonal to year, maybe getting close to a decade. I hate to say it, there are centers, well, I don't hate to say it, but there are centers, research centers that are running 3+ kilometers global, and they're now talking, they're actually now they've run decades. And here we struggle to run a year, or we have to plan and stuff. So we are behind the world in this technology, in our Earth system models, and indeed in our weather models too, when you look at what we can bring to the table compared to the Met Office and the IFS, for example. I'm not quite sure I answered all your questions, but I think things are moving and there's a lot of things happening in the world. And then, of course, as someone mentioned, maybe we'll all get our models will be replaced by machine learning. So, but I'll be retired by then. So,
yeah.
Yes.
So,
thank you.
I'll make a brief comment on maybe trying to articulate the problem, some of the controversy here between whether it should be centrally dictated or more community based. And it's
Yeah, I think one of the issues is, from what I've seen based on of today's talks versus what we saw last year at the workshop, is there is starting to be widespread adoption of MPAS. And not only that, a lot of folks are taking the MPAS model, going back and modifying it for their own specific applications, whether it be adding chemistry or changing some of the physics to support whatever application they want. And I know one of the things that was discussed last year was this CCPP, where there was going to be this common physics package that would get updated and controlled. So, you know, to kind of jump on that and go back to how should you answer your first question. One of the things I saw that I really liked was the developer's guide. To see that that's in the works. I think that's going to be really good for all the folks who are taking the model, going back and starting to work with it so they can work with it within the best possible way. Some of the other things that might be really useful going forward would be a repository of meshes to build off of the ones that are already available. I can see other groups are starting to develop their own meshes that seem to work well that aren't part of that. I don't know if there would be a process to take new meshes that come in, developed by other groups, do some sort of common quality control here, and then keep them in one repository. Another thing that might be helpful would be having a standardized package test of the model that anyone who's going to take MPAS, go run it with their own thing, add whatever they want to it to use either internally or otherwise, would then have a set of things that they're going to test the model on to make sure that they haven't done anything that breaks what is in the baseline MPAS, so that we don't end up with a bunch of different groups, each with their own version of MPAS that's a little bit different, tailored to an application, but all of them are just a little bit broken as well.
Okay, to start with the last one first, we are definitely behind in the development of regression testing for MPAS. Primarily because we've been very thin on software engineering for a long time. We have been addressing that over the last, I'd say, year to two. But as I think all of you appreciate who have to try to hire software engineers, and I know some of you here are in that position, it's very hard to find good ones and it's very hard to hang on to them. So we brought several in, some haven't worked, some are working, fortunately. And so I think we're going to be addressing the regression testing, which I think is critical for users to be able to just trigger a regression test and see, have I broken anything? Are things doing what they should do, et cetera. I'm trying to remember what the other thing. The developer's guide is related to that in the sense that we don't have the people resources to bring in physics like we did over the decades when most of the WRF physics came in. We just don't have the people that can sit with the developers and help them bring it in and do that. But with GitHub and the young scientists come along who know how to use that and know more about development, I think we're more comfortable with that kind of development. We're seeing that we're getting the pull requests are getting better and better, and hopefully with a developer's guide there'll even be more. So the overhead of us bringing new advances into the model shrink down and are less of a support and development burden on MQ. And I know there were other comments that I have probably not remembered. I'm sorry? Mesh library. Well, so we have a collection of meshes, but we don't have the statement saying, hey, donate your mesh to the MPAS community. And maybe we need to do that. Michael, we should definitely consider doing that. And the question is, should we? So we don't put the meshes onto GitHub because that's a lot of data, right? Is that correct? And
so we don't put the meshes in a GitHub repository or a Git repository for that matter, because they're binary files and we don't have versions of them. There's no sense of version control for those. But yeah, we're happy to take donations if anyone has a good mesh that you've generated. presuming you can generate your own mesh. That's a note that I've written to myself repeatedly throughout the day. Maybe next year we can have a talk or a Friday morning session next year about generating your own meshes. The more pressure we get, the more likely that is to happen. But yeah, I think that's a great idea that if some, I know some of you do have mesh generation software and know how to use it. So if you would be interested in donating those meshes, we'd certainly put those up on the download page and give you credit. Sorry, I'm not going to look at any person in particular here, but
yeah.
All right. Okay. Well, I just want to talk about the questions that you put there. So how should you support the dynamical core? I would start with, yes, you should support it. So that's, you know, the premise. And I think what was said before about code management is top of what would be on my list, you know, together with those 3 bullets. But I think if we know how to contribute and if we have the regression tests for that, that would be really a great service to the community. I think the other thing is to think about separation of concerns. So I would say that would be the best way to organize our thoughts. So we have physics, we have dynamical core, and then we have host models that bring it all together. And hopefully these host models bring it all in the best way. So I think what MCube can do is at least you know, focus on the dynamical core and focus on the entire MPAS or MPAS-A, whatever, host model. As far as the physics, I think there is an opportunity, big opportunity out there to contribute and collaborate with the bigger CCPP community, which I think it's more and more looking like as a constellation. I think it no longer looks like there's going to be a single CCPP repository managed by the Developmental Testbed Center, but that multiple groups will serve their physics. So I think earlier this morning in the workshop, we heard about the repository of shared physics with the goal of sharing between WRF MPAS-CMAQ, and then there was a box, other host models. I think we really could put more energy into that other box and think, you know, just create a roadmap about how we can share physics more broadly between MPAS and CCPP models, UFS, and the bigger community.
I would just add is that our efforts to develop the shared physics repository in MMM are as much trying to learn what works and what doesn't in terms of the technology, and then looking at that as any kind of a permanent solution. I think it's an experiment, and hopefully if we can't get ourselves in order in our own house here in NCAR, MMM, then it's going to be hard for us to actually work with these other repositories and feed into that. So I think it's going to be an interesting evolution of physics and building different systems with the different components distributed. And we're going to learn a lot of interesting things in the process.
I would just say, you know, as you're doing here right now, include the physics developers in these discussions about how we can all contribute to the shared repositories. You know, we had Joe Olson's talk. So yeah, we are definitely looking for entry points on how to connect.
So one of the benefits of the MPAS dynamical core going into the UFS is you're going to have to make the UFS physics work properly with MPAS. And that has been an impediment for us picking them up. And so I think that's going to, in itself, be very, very helpful to the community and what you'll be able to access. And it's only the details of how you're going to be able to access that I think need to be worked out.
I wanted to respond for just a second to Cliff's provocative statements earlier about decisions that were made roughly a decade ago. And just to put a silver lining on that maybe being a mistake or whatever it was, that the conversation that we're able to have now
about picking and choosing DAG cores or physics or models that you're coupling with an atmosphere, or all of these things have kind of come in the last decade that allow us to really take advantage of software modularity that gives us the ability to even have these conversations. I don't think that that was there 10 years ago, and saying, hey, we're choosing this one core that really was the monolith that was FE3, right? And we're going to have to choose one or the other of these models to be the thing. But everybody came around that choice, for better or worse, to say, well, how do we use this with the other thing that I've been working on for years, like ocean models or wave models or all the things, so that we can get them plugged in together to this framework. So I think with that choice came this proliferation of modularity in software and best practices around the modularity in each of these repositories that we're seeing community development in the testing frameworks and the code management. And I do just want to highlight that that was a huge, important outcome for us to be having the discussions we're having today, because of that particular choice, for better or worse on the forecast quality side. I won't get into that, but on the software side, I'm seeing that we are getting a lot of additional benefits from having that choice being made, and then how we responded to the choice in terms of what we wanted to do with it has come a long way for us to move forward in a software sense.
Mhm. Definitely. I don't have like a queue in Google Meet, so I'm just kind of alternating, if that's okay. Please, please.
Sorry. Oh. I thought I didn't mean to do that, but it's okay. So you were talking a little bit about just sort of trying to reduce the overhead, you know, for the MQ software developers when we are putting things into the model. So I was wondering if you could kind of speak to, I guess, the process or recommendations you have, or I guess if you wanted to contribute to MPAS, some feature or code changes, what is sort of the process that you recommend going through, and what is the timeline, I guess, that tends to happen?
Okay, so that process is going to show up in a developer's guide. But I can tell you the first thing, the critical thing, is talk to us first. So that we know what you're thinking of building. We may have thoughts on it. We may know other people who are working on the same thing. But that communication at the very beginning, I think, is critical for helping us, because it's kind of frustrating when we get a pull request we weren't even expecting. And then we look at it and like, oh, geez, it really should have been done another way. And that's based upon our intimate knowledge of our system, and not necessarily on a erroneous thinking by whoever was developing it. It's so by communicating right at the beginning, where we see things coming, and we can work with the developer, bring it in as a pull request that's effectively almost ready to go, that doesn't need a lot of work, is critical. And Michael, do you want to say anything more about that? Because you're the one who's probably right in the middle of that on the kind of technical side, the coding side, as opposed to I just look at the science and what it does.
I don't want to hurt everyone's neck. Let me come around here. Yeah, so you've made some really great pull requests, and so we'll get on those. No, I think so, and I mean that. So as Bill said, I think starting a conversation is probably the first thing. Let us know, hey, I have an intent. For example, to give a specific example, it would be really great if I could write an output stream only starting after a certain time. So, you know, from 24 hours through 36 hours, I want to write an output stream. We don't go looking for it, but we had a pull request for this, and it was implemented in a way that we said, well, that's probably not how I would do it. And I think there's a different way that it could be done, and it could be more flexible and so on. I think it builds harder feelings if you get kind of negative feedback on something that you've worked really hard on.
Project was going on that year. And what I remember from that is that there was a very healthy competitive spirit amongst models that were participating in that exercise. And the result of it was that nobody won anything, but everybody improved in some way. And the reason that happened is because as the exercise progressed and as people began to kind of break out of their sort of shell of saying, okay, I want my model to win, whether it was ICON or MPAS or the model that we had as when I was a PhD student, you know, we were proposing this and that and this technique and that method. And we all thought, hey, we're going to win this thing and we're going to look the best when we, you know, put up our results. Nobody won. That's what happened. After 4 days of all that, nobody won, but everybody was able to improve significantly.
Ah, this was DC MIP.
DC MIP, yeah.
Right, okay.
Yeah.
Big model under comparison project.
Right. And so I think that, you know, one thing that we could abandon from the previous decade is this idea that there's going to be a winner of all this, that there's going to be a model that wins. And there's the implication of that is there's a bunch of models that lose. And so we need to get away from that characterization of whatever model is being employed in a general sense, like the way MPAS is right now. I don't think we need to characterize it as a winner or FE3 as the current loser or FE3 as the past winner or anything of that sort. And balance our individual success as developers with our success as contributors to what's being driven in this collaborative sense. So, you know, I have a little model that I keep because I'm a model developer and I can solve the equations of motion. And so I keep a model that keeps me sharp and keeps me sort of engaged in techniques and things and numerics. But I'm not going to turn around and start proposing that as an alternative and try to compete with something like MPAS. What I'm going to do is actually take the insight that I gained from that and see how I can contribute that towards the greater current of what's going on. So I'm just saying this as a way of how the question was, how can we actually engage in these collaborations without getting in each other's way? So just some ideas as to how that can actually happen if we can abandon this competitive urge to declare winners and losers when we, you know, look at models and compare models and forecasts and whatnot.
Hi, I really want to help add to the conversation, reiterate something that's already been discussed here. It is to put my support out there for the development of the developer's guide. I will say it is very challenging for me to, as an agency that is not going to stand up its own MPAS. I'm going to say it now, you're probably never going to see an MPAS army version. But not being able to clearly articulate what the path is to tech transfer is actually one of the reasons that is prolonging or kind of delaying our commitment to be able to saying we're going to stop doing WRF transfer versus MPAS. So even if it's not perfect, you know, if there's just guidelines for rules of thumb, sustainment, kind of contributions, things like that, that would be very, very helpful to help move us in that direction. Again, even if it's not a 100% solution, but an 80% one and written down, I think would really help us be a more active participant. And if you need volunteers who you want to use as guinea pigs for kind of peer review of the developer's guide, we're happy to help. Yep.
So the answer to your questions up here is yes. Although I'm personally not that big on tutorials. I'd rather read the slides in a quarter of the time. But you're going to have to do all of those things. And then the question is how. And so you're going to need resources. And I think a great deal of the frustration on all sides of these questions comes from insufficient resources. So we're not going to completely redo the entire federal science enterprise. That's not going to happen. It would probably be even worse than the mess we have if we did try to redo it. We're not going to completely restructure atmospheric science in the United States. So what we need is for NCAR to have a few more resources. And I don't know exactly how many people or how much money. But I'll digress for a minute and say that this is an ongoing problem with NCAR. I've never worked for NCAR. I don't speak for NCAR, but I've lived with NCAR my entire life. My father worked for NCAR. I've paid attention to NCAR. I've gone to seminars. I've worked with people. NCAR has always had a dual personality. And sometimes those two personalities have been better integrated than other times. So on the one hand, everybody who works for NCAR is expected to do research. Most everybody. On the other hand, everybody who works for NCAR is supposed to be in service to the university community. And those things have always been in conflict in individuals and in the organization. So it's difficult, I think, for NCAR to decide that it needs to put resources into something that is essentially entirely service to the community. And yes, so the people who are doing that may also be able to do some research projects, but that's always been a tension. So somebody is going to have to, if MPAS is going to be the DICOR for most things that are done in the United States, at least in terms of atmospheric science modeling in the future, it's going to have to be resourced a little more, and it's going to have to be resourced at NCAR, and it's going to have to be somebody's job to do that.
Agreed. That was mostly political. Gretchen, do you want to say anything about all that, or?
To say no, I don't. Okay, no, I mean, I was just actually taking some notes, and I was gonna say, I mean, I actually think I also cannot speak for all of NCAR, but you know, myself, I'm well aware of this issue, and I think we are working to better integrate these two spaces, because honestly, I think at the core, why does the National Center exist? It is to serve the community, but how do we best serve the community? By coupling that service with deep expertise. And so if we are not being intentional about that, that's a problem. And I'm not going to claim that that's integrated across everywhere now, but that's definitely the work that I'm doing. And I see that work happening at leadership level. So I think that's, and if you have other ideas, you know, feel free to talk to me, but I would say that's my vision. And I think that's what we're working on.
I would say a decade ago, NSF, our primary sponsor, you can see it's now NSF NCAR everywhere you look. That's now the official only way we're supposed to do it. We're supposed to state it. 10 years ago, they were, I would say, antagonistic to our relationships with operations in particular at NOAA, because they thought, well, that's what NOAA should do. We shouldn't be spending NSF dollars on that. That has almost flipped completely. Right. That has almost flipped completely. So,
for the first time ever, there's a formal dear colleague letter from NSF that encourages us to work between operations and research and academia all together.
Right.
I did not think that I would see that in my lifetime, because we've been fighting for that for 30 years.
Right. And a decade ago, I wouldn't have believed that would have happened, but things have changed and for the better. And I think as the visibility of MPAS going to UFS, that hopefully will lead to more funding from NSF. Right now, as all of you, a number of you are federal employees know, that the budget is, it's a difficult budget time, especially in election year. So I think we're going to let the dust settle and see what happens, and hopefully things will improve and help us out. Curtis.
So, and that's Mike, go back to Gretchen again, but I want to connect a couple points that were made a little earlier here from both Cliff and your comment earlier, Bill, about software engineers, the challenge that, you know, you're having sustaining or, you know, obtaining those, and the fact that we have Epic, which is very much a software engineering organization. I'm wondering about the prospect of supporting, and I'm promised nothing, I'll say that right now. This is about my pay grade, but I think that there's some
decisions that are going to be made in the UFS governance, and that's a group that I'm involved with on supporting inclusion of things like MPAS as another DICOR in the UFS, and whether M-cubed could accept some level of support, for example, from Epic, yeah, in terms of either software engineering staff time, et cetera, and what that would look like. So I'm kind of just curious to read what your reaction is to that initially. Okay. Well, yes, agreed. I mean, I hear a need, and I think we've got a resource on this. So, yeah. Okay.
Yeah, we definitely want to encourage that and see if there's some possibilities. It's kind of matching up software engineering skill sets with the things we need done, because we're kind of an odd application, if you will, in terms of software engineering. So hopefully we can take advantage of that.
Okay, thanks.
I was just wondering if we've looked back to see what worked with WRF, right? Because one of the things that I heard right away when we were trying to go to FV3 was the graduate test, right? Can a graduate student grab this model and run it? And that's what I think, especially in the last 10 years, where WRF has really shined, is there's been this, I can pull it down and it just works, and I can get it running and get a base forecast really quickly. And that's something that after last year's workshop, I tried to do with MPAS and I couldn't do it. I'm not that advanced, but I'm also not,
Let me guess. PIO, was that the problem? That's
yes.
usually the top of the list. Yeah. Okay. And
so,
and now you don't need PIO. We have an alternative that was developed specifically to get past that, but I understand your point. Go ahead.
Yeah. So if we want, right, the thing to get the community involved in doing it is to make it easy to do it. So kind of an off the shelf, and I know, and I heard a lot of hesitation last year that, oh, well, you might need to change this. So we didn't want to set that like that, or, based on compiling and running it and having scripts and stuff. But I think they're having that base state, getting that instant gratification, getting people hooked on that, because it's addictive, is kind of a way to get the community engaged a lot. Because, I can't count how many, we say there was the graduate test for FE3, but I would say WRF is like an undergraduate test, right? With like stuff like UEMS. I mean, anybody can run that really easily. And so it's very widely used because of that. So I would say, something like that. And, kind of in regards to kind of resources, I know budgets everywhere are kind of an issue right now, but we really do have something special in this country, in that all this code, all this data, NextRed, all the stuff on AWS is free. And everywhere else in the world where I try to do this, I have to pay somebody for that data. So I really do think that, I know it's tough, but I think we really do, there's really bright future ahead here, because we have all this data, we have all this energy now and willingness to do this. So I'm pretty excited about this, but going back to, your kind of thing here, I do, the one thing I would ask of M-cubed is something, and I realize MPAS is still a little bit young, but something off the shelf like WRF that I can get that instant gratification that really kind of gets me going into doing the things I need to do with it.
Cliff.
I'd like to talk about czars and organization. What we're trying to do here is one of the most complex feats that mankind has ever pulled off. This makes the atomic bomb look like child's play, what we're trying to do. I mean, it's really true. And when they developed the atomic bomb, they had to divide themselves into teams, okay? And had quotes, observations to perfect the unit. Well, folks, we don't want a czar. We don't want a czar. That doesn't work, the czar. But we need to organize ourselves to do this effectively and to do it right. We all want the same thing. We want to have a modeling system that duplicates reality, the physics of reality, that forecasts reality. That's what we want to do. How do we get that? WRF was wonderful. I love WRF. I run WRF. But what the WRF development had a flaw to it. You know, the developers were great in getting the dynamical core, but physics, everybody's working on something. Okay. There was all this complexity. How many different parameterizations were there, right? But there was no organization to it. I mean, what was the defects of WRF? What were the physics that were deficient? Okay, could we put resources into where we needed it at? When you do physics, you have to look at multiple physics at the same time. You just cannot go at this in a random way. Now, the NCAR people are wonderful in creating the dynamical core. Okay, that's wonderful. That's done. But the physics and the data assimilation is all there. You have to think holistically to do this right at this stage. You can't do it any other way to push ahead to be the best, okay? And so we have to organize ourselves. We need a structure with intensive verification to find the flaws, to get the resources to fix the flaws. We have to do this together. We're not going to have a czar, but we have to bring the best of the country together to do this. That's the way we organize. That's why the original EPIC concept that Neil Jacobs and other people put together was actually quite good. You know, we'd have some kind of center here outside of the government that would, in an organized way, develop the best modeling system in the world. We can still do that. And it's time to do that. That's what's missing here. And we're at the point now that we realize we made a big mistake before, and it's time now to do it right.
Thank you, Gretchen. Another political comment.
Hey, Cliff. Yeah. So, I mean, I think I think when we think about things like physics, it definitely is like we need the whole community. Again, I'm not going to disagree with that part, that we want to bring expertise together. The challenge in a place like physics is to optimize it for what? And that's where, again, we end up with, there are many answers to that questions. Are we optimizing this for an urban environment? Are we optimizing physics for 3-kilometer CONUS forecasts of 500 millibar heights, or about precipitation, or about UH? Are we optimizing physics for like top of atmosphere radiation? I mean, we are not at a point where we're going to have a physics package that one physics to rule them all. You know, it's not where we are at yet, because these are approximations, right? So I think we can organize around certain problem spaces, and that would be a great idea. But let's recognize that there's different problem spaces. And somebody like us, NCAR, we are trying to support a community that works in lots of problem spaces. And so we're not going to have a single physics suite. And we want to encourage the community to be developing physics for different applications. I think we are looking at a change in, you know, the modularity. I love that comment earlier, like, and the constellation of physics, like some of that, we won't support all of that physics at one place. That might be some of that's supported by NOAA, and some of that's supported by the universities, and some of that's supported by NCAR. But let's also recognize, I think we do need lots of physics for lots of different types of applications.
The real world only has one physics. One.
Yeah, we can't do that yet. And often when we try to make the equations closer to what we think the real world does, we know the application answers get worse, right? So let's be honest. These are approximations. Again, maybe AI will fix it all, but I haven't seen that yet. So, and even there, AI only is trying to solve the problem you tell it to solve, right? So it still comes back to what's the application. So I think we recognize this is, again, part of this collaboration challenge, is that we have lots of different applications and they're all really valuable. So we're not going to have just one solution.
Go ahead.
I think a lot of these questions are kind of, and a lot of the things that people are using the model for are getting at one question that just kind of popped my head. And that is, as a community, what is it that we really want MPAS to be? Do we want it to be a model that can predict convection at longer lead times? Do we want it to be a fully integrated, fully coupled Earth system model for climate applications? Do we want it to be like, you know, what? Okay, everything. We want it to be the kitchen sink. And I think that goes towards a lot of the questions regarding physics and having common packages that fit everything else is what is the primary application of MPAS, and do we have a really solid definition of what that is?
We don't, I would say. On Thursday, part of the discussion session on Thursday, I'm going to put up that list that I showed of what we view as our priority development areas, which kind of touch upon that because they're all based on what different applications effectively. So with that, please.
Part of the discussion needs to be reframed a little bit of when something's added, how does it get sustained? I think that was one of the challenges with WRF was the entropy kind of took over of something wonderful gets committed, person graduates, goes and disappears into some other industry, and then there's nobody to kind of babysit it, and then you end up with elements that get lost. You know, again, developer documentation would be awesome for that. That should definitely be a part of it. But yeah, maybe not trying to pigeonhole it, but rather say rules of engagement and how do you keep it alive once you've invested the time into contributing it to the community. Yeah.
So about 4 or 5 years ago, or maybe more, when we were thinking about the WRF physics and also thinking about MPAS physics, we kind of put forward the idea that we would have which didn't come to fruition, I'd say in general, but of having contributed physics, where the issue with a lot of the physics is that when we advance the model, can we go back and test all the physics that are in it or make sure they work? And by having a contributed physics category, we can say, okay, we could put that back on the developers and say, hey, you've got to commit to, if you want to see these physics continue in use, to do that. And that was sort of moving to what I think the point you brought up is that having a longer term relationship with the developers and a commitment to some support, because that's what we found with WRF, with the millions of physics options in it, that we finally, things just fell by the wayside, and we still find, oh, some things don't work, or certainly combinations don't work for sure. So that's been a hard part. And I think we want the community and the developer community to be more engaged in that. I think GitHub and the way we're doing things in the community, we're evolving our physics, that may facilitate that. And here I was worried that we wouldn't fill up the whole hour and a half. I should have known. The three of you are there. Who wants to go next? Okay.
Yeah, just want to quickly add that from data simulation world, like JEDI system, you know, the different pieces of data simulation already sitting in the different GitHub repositories. So we have a lot of bundles, the bundles collecting all different pieces together. So I saw in the modeling world from this workshop, we're already doing some with that, like the physical, there are other repositories, US EPA, there are other CMAQ, MUSICA, there are some other. So I think it's very likely, you know, we have a MPAS ecosystem. So in the future, but not necessarily big repository, everything together, but we can, you know, make a car yourself with different repository together. I think we will see that way maybe better.
That's definitely how we're evolving.
I think this basically builds on what numerous people have said. I think we're headed towards a framework that allows for more innovation, broader collaboration. And I think that allows us to advance faster. So if things aren't all in one repository and everything has to be, you know, that MCube has to worry about every single connection within the modeling system, that's unsustainable given, you know, the budget situation. But if you can broaden things out and have a framework where you can have different people have different responsibilities, but all work together well, I think we're going to move faster. So, you know, just making it a more collaborative environment, but making sure that we have agreements about how we're going to collaborate and how we're all going to contribute and work together. Be able to move faster that way.
Agreed. And I think that last point, in terms of having agreement, That's what we don't yet have an understanding of with regards to the UFS, for example. We really haven't sat down. And my understanding is we're kind of waiting for that governance structure on the UFS side to solidify so that it's better understood where decisions are made.
Yes.
Okay, good. Thank you. I'm sure you had more than that to say though, so go ahead.
Yeah, I was first answering your question. So,
Oh, thank you. Thank you.
so just listening and looking around a little bit about where we've made progress and where we've not made progress. We do need to realize that our different communities, like a professor in a university or academia, a stereotypical professor in most universities wants to publish on their research and that tends to do things like, okay, I have a new cloud scheme. Why does this fit better with my physics observations? Whereas in operations, I don't care up to a level if I get the right answer for the right reason or the wrong reason. And some of the things that I'm seeing as going really much forward with in the recent past, CCPP. Actually, if you want to run a physics parameterization, there's one copy, not 16 copies that are all different. But the real power what came out of the CCPP is to select a few complete sets of physics and work with these. And in that way, actually look at the integration, the impact as a whole. Because what happened in the last 20 years, every time you would put a better die core in an operational model, the model has to be worse because the model is so well tuned to compensate errors. And you see the same thing in a UFS or a bigger coupled system. Researchers, development software engineers tend to look at the software stack. So can I do it a little bit better? Can I do it a little bit physically better? People in operations look at outcome. So you have to make a distinction between developing and managing the underlying software stack and having something that is measurable for better results. And so what we kind of drift towards is that we want the community to sort of organically deal with the software stack, where we hope that all the little communities that make that up do no harm when they do improvements. But we also select a global model, a global weather application, a regional weather application, and a hurricane application, and one or two more, just a few applications that we want to work together on as a whole. And so this idea of starting to work a little bit more together and look at where you are exactly in terms of improving the science and improving the understanding and improving projections and improving operations. You have to start having something that's measurable. You have to kind of make that distinction between the software stack and the application. And then to answer your questions, technical support documentation tutorials, yeah, that's 3 of the like 10 things you need to do. And none of us have enough money to begin with, but it depends on where you are and where you start from, what you're doing. And so, for instance, with the UFS side, our biggest problem was that it was absolutely impossible to run our models by anybody. It took Neil Jacobs a $15 million investment to run the GFS when he worked at Panasonic. And so the graduate student test that was mentioned a little earlier was us measuring to see if that we had made some progress with that. And some of these codes you can now implement in a day on about a dozen or so different known computers that we have. And so we really needed to go technical support and documentation. And then we go forward to the hurricane system. Okay, first reaction is, well, with the other models, we had to do this first. Well, the other application, we had to do this first. So we do this also with the hurricane? No, we didn't, because we had a community there and we wanted our community to switch over to software. So with the HAPS, we actually went with the tutorial first. And so you have to kind of think about what you want to do. And I'm not wanting to run NCAR. I don't want to run MPAS. I don't want to do these kind of things. But if I would have to, if I would be asked to advise you, I would grow my community more, because you have a pretty good technical support. You have a pretty good documentation. The more people more eyes you're going to get on your code, the faster you grow your community and the faster you leverage each other's work. And we've seen that with our HAFS community. We had like 80 or so papers on HAFS at the AMS meeting. And most of those were people who used to work in the HRF community. And half of them, we as weather service had no clue that people were working on it. So this idea of building an organic community by doing the support, the documentation, the tutorials, you have to pick out which one you want to pick, which one you need most. And so for some models, we needed the technical support, but by us doing the tutorials for the hurricane people, again, with the DTC as a community, first building an HRF community, it works. And so you have to look at it. I would build your community as fast as possible.
So I agree with you. I would say that's been our experience over the last 35 or more years, starting from MM1. Yeah, I think I agree with you completely. Jimmy.
Yeah. One of the points that was brought up was how easy it is to run WRF, and especially we call that the workflow. The workflow of WRF is very easy to you run GeoGrid, UNGrid, MetGrid, WRF, real and WRF, and that's a very easy thing for people to pick up and learn. We found through our experience with operational centers, they don't think in those terms, and the workflow with an operational model is so much harder. And that's same also, it turns out, for the climate model, where they have a coupled model, and those are just less flexible and less easy to understand if anything goes wrong. And they're also more limited to a particular application. So the benefit of the WRF workflow, which is also translated to a large extent to MPAS as well in the standalone model, is that they are easy to pick up and learn all the steps and just run through, because WPS pretty much is both WRF and MPAS now. And that allows you to use different constant data sets like elevations and weather data sets like GRIB, any GRIB or even other formats, and just bring them into your system. So that's what's needed for the research community, is a good, easy workflow, which we don't expect the operational centers or even the climate people to have as a priority. So an ideal view, from my point of view, is if MPAS can adopt the CCPP to have access to the operational physics and still keep the MPAS type workflow, that'll be one way to at least contribute with an easy research model to the operational physics. If you can duplicate what MPAS does within the UFS framework outside of the UFS framework, but just adopting the CCPP physics. And we saw that's one of the things Curtis had was it's 2 FTEs over multiple years to put the CCPP framework into MPAS. But that's one step that allows us to directly connect CCPP to MPAS. There are other steps beyond that, because even if you have access to all the CCPP physics through the framework, you still have to do things to convert the dynamical core variables to the physics variables, and there's things, we call them interstitials in the CCPP, which you have to write for particular die cores. But that's a much smaller step and easier to understand, because of the way CCPP is written, it has these meta files which tell you exactly what the physics needs, and there's only one entry point to the physics, which makes it easy to adapt any die core to the physics by just knowing exactly what variables you have to provide. So that's one ideal thing, in my view at least, is to have easy access to the operational physics, but outside of the operational workflows.
Did I see on one of Curtis's slide that the DTC is going to do this for us? Did I misread a slide? Does the DTC have support to put CCPP in MPAS? Or did I misread something? Or am I imagining it? It's been a long day, so some parts, okay. So well, that's the reason that's up there, is that this looks like if we're going to fully adopt the CCPP, now is probably the time, because it's going to be adopted in some sense in the UFS, and can we leverage that port to also use it in our community release? Yeah. Yeah. Yeah.
So
Almost guaranteed that there's more work, but ideally the plumbing is sort of mostly there, and then just the science needs to be sorted. We're almost at time here. I wanted to make one. Go ahead, Louise.
I wanted to make a quick follow-on comment to Jimmy's comment about workflow. And I'm probably going to get myself in trouble because I'm not in depth in the technical details, but while the infrastructure, like the coupling infrastructure between the UFS and CSM is shared to a certain degree, the workflow is not. Those are totally separate. And so I do think there is a need for like the simpler workflow for the researchers, and then there's more complicated workflows for like the full climate modeling and the operational. So, but in some respects, if there's some way to share some common tools across those aspects, also would be helpful to kind of keep that modularity and familiarity when you have to move from one step to another. But just keeping in mind that there's, but he's laughing. Hey. I'll let Christina take over because she's our workflow expert.
Okay, great, please.
I do just want to mention that we are developing a unified workflow under the UFS, and we have already developed a workflow that is capable of running these things in series for cold start forecast. Come see our poster number 13. We'll talk to you about it. But the idea there is that we're trying to give us a common framework for doing a lot of these same types of experiments where you can maybe just provide a YAML and say, I would like to run the initialization steps for its change res cube and FE3 to run a global forecast for FE3 versus ungrib and MPAS-init and then MPAS in the same kind of language and the same set of tools that are based on like this idea of Linux-based tools where you're just running from the command line with a config file to make it super simple to set up and run a very basic test. And then a couple of additional tools are there for helping to set up automation for that, like with Ricotta workflow and maybe EasyFlow in the future. We talked about Silk as a possibility to support as well, so that we do start to see that automation of being able to do that on a regular ongoing basis instead of having to run that command every time you want to do those things. So we are moving in that direction. We do start to see some proof of concept workflows, and MPAS is our first one where we've actually been able to implement that because it does have that kind of simple workflow that you were talking about that came over from the WRF era, where it's like there are just a couple sets of things that you need to be able to build and run to get that final forecast. So that's been a super simple thing for us to do, and poster 13 will kind of outline how we've done that. But I do just want to say thanks for the plug.
Okay, unless you've got something else to say, because it's 5 o'clock. Or actually, it's 5:01. Oh, geez, the beer's getting warm. We've got to. I want to thank everyone for their energetic participation in all the comments. It's been really good. And on Thursday, we'll revisit, we'll visit some other topics related to MPAS. Thursday afternoon. So I hope most of you will be able to make it, and it'll be as successful as this one.